Learn about machine learning and AI with this comprehensive 11-hour course. This is not just a crash course. This course covers everything from fundamental concepts to advanced algorithms, complete with real-world case studies in recommender systems and predictive analytics. This course goes beyond theory to provide hands-on implementation experience, career guidance, and great insights from industry professionals. It also includes a career guide on how to build a data science career, launch a startup, and prepare for interviews. Tada Van Vahi from LunarTech developed this course.
Over 80% of the companies worldwide are unable to find data scientists and AI professionals to bring their ideas into the market and to become more competitive. In the next decade, the demand for data science and ML professionals is only going to increase, as the market in the data science and AI is projected to pass the $400 billion valuation. About 95% of all employees worldwide are asking their employers to get training in the field of generative AI and machine learning. And if this didn't convince you to get into this lucrative and highly demanded industry, then let me tell you that the salaries of data science and AI professionals are at the moment about the $150,000 up to $200,000 in US. And in some cases, the salaries of most in-demand AI and machine learning professionals can pass the $500,000 US dollars. Welcome to this involved crash course in machine learning and data science. In this 11 hours, you will get a comprehensive overview of the machine learning and data science from different perspectives, both the theory, practice, implementation, career insights, and what you can expect from this career. This will be a great course for anyone who wants to become a machine learning engineer or AI engineer. So here's what we are going to cover as part of this comprehensive crash course in machine learning. So we are going to start with the machine learning roadmap for 2024. Here we are going to provide you a structured overview of the machine learning landscape, helping you understand what it's like to become a machine learning engineer, what you can expect from this career, what exactly you need to learn, what kind of skill sets, from what kind of industries, and also you are going to see what kind of career directions you can take in the field of machine learning. So how you can get into machine learning, how you can kickstart a career, and what is that you need to learn. After that, we are going to get into the top machine learning algorithms. So here you will learn the most important machine learning algorithms, from linear regression to advanced algorithms like the boosting algorithms. Of course, this won't be your comprehensive machine learning course because this is aimed to provide you the basics and the fundamentals. But this would be a great starting point for you to get a taste what it's like to learn the theory of machine learning. You will learn the theory. You will also learn the definitions, the pros and the cons of these algorithms, along with the practical Python implementation. So this will be a great way to learn the basics and to also learn how to implement this in Python. Of course, as a prerequisite for this, it is required that you know basics in Python, like how to create lists, how to work with scikit-learn, or how to create variables. So for this is important. Next up, we have the hands-on case studies. So after learning the basics in machine learning in terms of the theory and implementation in Python, with the real examples, you are ready to get into a hands-on machine learning work. And this won't be just quick case studies that you can complete in 30 minutes, but rather those will be involved 3 different case studies. So we will start with the basics, like performing a behavior analysis and data analytics, which is always a must when it comes to becoming machine learning or AI engineers. So you will learn how to perform data analytics, how to perform customer segmentation using Python, how to perform data wrangling, how to do exploratory data analysis, all in Python, and then to make those important conclusions and tell your data story. This is really important as an AI professional to know data science and data analytics. So this first case study, which is the Superstore customer behavior analysis that will be conducted and presented to you by Vahe Aslayan, co-founder of LunarTech, that will provide you good insights into the basics of machine learning, and how to do a data analytics and data science in a real-life case study. In the second case study, we will then get more hands-on with machine learning, and we will be predicting the Californian house prices. We will do exploratory data analysis. We will use Python to clean the data, use statistics to perform outlier detection, data visualization. We will also perform causal analysis, and we will be using linear regression to perform the predictions. By leveraging practical data analytics, but this time also data science skills, and combining this with Python libraries like scikit-learn. And the third case study will be about building a movie recommender system. So here we will explore the NLP, the natural language preprocessing, another very important topic in the field of AI and machine learning these days. And here we will be using NLP. We will use also machine learning data science too to develop a recommender algorithm. So this project will then enhance your skills in the text data analysis, how to process this text data, how to use Python for doing that, as well as practical machine learning applications like building a recommender system. Keep in mind that you can also put these case studies on your resume to showcase your experience. After we are done with these 3 end-to-end involved case studies, we are going to provide you career insights. Now, as a data science and AI professional, you have 2 choices. You can either decide to get into the corporate world, so become a data scientist or AI professional, or you can decide to build your own startup. And to provide you information on both of these directions, in the first conversation, you will join me and the data science manager from Allianz, Cornelius, where you can learn from him how to break into the field of data science and machine learning, especially from non-traditional background. Here you can get a lot of tips on succeeding in this field, how to get promoted, what to expect from interviews, what is like that selection process, and much more about data science and AI corporate career. So once we are done with that conversation, then we will provide you the next choice, which is about the building of a startup as a machine learning or AI professional. So here you can then listen to the conversation between co-founder of LunarTech, Vahe Aslayan, and a serial entrepreneur and a successful investor, Adam Coffey. So here, Adam Coffey will be then provide you a lot of insights on how to launch a startup, how to raise funds, what to expect from this type of career. So once we are done with all this, with this career insight as well, we will then get into the final part of this course, which is about interview preparation. We will conclude with providing you the most popular machine learning interview questions with the corresponding detailed answers. This will be great for anyone who wants to ace their interviews and who is now preparing for machine learning or AI interviews. This crash course for 11 hours is more than just a short introduction. It's an involved, comprehensive overview of everything that you can expect from the world of machine learning and AI. Want to become more hands-on and get the entire comprehensive overview and learn everything in one place to become a job-ready machine learning and AI professional, then make sure to check the lunartech.ai, our data science bootcamps, and many other courses that will provide you that all-in-one approach to become a job-ready professional. If you like this video, make sure to like, subscribe, and comment. So if you're ready, I'm really excited. Let's get started. Hi there! In this video, we are going to talk about how you can get into machine learning in 2024. First, we are going to start with all the skills that you need in order to get into machine learning. Step by step, what are the topics that you need to cover and what are the topics that you need to study in order to get into machine learning. We are going to talk about what is machine learning. Then we are going to cover step by step what are the exact topics and the skills that you need in order to become a machine learning researcher or just get into machine learning. Then we're going to cover the type of exact projects you can complete, so examples of portfolio projects, in order to put it on your resume and to start to apply for machine learning related jobs. And then we are going to also talk about the type of industries that you can get into once you have all the skills and you want to get into machine learning. So the exact career path and what kind of business titles are usually related to machine learning. We are also going to talk about the average salary that you can expect for each of those different machine learning related positions. At the end of this video, you are going to know what exactly machine learning is, where is it used, what kind of skills are there that you need in order to get into machine learning in 2024, and what kind of career path with what kind of compensation you can expect with the corresponding business titles when you want to start your career in machine learning. I'm Datev, co-founder of LunarTech, and I come from econometrical and statistical background. I have been in the tech field and specifically in data science and AI for the last 5 years, working across different data science and AI projects across the globe. And now I'm going to tell you what exactly machine learning is and what are the skill sets that you need in order to get into machine learning in 2024. So without further ado, let's get started. So what is machine learning? Machine learning is a branch of artificial intelligence, of AI, that helps to build models based on the data and then learn from this data in order to make different decisions. So we will first start with the definition of machine learning, what machine learning is, and what are the different sorts of applications of machine learning that you most likely have heard of, but you didn't know that it was based on machine learning. So machine learning is a branch of artificial intelligence that is using data in order to learn from this data by using different sorts of algorithms. And it is being used across different industries, starting from healthcare till entertainment, in order to improve the customer experience, identify customer behavior, improve the sales for the businesses, and it also helps governments to make decisions. So it really has a wide range of applications. So let's start with the healthcare. For instance, machine learning is being used in the healthcare to help with the diagnosis of diseases. It can help to diagnose cancer. During the COVID, it helped many hospitals to identify whether people are getting more severe side effects or they are getting pneumonia based on those pictures. And that was all based on machine learning and specifically computer vision. In the healthcare, it's also being used for drug discovery, it's being used for personalized medicine, for personalizing treatment plans, to improve the operations of the hospitals, to understand what is the amount of people and patients that hospital can expect in each of those days per week, and also to estimate the amount of doctors that needs to be available, the amount of people that the hospital can expect in the emergency room based on the day or the time of the day. And this is basically not a machine learning application. Then we have machine learning in finance. Machine learning is being largely used in finance for different applications, starting from fraud detection in credit cards or in other sorts of banking operations. It's also being used in trading, specifically in combination with quantitative finance, to help traders to make decisions whether they need to go short or long into different stocks or bonds or different assets just in general, to estimate the price that those stocks will have and assets in real time in the most accurate way. It's also being used in retail. It helps to understand and estimate the demand for certain products in certain warehouses. It also helps to understand what is the most appropriate or closest warehouses that the items for that corresponding customer should be shipped. So it's optimizing the operations. It's also being used to build different recommender systems and search engines like the infamous Amazon is doing. So every time when you go to Amazon and you are searching for a project or product, you will most likely see many article recommenders. And that's based on machine learning, because Amazon is gathering the data and comparing your behavior. So based on what you have bought, based on what you are searching to other customers and those items to other items, in order to understand what are the items that you will most likely will be interested in and eventually will buy it. And that's exactly based on machine learning and specifically different sorts of recommender system algorithm. And then we have marketing, where machine learning is being heavily used, because this can help to understand what are these different tactics and specific targeting groups that you belong, and how retailers can target you in order to reduce their marketing costs and to result in high conversion rates, so to ensure that you buy their product. Then we have machine learning in autonomous vehicles. That's based on machine learning and specifically deep learning applications. And then we have also natural language preprocessing, which is highly related to the famous ChatGPT. I'm sure you're using it, and that's based on the machine learning and specifically the large language models. So the transformers, large language models, where you will going and providing your text and then question, and the ChatGPT will provide answers to you, or in fact any other virtual assistant or chatbots. Those are all based on machine learning. And then we have also smart home devices. So Alexa is based on machine learning. Also in agriculture, machine learning is being used heavily these days to estimate what the weather conditions will be, to understand what will be the production of different plants, what will be the outcome of this, to understand and to make decisions, also how they can optimize those crop yields, to monitor soil health, and for different sorts of applications that can just in general improve the revenue for the farmers. And then we have, of course, in the entertainment, so the vivid example is Netflix, that uses the data that you are providing related to the movies, and also based on what kind of movies you are watching. Netflix is building this super smart recommender system to recommend you movies that you most likely will be interested in, and you will also like it. So in all this, machine learning is being used, and it's actually super powerful topic and super powerful field to get into. And in the upcoming 10 years, this is only going to grow. So if you have made that decision, or you are about to make that decision to get into machine learning, continue watching this video, because I'm going to tell you exactly what kind of skills you need and what kind of practice projects you can complete in order to get into machine learning in 2024. So you first need to start with mathematics. You also need to know Python. You also need to know statistics. You will need to know machine learning, and you will need to know some NLP to get into machine learning. So let's now unpack each of those skill sets. So independent the type of machine learning you are going to do, you need to know mathematics. And specifically, you need to know linear algebra. So you need to know what is matrix multiplication, what are the vectors, matrices, dot product. You need to know how you can multiply those different matrices, matrix with vectors, what are these different rules, the dimensions. Also, what does it mean to transform a matrix, the inverse of the matrix, identity matrix, diagonal matrix. Those are all concepts as part of linear algebra that you need to know as part of your mathematical skill set in order to understand those different machine learning algorithms. Then, as part of your mathematics, you also need to know calculus and specifically differential theory. So you need to know these different theorems such as chain rule, the rule of differentiating when you have sum of instances, when you have constant multiply with an instance, when you have sum, but also subtraction, division, multiplication of two items, and then you need to take the derivative of that. What is this idea of derivative? What is the idea of partial derivative? What is the idea of Hessian? So first order derivative, second order derivative, and it would be also great to know a basic integration theory. So we have differentiation, and the opposite of it is integration theory. So this is kind of basic. You don't need to know too much when it comes to calculus, but those are basic things that you need to know in order to succeed in machine learning. So, then the next concepts such as discrete mathematics. So you need to know what is this idea of graph theory, what are these combinations, combinators, what is this idea of complexity, which is important when you want to become a machine learning engineer, because you need to understand what is this big O notation. So you need to understand what is this complexity of n squared, complexity of n, complexity of n log n. And about that, you need to know some basic mathematics which comes from usually high school. So you need to know multiplication, division. You need to understand multiplying amounts which are within the parentheses. You need to understand different symbols that represent mathematical values. You need to know this idea of using x's, y's, and then what is x squared, what is y squared, what is x to the power 3, so different exponents of the different variables. Then you need to know what is logarithm at the base of 2, what is logarithm at the base of e, and then at the base of 10. What is the idea of e? So what is the idea of pi? What is this idea of exponent, logarithm, and how does those transform when it comes to taking derivative of the logarithm, taking the derivative of the exponent? Those are all values and all topics that are actually quite basic. They might sound complicated, but they are actually not. So if someone explains you clearly, then you will definitely understand it from the first go. And for this, to understand all those different mathematical concepts, so linear algebra, calculus, differential theory, and then discrete mathematics and those different symbols, you need to go, for instance, and look for courses or YouTube tutorials that are about basic mathematics for machine learning and AI. Don't go and look further. You can check, for instance, Khan Academy, which is quite favorite when it comes to learning math, both for uni students and also for just people who want to learn mathematics. And this will be your guide. Or you can check our resources at lunartech.ai, because we are going also to provide these resources for you in case you want to learn mathematics for your machine learning journey. The next skill set that you need to gain in order to break into machine learning is the statistics. So you need to know, this is a must, statistics, if you want to get into machine learning and in AI in general. So there are a few topics that you must study when it comes to statistics. And those are descriptive statistics, multivariate statistics, inferential statistics, probability distribution, and some Bayesian thinking. So let's start with descriptive statistics. When it comes to descriptive statistics, you need to know what is this idea of mean, median, standard deviation, variance, and just in general how you can analyze the data with using these descriptive measures. So distance measures, but also variational measures. Then the next topic area that you need to know as part of your statistical journey is the inferential statistics. So you need to know those infamous theories such as central limit theorem, the law of large numbers, and how you can relate to this idea of population, sample, unbiased sample, and also a hypothesis testing, confidence interval, statistical significance, and how you can test different theories by using this idea of statistical significance. What is the power of the test? What is type 1 error? What is type 2 error? So this is super important for understanding different sorts of machine learning applications if you want to get into machine learning. Then you have probability distributions and this idea of probabilities. So to understand those different machine learning concepts, you need to know what are probabilities. So what is this idea of probability? What is this idea of sample versus population? What does it mean to estimate probability? What are those different rules of probability? So conditional probability and those probability values and rules that usually you can apply when you have a probability of multipliers, probability of two sums, and then you need to understand some popular, and you need to know some popular probability distribution functions. And those are Bernoulli distribution, binomial distribution, normal distribution, uniform distribution, exponential distribution. So those are all super important distributions that you need to know in order to understand this idea of normality, normalization, also this idea of Bernoulli trials, and relating different probability distributions to different higher level statistical concepts. So rolling a dice, the probability of it, how it is related to Bernoulli distribution or to binomial distribution. And those are super important when it comes to hypothesis testing, but also for many other machine learning applications. So then we have the Bayesian thinking. This is super important when it comes to more advanced machine learning, but also some basic machine learning. You need to know what is the Bayes theorem, which arguably is one of the most popular statistical theorems out there, comparable also to the central limit theorem. You need to know what is conditional probability, what is this Bayes theorem, and how does it relate to conditional probability, what is this Bayesian statistics idea at very high level. You don't need to know everything in super detailed, but you need to know these concepts, at least at high level, in order to understand machine learning. So to learn statistics and the fundamental concepts of statistics, you can check out the Fundamentals to Statistics course at lunartech.ai. Here you can learn all these required concepts and topics, and you can practice it in order to get into machine learning and to gain the statistical skills. The next skill set that you must know is the Fundamentals to Machine Learning. So this covers not only the basics of machine learning, but also the most popular machine learning algorithms. So you need to know this different mathematical side of these algorithms, step by step how they work, what are the benefits of them, what are the demerits, and which one to use for what type of applications. So you need to know this categorization of supervised versus unsupervised versus semi-supervised. Then you need to know what is this idea of classification, regression, or clustering. Then you need to know also time series analysis. You also need to know these different popular algorithms, including linear regression, also logistic regression, LDA, so linear discriminant analysis. You need to know KNN. You need to know decision trees, both classification and regression case. You need to know random forest, bagging, but also boosting. So popular boosting algorithms like light GBM, so gradient boosting models. And you need to know XGBoost. You also need to know some unsupervised learning algorithms such as k-means, usually used for clustering. You need to know dbScan, which becomes more and more popular in clustering algorithms. You also need to know hierarchical clustering. And for all this type of models, you need to understand the idea behind them, what are the advantages and disadvantages, whether they can be applied for unsupervised versus supervised versus semi-supervised. You need to know whether they are for regression, classification, or for clustering. Beside of these popular algorithms and models, you also need to know the basics of training a machine learning model. So you need to know this process behind training, validating, and testing your machine learning algorithms. So you need to know what does it mean to perform hyperparameter tuning, what are those different optimization algorithms that can be used to optimize your parameters, such as GD, SGD with momentum, ADAM, and ADAM-V. You also need to know the testing process, this idea of splitting the data into train, validation, and then test. You need to know resampling techniques, why are they used, including the bootstrapping and cross-validation, and there's different sorts of cross-validation techniques such as leave one out cross-validation, k-fold cross-validation, validation set approach. You also need to know this idea of matrix and how you can use different matrix to evaluate your machine learning models, such as classification type of metrics like F1 score, F-beta, precision, recall, cross entropy, and also you need to know some matrix that can be used to evaluate regression type of problems, like the mean squared error, so MSE, root mean squared error, RMSE, MAA, so the absolute version of those different sorts of errors, or the residual sum of squares. For all these cases, you not only need to know high level what those algorithms or those topics or concepts are doing, but you actually need to know the mathematics behind it, their benefits, the disadvantages, because during the interviews, you can definitely expect questions that will test not only your high level understanding, but also this background knowledge. If you want to learn machine learning and you want to gain those skills, then feel free to check out my Fundamentals to Machine Learning course, which is part of the Ultimate Data Science Bootcamp at lunartech.ai, or you can also check out and download for free the Fundamentals to Machine Learning handbook that I published with freeCodeCamp. Then the next skill set that you definitely need to gain is the knowledge in Python. Python is actually one of the most popular programming languages out there, and it's being used across software engineers, AI engineers, machine learning engineers, data scientists. So this is the universal language, I would say, when it comes to programming. So if you're considering getting into machine learning in 2024, then Python will be your friend. So knowing the theory is one thing, then implementing it in the actual job is another. And that's exactly where Python comes in handy. So you need to know Python in order to perform descriptive statistics, in order to train machine learning model or more advanced machine learning models or deep learning models. You can use for training, validation, and for testing of your models, and also for building different sorts of applications. So Python is super powerful, therefore it's also gaining such a high popularity across the globe because it has so many libraries. It has TensorFlow, PyTorch, both that are must if you want to not only get into machine learning, but also the advanced levels of machine learning. So if you are considering the AI engineering jobs or machine learning engineering jobs, and you want to train, for instance, deep learning models, or you want to build large language models or generative AI models, then you definitely need to learn PyTorch and TensorFlow, which are frameworks that are used in order to implement different deep learning, which are advanced machine learning models. Here are a few libraries that you need to know in order to get into machine learning. So you definitely need to know Pandas, NumPy, you need to know scikit-learn, SciPy, you also need to know NLTK for the text data, you also need to know TensorFlow and PyTorch for a bit more advanced machine learning. And beside this, there are also data visualization libraries that I would definitely suggest you to practice with, which are the Matplotlib, and specifically the PyPlot, and also the Seaborn. When it comes to Python, besides knowing how to use libraries, you also need to know some basic data structures. So you need to know what are these variables, how you can create variables, what are the matrices, arrays, how the indexing works, and also what are the lists, what are the sets, so unique lists, what are the ways that you can, what are the different operations you can perform, how does the sorting, for instance, work. I would definitely suggest to know some basic data structures and algorithms such as binary sort, so an optimal way to sort your arrays. You also need to know the data processing in Python, so you need to understand how to identify missing data, how to identify duplicates in your data, how to clean this, how to perform feature engineering, so how to combine multiple variables or to perform operations to create new variables. You also need to know how you can aggregate your data, how you can filter your data, how you can sort your data. And of course, you also need to know how you can perform A/B testing in your Python, and how you can train machine learning models, how you can test it, and how you can evaluate them, and also visualize the performance of it. If you want to learn Python, then the easiest thing you can do is just to Google for Python for data science or Python for machine learning tutorials or blogs, or you can even try out the Python for Data Science course at lunartech.ai in order to learn all these basics and the usage of these libraries and some practical examples when it comes to Python for machine learning. The next skill set that you need to gain in order to get into machine learning is the basic introduction to NLP, natural language processing. So you need to know how to work with text data, given that these days the text data is the cornerstone of all these different advanced algorithms such as GPTs, transformers, the attention mechanisms. So those applications that you see as part of building chatbots or this personalized applications based on text data, they are all based on NLP. So therefore, you need to know these basics of NLP to just get started with machine learning. So you need to know this idea of text data, what are those strings, how you can clean text data, so how you can clean those dirty data that you get, and what are the steps involved, such as lowercasing, removing punctuation, tokenization, also what is this idea of stemming, lemmatization, stop words, how you can use the NLTK in Python in order to perform this cleaning. You also need to know this idea of embeddings, and you can also learn this idea of the TF-IDF, which is a basic NLP algorithm. You also can learn this idea of word embeddings, the subword embeddings, and the character embeddings. If you want to learn the basics of NLP, you can check out those concepts and learn them as part of the blogs. There are many tutorials on YouTube. You can also try the introduction to NLP course at lunartech.ai in order to learn these different basics that form the NLP. If you want to go beyond this intro till medium level machine learning, and you also want to learn a bit more advanced machine learning, and this is something that you need to know after you have gained all these previous skills that I mentioned, then you can gain this knowledge and the skill set by learning deep learning, and also you can consider getting into generative AI topics. So you can, for instance, learn what are the RNNs, what are the ANNs, what are the CNNs. You can learn what is this autoencoder concept, what are the variational autoencoders, what are the generative adversarial networks, so GANs. You can understand what is this idea of reconstruction error. You can understand these different sorts of neural networks. What is this idea of backpropagation, the optimization of these algorithms by using these different optimization algorithms such as GD, SGD, SGD momentum, ADAM-W, RMS-prop. You can also go one step beyond, and you can get into generative AI topics such as the variational autoencoders, like I just mentioned, but also the large language models. So if you want to move towards the NLP side of generative AI and you want to know how the ChatGPT has been invented, how the GPTs work, or the BERT model, then you will definitely need to get into this topic of language models. So what are the n-grams? What is the attention mechanism? What is the difference between the self-attention and attention? What is one-head self-attention mechanism? What is multi-head self-attention mechanism? You also need to know at high level this encoder-decoder architecture of transformers. So you need to know the architecture of transformers and how they solve different problems of recurrent neural networks, so RNNs and LSTMs. You can also look into this encoder-based or decoder-based algorithms such as GPTs or BERT model. And those all will help you to not only get into machine learning, but also stand out from all the other candidates by having this advanced knowledge. Let's now talk about different sorts of projects that you can complete in order to train your machine learning skill set that you just learned. So there are a few projects that I suggest you to complete, and you can put this on your resume to start to apply for machine learning roles. The first application, the project that I would suggest you to do, is building a basic recommender system, whether it's a job recommender system or a movie recommender system. In this way, you can showcase how you can use, for instance, text data from those job advertisements, how you can use numeric data such as the ratings of the movies in order to build a top-end recommender system. This will showcase your understanding of the distance measures such as cosine similarity, the scan algorithm idea, and this will help you to tackle this specific area of data science and machine learning. The next project I would suggest you to do will be to build a regression-based model. So in this way, you will showcase that you understand this idea of regression, how to work with predictive analytics and predictive model that has a dependent variable, a response variable that is in the numeric format. So here, for instance, you can estimate the salaries of the jobs based on the characteristics of the job, based on this data, which you can get, for instance, from open source web pages such as Kaggle. And you can then use different sorts of regression algorithms to perform your predictions of the salaries, evaluate the model, and then compare the performance of these different machine learning regression-based algorithms. For instance, you can use the linear regression, you can use the decision trees regression version, you can use the random forest, you can use GBM, XGBoost, in order to showcase and then in one graph to compare this performance of these different algorithms by using a single regression ML model metrics. So for instance, the RMSE. This project will showcase that you understand how you can train a regression model, how you can test it and validate it, and it will showcase your understanding of optimization of this regression algorithm. You understand this concept of hyperparameter tuning. The next project that I would suggest you to do in order to showcase your classification knowledge, so when it comes to predicting a class for an observation given the feature space, would be to build a classification model that would classify emails being a spam or not a spam. So you can use a publicly available data that will be describing a specific email, and then you will have multiple emails. And the idea is to build a machine learning model that would classify the email to the class 0 and class 1, where class 0, for instance, can be your not being a spam and 1 being a spam. So with this binary classification, you will showcase that you know how to train a machine learning model for classification purposes. And you can here use, for instance, logistic regression. You can use also the decision trees for classification case. You can also use random forest, the XGBoost for classification, GBM for classification. And with all these models, you can then obtain the performance metrics such as F1 score, or you can plot the ROP curve or the area under the curve metrics, and you can also compare those different classification models. So in this way, you will also tackle another area of expertise when it comes to the machine learning. Then the final project that I would suggest you to do would be from the unsupervised learning to showcase another area of expertise. And here you can, for instance, use data to your customers into good, better, and best customers based on their transaction history, the amount of money that they are spending in the store. So in this case, you can, for instance, use k-means, dbScan, hierarchical clustering, and then you can evaluate your clustering algorithms and then select the one that performs the best. So you will then, in this case, cover yet another area of machine learning, which would be super important to showcase that you can not only handle recommender systems or supervised learning, but also unsupervised learning. And the reason why I suggest you to cover all these different areas and complete these 4 different projects is because in this way, you will be covering different expertise and areas of machine learning. So you will be also putting projects on your resume that are covering different sorts of algorithms, different sorts of metrics and approaches, and it will showcase that you actually know a lot from machine learning. Now, if you want to go beyond the basic or medium level and you want to be considered for medium or advanced machine learning levels and positions, you also need to know a bit more advanced, which means that you need to complete a bit more advanced projects. For instance, if you want to apply for generative AI related or large language models related positions, I would suggest you to complete a project where you are building a very basic large language model, and specifically the pre-training process, which is the most difficult one. So in this case, for instance, you can build a baby GPT, and I'll put here a link that you can follow where I'm building a baby GPT, a basic pre-trained GPT algorithm, where I am using a text data, publicly available data, in order to process data in the same way like GPT is doing, and the encoder part of the transformers. In this way, you will showcase to your hiring managers that you understand this architecture behind transformers, architecture behind the large language models and the GPTs, and you understand how you can use PyTorch in Python in order to do this advanced NLP and generative AI task. And finally, let's now talk about the common career path and the business titles that you can expect from a career in machine learning. So assuming that you have gained all the skills that are must for breaking into machine learning, there are different sorts of business titles that you can apply in order to get into machine learning. So when it comes to machine learning, you can get into machine learning, and there are different fields that are covered as part of this. So first we have the general machine learning researcher. Machine learning researcher is basically doing research, so training, testing, evaluating different machine learning algorithms. They are usually people who come from academic background, but it doesn't mean that you cannot get into machine learning research without getting a degree in statistics, mathematics, or in machine learning specifically. Not at all. So if you have this desire and this passion for reading, doing research, and you don't mind reading research papers, then machine learning researcher job would be a good fit for you. So machine learning combined with research then sets you for the machine learning researcher role. Then we have the machine learning engineer. So machine learning engineer is the engineering version of the machine learning expertise, which means that we are combining machine learning skills with the engineering skills such as productionization, building pipelines, so end-to-end robust pipelines, scalability of the model, considering all these different aspects of the model, not only from the performance side when it comes to the quality of the algorithm, but also the scalability of it and when putting it in front of many users. So when it comes to combining engineering with machine learning, then you get machine learning engineering. So if you're someone who is a software engineer and you want to get into machine learning, then machine learning engineering would be the best fit for you. So for machine learning engineering, you not only need to have all these different skills that I already mentioned, but you also need to have this good grasp of scalability of algorithms, the data structures and algorithms type of skill set, the complexity of the model, also system design. So this one converges more towards and similar to the software engineering position combined with machine learning rather than your pure machine learning or AI role. Then we have the AI research versus AI engineering position. So the AI research position is similar to the machine learning research position, and the AI engineer position is similar to the machine learning engineer position, with only single difference. When it comes to machine learning, we are specifically talking about this traditional machine learning. So linear regression, logistic regression, and also random forest, XGBoost, bagging. And when it comes to AI research and AI engineer position, here we are tackling more the advanced machine learning. So here we are talking about deep learning models such as RNNs, LSTMs, GRUs, CNN, so computer vision applications. And we are also talking about generative AI models, large language models. So we are talking about the transformers, the implementation of transformers, the GPTs, T5, all these different algorithms that are from more advanced AI topics rather than traditional machine learning. For those, you will then be applying for AI research and AI engineering positions. And finally, you have these different sorts of observations, niches from AI, for instance, NLP research, NLP engineer, or even data science positions for which you will need to know machine learning, and knowing machine learning will set you apart for these sorts of positions. So also the business titles such as data science or technical data science positions, NLP researcher, NLP engineer, for this all, you will need to know machine learning. And knowing machine learning will help you to break into those positions and those career paths.
In this lecture, we will go through the basic concepts in machine learning that is needed to understand and follow conversations and solve main problems using machine learning. Strong understanding of machine learning basics is an important step for anyone looking to learn more about or work with machine learning. We'll be looking at the three concepts in this tutorial. We will define and look into the difference between supervised and unsupervised machine learning models. Then we will look into the difference between the regression and classification type of machine learning models. After this, we will look into the process of training machine learning models from scratch and how to evaluate them by introducing performance metrics, what you can use depending on the type of machine learning model or problem you are dealing with. So whether it's a supervised or unsupervised, whether it's regression versus classification type of problem. Machine learning methods are categorized into two types depending on the existence of the labeled data in the training dataset, which is especially important in the training process. So we are talking about the so-called dependent variable that we saw in the section of fundamentals to statistics. Supervised and unsupervised machine learning models are two main types of machine learning algorithms. One key difference between the two is the level of supervision during the training phase. Supervised machine learning algorithms are guided by the labeled examples, while unsupervised algorithms are not. This learning model is more reliable, but it also requires a larger amount of labeled data, which can be time-consuming and quite expensive to obtain. Examples of supervised machine learning models include regression and classification type of models. On the other hand, unsupervised machine learning algorithms are trained on unlabeled data. The model must find patterns and relationships in the data without the guidance of correct outputs, so we no longer have a dependent variable. So, unsupervised ML models require training data that consists only of independent variables or the features, and there is no dependent variable or labeled data that can supervise the algorithm while learning from the data. Examples of unsupervised models are clustering models and outlier detection techniques. Supervised machine learning methods are categorized into two types depending on the type of dependent variable they are predicting. So we have regression type and we have classification type. Some key differences between regression and classification include output type. So the regression algorithms predict continuous values, while the classification algorithms predict categorized values. Some key differences between regression and classification include the output type, the evaluation metrics, and their applications. So, with regards to the output type, regression algorithms predict continuous values, while classification algorithms predict categorical values. With regards to the evaluation metric, different evaluation metrics are being used for regression and classification tasks. For example, mean squared error is commonly used to evaluate regression models, while accuracy is commonly used to evaluate classification models. When it comes to applications, regression and classification models are used in entirely different types of applications. Regression models are often used for prediction tasks, while classifications are used for decision-making tasks. Regression algorithms are used to predict a continuous value, such as price or probability. For example, a regression model might be used to predict the price of a house based on its size, location, or other features. Examples of regression type of machine learning models are linear regression, fixed effect regression, XGBoost regression, etc. Classification algorithms, on the other hand, are used to predict the categorical value. These algorithms take an input and classify it to one of the several predetermined categories. For example, a classification model might be used to classify emails as spam or as not a spam, or to identify the type of animal in an image. Examples of classification type of machine learning models are logistic regression, XGBoost classification, random forest classification. Let us now look into different type of performance metrics we can use in order to evaluate different type of machine learning models. For regression models, common evaluation metrics include residual sum of squared, which is the RSS, mean squared error, which is the MSE, the root mean squared error, or RMSE, and the mean absolute error, which is the MAE. These metrics measure the difference between the predicted values and the true values, with the lower value indicating a better fit for the model. So let's go through these metrics one by one. The first one is the RSS, or the residual sum of squares. This is a metric commonly used in the setting of linear regression when we are evaluating the performance of the model in estimating the different coefficients. And here the beta is a coefficient, and the yi is our dependent variable value, and the y hat is the predicted value. As you can see, the RSS, or the residual sum of square, or the beta, is equal to sum of all the squared of yi minus y hat across all I is equal to 1 till n, where I is the index of the each row or the individual or the observation included in the data. The second metric is the MSE, or the mean squared error, which is the average of the squared differences between the predicted values and the true values. So as you can see, MSE is equal to 1 divided to n, and then sum across all I, yi minus y hat squared. As you can see, the RSS and the MSE are quite similar in terms of their formulas. The only difference is that we are adding a 1 divided to n, and then this makes it the average across all the square differences between the predicted value and the actual true value. A lower value of MSE indicates a better fit. The RMSE, which is the root mean squared error, is the square root of the MSE. So as you can see, it has the same formula as MSE, only with the difference that we are adding a square root on the top of that formula. A lower value of RMSE indicates a better fit. And finally, the MAE, or the mean absolute error, is the average absolute difference between the predicted values, so the y hat, and the true values, or yi. A lower value of this indicates a better fit. The choice of a regression metrics depends on the specific problem you are trying to solve and the nature of your data. For instance, the MSE is commonly used when you want to penalize large errors more than the small ones. MSE is sensitive to outliers, which means that it may not be the best choice when your data contains many outliers or extreme values. RMSE, on the other hand, which is the square root of the MSE, makes it easier to interpret. So it's easier interpretable because it's in the same units as the target variable. It is commonly used when you want to compare the performance of different models or when you want to report the error in a way that it's easier to understand and to explain. The MIA is commonly used when you want to penalize all errors equally, regardless of their magnitude, and MIA is less sensitive to outliers compared to MSE. For classification models, common evaluation metrics include accuracy, precision, recall, and F1 score. These metrics measure the ability of the machine learning model to correctly classify instances into the correct categories. Let's briefly look into these metrics individually. So the accuracy is a proportion of correct predictions made by the model. It's calculated by taking the correct predictions, so the correct number of predictions, and divide to all number of predictions, which means correct predictions plus incorrect predictions. Next, we will look into the precision. So precision is the proportion of true positive predictions among all positive predictions made by the model, and it's equal to true positive divided to true positive plus false positive, so all number of positives. True positives are cases where the model correctly predicts a positive outcome, while false positives are the cases where the model incorrectly predicts a positive outcome. Next metric is recall. Recall is a proportion of true positive predictions among all actual positive instances. It's calculated as the number of true positive predictions divided by the total number of actual positive instances, which means dividing the true positive 2 true positive plus false negative. So, for example, let's say we are looking into a medical test. A true positive would be a case where the test correctly identifies a patient as having a disease, while a false positive would be a case where the test incorrectly identifies a healthy patient as having the disease. And the final score is the F1 score. The F1 score is the harmonic mean or the usual mean of the precision and recall, with a higher value indicating a better balance between precision and recall, and it's calculated as the 2 times recall times precision divided to recall plus precision. For unsupervised models such as clustering models, whose performance is typically evaluated using metrics that measure the similarity of the data points within a cluster and the dissimilarity of the data points between different clusters, we have 3 types of metrics that we can use. Homogeneity is a measure of the degree to which all of the data points within a single cluster belong to the same class. A higher value indicates a more homogeneous cluster. So as you can see, homogeneity of H, where H is simply the short way of describing homogeneity, is equal to 1 minus conditional entropy given cluster assignments divided to the entropy of predicted class. If you're wondering what this entropy is, then stay tuned as we are going to discuss this entropy whenever we will discuss the clustering as well as decision trees. The next metric is the silhouette score. Silhouette score is a measure of the similarity of the data point to its own cluster compared to the other clusters. A higher silhouette score indicates that the data point is well matched to its own cluster. This is usually used for dbScan or k-means. So here, the silhouette score can be represented by this formula. So the SO, or the silhouette score, is equal to BO minus AO divided to the maximum of AO and BO, where SO is the silhouette coefficient of the data point characterized by O, AO is the average distance between O and all the other data points in the cluster to which O belongs, and the BO is the minimum average distance from O to all the clusters to which O does not belong. The final metrics we will look into is the completeness. Completeness is another measure of the degree to which all of the data points that belong to a particular class are assigned to the same cluster. A higher value indicates a more complete cluster. Let's conclude this lecture by going through the step-by-step process of evaluating a machine learning model at a very simplified version, since there are many additional considerations and techniques that may be needed depending on a specific task and the characteristics of the data. Knowing how to properly train a machine learning model is really important, since this defines the accuracy of the results and conclusions you will make. The training process starts with the preparing of the data. This includes splitting the data into training and test sets, or if you are using more advanced resampling techniques that we will talk about later, then splitting your data into multiple sets. The training set of your data is used to feed the model. If you have also a validation set, then this validation set is used to optimize your hyperparameters and to pick the best model, while the test set is used to evaluate the model performance. When we will approach more lectures in this section, we will talk in detail about these different techniques, as well as what the training means, what the test means, what validation means, as well as what the hyperparameter tuning means. Secondly, we need to choose an algorithm or set of algorithms and train the model on the training data and save the fitted model. There are many different algorithms to choose from, and the appropriate algorithm will depend on the specific task and the characteristics of the data. As a third step, we need to adjust the model parameters to minimize the error on the training set by performing hyperparameter tuning. For this, we need to use validation data, and then we can select the best model that results in the least possible validation error rate. In this step, we want to look for the optimal set of parameters that are included as part of our model to end up with a model that has the least possible error, so it performs in the best possible way. In the final 2 steps, we need to evaluate the model. We are always interested in a test error rate and not the training or the validation error rates, because we have not used the test set, but we have used the training and validation sets. So this test error rate will give you an idea of how well the model will generalize to the new, unseen data. We need to use the optimal set of parameters from hyperparameter tuning stage and the training data to train the model again with these hyperparameters and with the best model. So we can use the best fitted model to get the predictions on the test data, and this will help us to calculate our test error rate. Once we have calculated the test error rate and we have also obtained our best model, we are ready to save the predictions. So once we are satisfied with the model performance and we have tuned the parameters, we can use it to make predictions on a new unseen data, on the test data, and compute the performance metrics for the model using the predictions and the real values of the target variable from the test data. And this completes this lecture. So in this lecture, we have spoken about the basics of machine learning. We have discussed the difference between the unsupervised and supervised learning models, as well as regression versus classification. We have discussed in detail the different type of performance metrics we can use to evaluate different type of machine learning models, as well as we have looked into the simplified version of the step-by-step process to train a machine learning model. In this lecture, lecture number 2, we will discuss a very important concept which you need to know before considering and applying any statistical or machine learning model. Here I'm talking about the bias of the model and the variance of the model and the trade-off between the two, which we call bias-variance trade-off. Whenever you are using a statistical, econometrical, or machine learning model, no matter how simple the model is, you should always evaluate your model and check its error rate. In all these cases, it comes down to the trade-off you make between the variance of the model and the bias of your model, because there is always a catch when it comes to the model choice and the performance. Let us firstly define what bias and the variance of the machine learning model are. The inability of the model to capture the true relationship in the data is called bias. Hence, the machine learning models that are able to detect the true relationship in the data have low bias. Usually, complex models or more flexible models tend to have a lower bias than simpler models. So mathematically, the bias of the model can be expressed as the expectation of the difference between the estimate and the true value. Let us also define the variance of the model. The variance of the model is the inconsistency level or the variability of the model performance when applying the model to different data sets. When the same model that is trained using training data performs entirely differently than on the test data, this means that there is a large variation or variance in the model. Complex models or more flexible models tend to have a higher variance than simpler models. In order to evaluate the performance of the model, we need to look at the amount of error that the model is making. For simplicity, let's assume we have the following simple regression model, which aims to use a single independent variable x to model the numeric y-dependent variable. That is, we fit our model on our training observations where we have a pair of independent and dependent variables, x1, y1, x2, y2, up to xn, yn, and we obtain an estimate for our training observations, f hat. We can then compute this, let's say f hat x1, f hat x2 up to f hat xn, which are the estimates for our dependent variable y1, y2 up to yn. And if these are approximately equal to these actual values, so y1 hat is approximately equal to y1, y2 hat is approximately equal to y2 hat, etc., then the training error rate would be small. However, if we are really interested in whether our model is predicting the dependent variable appropriately, we want to, instead of looking at the training error rate, we want to look at our test error rate. So the error rate of the model is the expected square difference between the real test values and their predictions, where the predictions are made using the machine learning model. We can rewrite this error rate as the sum of two quantities, where as you can see, the left part is the amount of fx minus f hat x squared, and the second entity is the variance of the error term. So the accuracy of y hat as a prediction for y depends on the two quantities, which we can call the reducible error and the irreducible error. So this is the reducible error equal to fx minus f hat x squared, and then we have our irreducible error or the variance of epsilon. So the accuracy of y hat as a prediction for y depends on the two quantities, which we can call the reducible error and the irreducible error. In general, the f hat will not be a perfect estimate for f, and this inaccuracy will introduce some errors. This error is reducible since we can potentially improve the accuracy of F-hat by using the most appropriate machine learning model and the best version of it to estimate the F. However, even if it was possible to find a model that would estimate F perfectly so that the estimated response took the form of y hat is equal to fx, our prediction would still have some error in it. This happens because y is also a function of the error rate epsilon, which by definition cannot be predicted by using our feature x. So there will always be some error that is not predictable. So variability associated with the error epsilon also affects the accuracy of the predictions. And this is known as the irreducible error because no matter how well we will estimate f, we cannot reduce the error introduced by the epsilon. This error contains all the features that are not included in our model, so all the unknown factors that have an influence on our dependent variable but are not included as part of our data. But we can reduce the reducible error rate, which is based on two values, the variance of the estimates and the bias of the model. If we were to simplify the mathematical expression describing the error rate that we got, then it's equal to the variance of our model plus squared bias of our model plus the irreducible error. So, even if we cannot reduce the irreducible error, we can reduce the reducible error rate, which is based on these two values, the variance and the squared bias. So, though the mathematical derivation is out of the scope of this course, just keep in mind that the reducible error of the model can be described as the sum of the variance of the model and the squared bias of the model. So, mathematically, the error in the supervised machine learning model is equal to the squared bias in the model, the variance of the model, and the irreducible error. Therefore, in order to minimize the expected test error rate, so on the unseen data, we need to select a machine learning method that simultaneously achieves low variance and low bias. And that's exactly what we call bias-variance trade-off. The problem is that there is a negative correlation between the variance and the bias of the model. Another thing that is highly related to the bias and the variance of the model is the flexibility of the machine learning model. So flexibility of the machine learning model has a direct impact on its variance and on its bias. Let's look at these relationships one by one. So complex models or more flexible models tend to have a lower bias, but at the same time, complex models or more flexible models tend to have higher variance than simpler models. So, as the flexibility of the model increases, the model finds the true patterns in the data easier, which reduces the bias of the model. At the same time, the variance of such models increases. So, as the flexibility of the model decreases, model finds it more difficult to find the true patterns in the data, which then increases the bias of the model, but also decreases the variance of the model. Keep this topic in mind, and we will continue this topic in the next lecture when we will be discussing the topic of overfitting and how to solve the overfitting problem by using regularization. In this lecture, lecture number 3, we will talk about a very important concept called overfitting and how we can solve overfitting by using different techniques, including regularization. This topic is related to the previous lecture and to the topics of error of the model, train error rate, test error rate, bias, and a variance of the machine learning model. Overfitting is important to know and also how to solve it with regularization, because this topic can lead to inaccurate predictions and a lack of generalization of the model to new data. Knowing how to detect and prevent overfitting is crucial in building effective machine learning models. Questions about this topic are almost guaranteed to appear during every single data science interview. In the previous lecture, we discussed the relationship between model flexibility and the variance as well as the bias of the model. We saw that as the flexibility of the model increases, model finds the true patterns in the data easier, which reduces the bias of the model. But at the same time, the variance of such models increases. So, as the flexibility of the model decreases, model finds it more difficult to find the true patterns in the data, which then increases the bias of the model and decreases the variance of the model. Let's first formally define what the overfitting problem is, as well as what the underfitting is. So overfitting occurs when the model performs well in the training, while the model performs worse on the test data. So you end up having a low training error rate, but a high test error rate. And in an ideal world, We want our test error rate to be low, or at least that the training error rate is equal to the test error rate. Overfitting is a common problem in machine learning, where a model learns the detail and the noise in the training data to the point where it negatively impacts the performance of the model on this new data. So, the model follows the data too closely, closer than it should. This means that the noise or random fluctuations of the training data is picked up and learned as concepts by the model, which it should actually ignore. The problem is that the noise or random component of the training data will be very different from the noise in the new data. The model will therefore be less effective in making predictions on new data. Overfitting is caused by having too many features, too complex of a model, or too little of the data. When the model is overfitting, then also the model has high variance and low bias. Usually, the higher is the model flexibility, the higher is the risk of overfitting, because then we have higher risk of having a model following the data too closely and following the noise. So underfitting is the other way around. Underfitting occurs when our test error rate is much lower than our training error rate. Given that overfitting is much bigger of a problem and we want ideally to fix the case when our test error rate is large, we will only focus on the overfitting. And this is also the topic that you can expect during your data science interviews, as well as something that you need to be aware of whenever you are training a machine learning model. All right, so now when we know what overfitting is, we should now talk about how we can fix this problem. There are several ways of fixing or preventing overfitting. First, you can reduce the complexity of the model. We saw that higher the complexity of the model, higher is the chance of the following the data, including the noise, too closely, resulting in overfitting. Therefore, reducing the flexibility of the model will reduce the overfitting as well. This can be done by using a simpler model with fewer parameters, or by applying a regularization techniques such as L1 or L2 regularization that we will talk in a bit. Second solution is to collect more data. The more data you have, the less likely your model will overfit. Third, and another solution is using resampling techniques, one of which is cross-validation. This is a technique that allows you to train and test your model on different subsets of your data, which can help you to identify if your model is overfitting. We will discuss cross-validation as well as other resampling techniques later in this section. Another solution is to apply early stopping. Early stopping is a technique where you monitor the performance of the model on a validation set during the training process and stop the training when the performance starts to decrease. Another solution is to use ensemble methods. By combining multiple models such as decision trees, overfitting can be reduced. We will be covering many popular ensemble techniques in this course as well. Finally, you can use what we call dropout. Dropout is a regularization technique for reducing overfitting in neural networks by dropping out or setting to zero some of the neurons during the training process. Because from time to time, dropout-related questions do appear during the data science interviews for people with no experience. So if someone asks you about dropout, then at least you will remember that it's a technique used to solve overfitting in the setting of deep learning. It's worth noting that there is no one solution that works for all types of overfitting, and often a group of these techniques that we just talked about should be used to address the problem. We saw that when the model is overfitting, then the model has high variance and low bias. By definition, regularization, or what we also call shrinkage, is a method that shrinks some of the estimated coefficients towards zero, to penalize unimportant variables for increasing the variance of the model. This is a technique used to solve the overfitting problem by introducing a little bias in the model while significantly decreasing its variance. There are three types of regularization techniques that are widely known in the industry. The first one is the ridge regression, or L2 regularization. The second one is the lasso regression, or the L1 regularization. And finally, the third one is the dropout, which is a regularization technique used in deep learning. We will cover the first two types in this lecture. Let's now talk about ridge regression, or L2 regularization. So ridge regression, or L2 regularization, is a shrinkage technique that aims to solve overfitting by shrinking some of the model coefficients towards zero. Ridge regression introduces little bias into the model while significantly reducing the model variance. Ridge regression is a variation of linear regression, but instead of trying to minimize the sum of squared residuals that linear regression does, it aims to minimize the sum of squared residuals added on the top of the squared coefficients, what we call L2 regularization term. Let's look at a multiple linear regression example with P independent variables or predictors that are used to model the dependent variable y. If you have followed the statistical section of this course, you might also recall that the most popular estimation technique to estimate the parameter of the linear regression, assuming its assumptions are satisfied, is the ordinary least squares, or the OLS, which finds the optimal coefficients by minimizing the sum of squared residuals, or the RSS. So ridge regression is pretty similar to the OLS, except that the coefficients are estimated by minimizing a slightly different cost or loss function. This is the loss function of the ridge regression, where beta j is the coefficient of the model for variable j, beta 0 is the intercept, and xij is the input value for the variable j and observation I. yi is the target variable or the dependent variable for observation y, and n is the number of samples, and lambda is what we call regularization parameter of the ridge regression. So this is the loss function of OLS that you can see here, and added a penalization term. So it's combined, what we call RSS. So if you check out the very initial lecture in this section where we spoke about different metrics that can be used to evaluate regression type of models, you can see RSS and the definition of RSS. Well, if you compare this expression, then you can easily find that this is the exact formula for the RSS added with an intercept. And this right term is what we call a penalty amount, which basically represents the lambda times the sum of the squared of the coefficients included in our model. Here, lambda, which is always positive, so it's always larger than equals 0, is a tuning parameter or the penalty parameter. This expression of the sum of squared coefficients is called L2 norm, which is why we call this L2 penalty-based regression or L2 regularization. In this way, ridge regression assigns a penalty by shrinking their coefficients towards 0, reducing the overall model variance. But these coefficients will never become exactly 0. So the model parameters are never set to exactly 0, which means that all P predictors of the model are still intact. This one is a key property of ridge regression to keep in mind, that it shrinks the parameters towards 0, but never exactly sets them equal to 0. L2 norm is a mathematical term coming from linear algebra, and it's standing for Euclidean norm. We spoke about the penalty parameter lambda, what we also call the tuning parameter lambda, which serves to control the relative impact of the penalty on the regression coefficient estimates. When the lambda is equal to 0, the penalty term has no effect, and the ridge regression will introduce the ordinary least squares estimates. But as the lambda increases, the impact of the shrinkage penalty grows, and the ridge regression coefficient estimates approach to 0. What is important to keep in mind, which you can also see from this graph, is that in ridge regression, large lambda will assign a penalty to some variables by shrinking their coefficients towards 0, but they will never become exactly 0, which becomes a problem when you are dealing with a model that has a large number of features, and your model has a low interpretability. Ridge regression's advantage over ordinary least squares is coming from the earlier introduced bias-variance trade-off phenomenon. So as the lambda, the penalty parameter, increases, the flexibility of the ridge regression fit decreases, leading to decreased variance, but increased bias. The main advantages of ridge regression are solving overfitting. Ridge regression can shrink the regression coefficient of less important predictors towards 0. It can improve the prediction accuracy as well by reducing the variance and increasing the bias of the model. Ridge regression is less sensitive to outliers in the data compared to linear regression. Ridge regression is computationally less expensive compared to lasso regression. The main disadvantage of ridge regression is the low model interpretability, as the P, so the number of features in your model, is large. Let's now look into another regularization technique called lasso regression, or L1 regularization. By definition, lasso regression, or L1 regularization, is a shrinkage technique that aims to solve overfitting by shrinking some of the model coefficients towards zero and setting some to exactly zero. Lasso regression, like ridge regression, introduces little bias into the model while significantly reducing model variance. There is, however, a small difference between the two regression techniques that makes a huge difference in their results. We saw that one of the biggest disadvantages of ridge regression is that it will always include all the predictors or all the p-predictors in the final model. Whereas in case of lasso, it overcomes this disadvantage. So, large lambda, or penalty parameter, will assign a penalty to some variables by shrinking their coefficients towards zero. In case of ridge regression, they will never become exactly zero, which becomes a problem when your model has a large number of features and it has a low interpretability. And lasso regression overcomes this disadvantage of ridge regression. Let's have a look at the loss function of lasso regularization. So, this is the loss function of OLS, which is the left part of the formula called RSS, combined with a penalty amount, which is the right-hand side of the expression, the lambda times sum of the absolute values of the coefficients beta j. As you can see, this is the RSS that we just saw, which is exactly the same as the loss function of the OLS, and then we are adding the second term, which basically is the lambda, the penalization parameter, multiplied by the sum of the absolute value of the coefficient beta j, where j goes from 1 till p, and the p is number of predictors included in our model. Here, once again, the lambda, which is always positive, larger than or equals 0, is a tuning parameter or the penalty parameter. This expression of the sum of squared coefficients is called L1 norm, which is why we call this L1 penalty-based regression or L1 regularization. In this way, lasso regression assigns a penalty to some of the variables by shrinking their coefficients towards 0 and setting some of these parameters to exactly 0. So, this means that some of the coefficients will end up being exactly equal to 0, which is a key difference between the lasso regression versus the ridge regression. The L1 norm is a mathematical term coming from the linear algebra, and it's standing for Manhattan norm or distance. You might see here a key difference when comparing the visual representation of the lasso regression compared to the visual representation of the ridge regression. So if you look at this point, you can see that there will be cases where our coefficients will be set to exactly 0. This is where we have this intersection. Whereas in case of ridge regression, you can recall that there was not a single intersection. So the numbers where the circle was close to the intersection points, but there was not a single point when there was an intersection and the coefficients were put to 0. And that's the key difference between two regression type of models, between these two regularization techniques. The main advantages of lasso regression are solving overfitting. So lasso regression can shrink the regression coefficients of less important predictors towards 0 and sum to exactly 0. As the model filters some variables out, lasso indirectly performs also what we call feature selection, such that the resulted model is highly interpretable and with less features, and much more interpretable compared to the ridge regression. Lasso can also improve the prediction accuracy of the model by reducing the variance and increasing the bias of the model, but not as much as the ridge regression. Earlier, when speaking about correlation, we also briefly discussed the concept of causation. We discussed that correlation is not a causation, and we also briefly spoke the methods used to determine whether there is a causation or not. That model is the infamous linear regression, and even if this model is recognized as a simple approach, it's one of the few methods that allows identifying features that have an impact or a statistically significant impact on a variable that we are interested in and we want to explain. And it also helps to identify how and how much there is a change in the target variable when changing the independent variable values. To understand the concept of linear regression, you should also know and understand the concepts of dependent variable, independent variable, linearity, and statistical significant effect. Dependent variables are often referred to as response variables or explained variables. By definition, dependent variable is a variable that is being measured or tested. It's called the dependent variable because it's thought to depend on the independent variables. So you can have one or multiple independent variables, but you can have only one dependent variable that you are interested in, that is your target variable. Let's now look into the independent variable definition. So independent variables are often referred as regressors or explanatory variables. And by definition, independent variable is the variable that is being manipulated or controlled in the experiment and is believed to have an effect on the dependent variable. Put it differently, the value of the dependent variable is thought to depend on the value of the independent variable. For example, in an experiment, to test the effect of having a degree on the wage, the degree variable would be your independent variable, and the wage would be your dependent variable. Finally, let's look into the very important concept of statistical significance. We call the effect statistically significant if it's unlikely to have occurred by random chance. In other words, a statistically significant effect is one that is likely to be real and not due to random chance. Let's now define the linear regression model formally, and then we will dive deep into the theoretical and practical details. By definition, linear regression is a statistical or machine learning method that can help to model the impact of a unit change in the variable, the independent variable, on the values of another target variable or the dependent variable when the relationship between the two variables is assumed to be linear. When the linear regression model is based on a single independent variable, then we call this model simple linear regression. When the model is based on multiple independent variables, we call it multiple linear regression. Let's look at the mathematical expression describing linear regression. You can recall that when the linear regression model is based on a single independent variable, we just call it a simple linear regression. This expression that you see here is the most common mathematical expression describing simple linear regression. So you can see that we are saying that the yi is equal to beta 0 plus beta 1 xi plus ui. In this expression, the yi is the dependent variable, and the I that you see here is the index corresponding to the each row. So whenever you are getting the data and you want to analyze this data, you will have multiple rows. And if your multiple rows describe the observations that you have in your data, so it can be people, it can be observation describing your data, then the each characterizes the specific row, the each row that you have in your data. And the yi is then the dependent variable's value corresponding to that each row. Then the same holds for the xi. So the xi is then the independent variable or the explanatory variable or the regressor that you have in your model, which is the variable that we are testing. So we want to manipulate it to see whether this variable has a statistically significant impact on the dependent variable y. So we want to see whether unit change in the x will result in a specific change in the y, and what kind of change is that. So beta 0 that you see here is not a variable, and it's called intercept or constant, something that is unknown, so we don't have that in our data, and it's one of the parameters of a linear regression. It's an unknown number, which the linear regression model should estimate. So we want to use the linear regression model to find out this unknown value, as well as the second unknown value, which is the beta 1, as well as we can estimate the error terms, which are represented by the ui. So beta 1 next to the xi, so next to the independent variable, is also not a variable. So like beta 0, it's an unknown parameter in the linear regression model, an unknown number, which the linear regression model should estimate. Beta 1 is often referred as the slope coefficient of a variable x, which is the number that quantifies how much the dependent variable y will change if the independent variable x will change by 1 unit. So that's exactly what we are most interested in, the beta 1, because this is the coefficient and this is the unknown number that will help us to understand and answer the question whether our independent variable x has a statistically significant impact on our dependent variable y. Finally, the u that you see here, or the ui, in the expression is the error term, or the amount of mistake that the model makes when explaining the target variable. We add this value since we know that we can never exactly and accurately estimate the target variable. So we will always make some amount of estimation error, and we can never estimate the exact value of y. Hence, we need to account for this mistake that we are going to make, and we know in advance that we are going to have this mistake by adding an error term to our model. Let's also have a brief look at how multiple linear regression is usually expressed in mathematical terms. So you might recall that the difference between the simple linear regression and multiple linear regression is that the first one has a single independent variable in it, whereas the latter, so the multiple linear regression, like the name suggests, has multiple independent variables in it, so more than one. Knowing this type of expression is critical since they not only appear a lot in the interviews, but also in general, you will see them in the data science blogs, in presentations, in books, and also in papers. So being able to quickly identify and say, I remember saying this at once, then it will help you to easier understand and follow the process and the storyline. So what you see here, you can read as yi is equal to beta 0 plus beta 1 times x1i plus beta 2 times x2i plus beta 3 times x3i plus ui. So this is the most common mathematical expression describing multiple linear regression, in this case with 3 independent variables. So if you were to have more independent variables, you should add them with their corresponding indices and coefficients. So in this case, the method will aim to estimate the model parameters, which are beta 0, beta 1, beta 2, and beta 3. So like before, yi is our dependent variable, which is always a single one. So we only have one dependent variable. Then we have beta 0, which is our intercept or the constant. Then we have our first slope coefficient, which is beta 1, corresponding to our first independent variable x1. Then we have x1i, which stands for the independent variable, the first independent variable with an index 1, and the I stands for the index corresponding to the row. So whenever we have multiple linear regression, we always need to specify 2 indices and not only one, like we had in our single linear regression. The index that characterizes which independent variable we are referring to, so whether it's independent variable 1, 2, or 3, and then we need to specify which row we are referring to, which is the index I. So you might notice that in this case, all the indices are the same because we are looking into one specific row and we are representing this row by using the independent variables, the error term, and the dependent variable. So then we are adding our third term, which is beta 2 times x2i. So the beta 2 is our third unknown parameter in the model, and the second slope coefficient corresponding to our second independent variable. And then we have our third independent variable with the corresponding slope coefficient beta 3, as well as we also add, like always, an error term to account for the error that we know that we are going to make. So now when we know what the linear regression is and how to express it in the mathematical terms, you might be asking the next logical question. Well, we know that when we know what the linear regression is and how to express it in the mathematical terms, you might be asking the next logical question. How do we find those unknown parameters in the model in order to find out how the independent variables impacted the dependent variable? Finding these unknown parameters is called estimating in data science and in general. So we are interested in finding out the possible values or the values that the best approximate the unknown values in our model. And we call this process estimation. And one technique used to estimate linear regression parameters is called OLS, or ordinary least squares. So the main idea behind this approach, the OLS, is to find the best fitting straight line, so the regression line, through a set of paired x and y's, so our independent variables and dependent variables values, by minimizing the sum of squared errors. So to minimize the sum of squares of the differences between the observed dependent variable and its values, which are the predicted values that we have predicted by our model, that's exactly what we want to do by using this linear function of the independent variables, the residuals. So this is too much information. Let's go it step by step. So in linear regression, we just saw when we were expressing our simple linear regression, we had this error term. And we can never know what is the actual error term. But what we can do is to estimate the value of the error term, which we call residual. So we want to minimize the sum of squared residuals because we don't know the errors. So we want to find a line that will best fit our data in such a way that the error that we are making or the sum of squared errors is as small as possible. And since we don't know the errors, we can estimate the errors by each time looking at the predicted value that is predicted by our model and the true value, and then we can subtract them from each other, and we can see how good our model is estimating the values that we have. So how good is our model estimating the unknown parameters? So to minimize the sum of squared of the differences between the observed dependent variable and its values predicted by the linear function of the independent variables, so the minimizing the sum of squared residuals. So we define the estimate of parameters and variables by adding a hedge on the top of the variables or parameters. So in this case, you can see that yi hat is equal to beta 0 hat plus beta 1 hat xi. So you can see that we no longer have an error term in this. And we say that yi hat is the estimated value of yi. And beta 0 hat is the estimated value of beta 0. Beta 1 hat is the estimated value of our beta 1. And the xi is still our data, so the values that we have in our data, and therefore we don't have a hat since that does not need to be estimated. So what we want to do is to estimate our dependent variable, and we want to compare our estimated value that we got using our OLS with the real value, such that we can calculate our errors or the estimate of the error, which is represented by the ui hat. So the ui hat is equal to yi minus yi hat, where ui hat is simply the estimate of the error term or the residual. So this predicted error is always referred as residual. So make sure that you do not confuse the error with the residual. So error can never be observed. Error you can never calculate and you will never know. But what you can do is to predict the error. And when you predict the error, then you get a residual. And what OLS is trying to do is to minimize the amount of error that it's making. Therefore, it looks at the sum of squared residuals across all the observation, and it tries to find the line that will minimize this value. Therefore, we are saying that the OLS tries to find the best fitting straight line such that it minimizes the sum of squared residuals. We have discussed this model when we were talking about this model mainly from the perspective of causal analysis in order to identify features that have a statistically significant impact on the response variable. But linear regression can also be used as a prediction model for modeling linear relationship. So let's refresh our memory with the definition of linear regression model. By definition, linear regression is a statistical or a machine learning method that can help to model the impact of a unit change in the variable, the independent variable, on the values of another target variable, the dependent variable, when the relationship between two variables is linear. In the lecture number 6 from the statistical section, we also discussed how mathematically we can express what we call simple linear regression and a multiple linear regression. So this is how the simple linear regression can be represented. So in case of simple linear regression, you might recall that we are dealing with just a single independent variable, and we always have just one dependent variable, both in the single linear regression and in the multiple linear regression. So here you can see that yi is equal to beta 0 plus beta 1 times xi plus ui, where y is the dependent variable and the I is basically the index of each observation or the row. And then the beta 0 is the intercept, which is also known as constant. And then the beta 1 is the slope coefficient or a parameter corresponding to the independent variable x, which is unknown, and a constant which we want to estimate along to the beta 0. And then the xi is the independent variable corresponding to the observation I. And then finally, the ui is the error term corresponding to the observation I. Do keep in mind that this error term we are adding because we do know that we always are going to make a mistake and we can never perfectly estimate the dependent variable. Therefore, to account for this mistake, we are adding this ui. So let's also recall the estimation technique that we use to estimate the parameters of the linear regression model, so the beta 0 and beta 1, and to predict the response variable. So we call this estimation technique OLS, or the ordinary least squares. And OLS is an estimation technique for estimating the unknown parameters in a linear regression model to predict the response or the dependent variable. So we need to estimate the beta 0, so we need to get the beta 0 hat, and we need to estimate the beta 1 or the beta 1 hat in order to obtain the yi hat. So yi hat is equal to beta 0 hat plus beta 1 hat times xi, where the difference between the yi hat and the yi, so the true value of the dependent variable and the predicted value, their difference will then produce our estimate of the error, or what we also call residual. The main idea behind this approach is to find the best fitting straight line, so the regression line, through a set of paired x and y values by minimizing the sum of squared residuals. So we want to minimize our errors as much as possible. Therefore, we are taking their squared version and we are trying to sum them up, and we want to minimize this entire error. So to minimize the sum of squared residuals, so the difference between the observed dependent variable and its values predicted by the linear function of the independent variables, we need to use the OLS. One of the most common questions related to linear regression that comes time and time again in the data science related interviews is the topic of the assumptions of the linear regression model. So you need to know each of these 5 fundamental assumptions of the linear regression and the OLS, and also you need to know how to test whether each of these assumptions are satisfied. So the first assumption is the linearity assumption, which states that the relationship between the independent variables and the dependent variable is linear. We also say that the model is linear in parameters. You can also check whether the linearity assumption is satisfied by plotting the residuals to the fitted values. If the pattern is nonlinear, then the estimate will be biased. In this case, we say that the linearity assumption is violated, and we need to use more flexible models such as tree-based models that we will discuss in a bit that are able to model these nonlinear relationships. The second assumption in the linear regression is the assumption about randomness of the sample, which means that the data is randomly sampled, and which basically means that the errors or the residuals of the different observations in the data are independent of each other. You can also check whether the second assumption, so this assumption about random sample, is satisfied by plotting the residuals. You can then check whether the mean of these residuals is around 0, and if not, then the OLS estimate will be biased and the second assumption is violated. This means that you are systematically over or under predicting the dependent variable. The third assumption is the exogeneity assumption, which is a really important assumption often asked during the data science interviews. Exogeneity means that each independent variable is uncorrelated with the error terms. Exogeneity refers to the assumption that the independent variables are not affected by the error term in the model. In other words, the independent variables are assumed to be determined independently of the errors in the model. Exogeneity is a key assumption of linear regression models, as it allows us to interpret the estimated coefficients as representing the true causal effects of the independent variables on the dependent variable. If the independent variables are not exogenous, then the estimated coefficients may be biased and the interpretation of the results may be invalid. In this case, we call this problem an endogeneity problem, and we say that the independent variable is not exogenous, but it's endogenous. It's important to carefully consider the exogeneity assumption when building a linear regression model, as violation of this assumption can lead to invalid or misleading results. If this assumption is satisfied for an independent variable in the linear model, we call this independent variable exogenous. So otherwise, we call it endogenous, and we say that we have a problem of endogeneity. Endogeneity refers to the situation in which the independent variables in the linear regression model are correlated with the error terms in the model. In other words, the errors are not independent of the independent variables. Endogeneity is a violation of one of the key assumptions of the linear regression model, which is that the independent variables are exogenous or not affected by the errors in the model. Endogeneity can arise in a number of ways. For example, it can be caused by omitted variable bias, in which an important predictor of the dependent variable is not included in the model. It can also be caused by the reverse causality, in which the dependent variable affects the independent variable. So those two are very popular examples of the case when we can get an endogeneity problem. And those are things that you should know whenever you are interviewing for data science roles, especially when it's related to machine learning, because those questions are being asked to you in order to test whether you understand the concept of exogeneity versus endogeneity, and also in which cases you can get endogeneity, and also how you can solve it. So in case of omitted variable bias, let's say you are estimating a person's salary and you are using as independent variable their education, their number of years of experience, and some other factors. But you are not including, for instance, in your model, a feature that would describe the intelligence of a person or, for instance, IQ of the person. Well, given that those are a very important indicator for a person in order to perform in their field, and this can definitely have indirect impact on their salary, not including these variables will result in omitted variable bias, because this will then be incorporated in your error term. And this can also relate to the other independent variables, because then your IQ is also related to the education that you have. Higher is your IQ, usually higher is your education. So in this way, you will have an error term that includes an important variable. So this is the omitted variable, which is then correlated with your one of your or multiple of your independent variables included in your model. So the other example, the other cause of the endogeneity problem is the reverse causality. And what reverse causality means is basically that not only the independent variable has an impact on the dependent variable, but also the dependent variable has an impact on the independent variable. So there is a reverse relationship, which is something that we want to avoid. We want to have our features that include in our model that have only an impact on the dependent variable. So they are explaining the dependent variable, but not the other way around. Because if you have the other way, so you have the dependent variable impacting your independent variable, then you will have the error term being related to this independent variable, because there are some components that also define your dependent variable. So knowing the few examples such as those that can cause endogeneity, so they can violate the exogeneity assumption, is really important. Then you can also check for the exogeneity assumption by conducting a formal statistical test. This is called Hausmann test. So this is an econometrical test that helps to understand whether you have an exogeneity violation or not. But this is out of the scope of this course. I will, however, include many resources related to the exogeneity, endogeneity, the omitted variable bias, as well as the reverse causality, and also how the Hausmann test can be conducted. So for that, check out the interview preparation guide, where you can also find the corresponding free resources. The fourth assumption in linear regression is the assumption about homoscedasticity. Homoscedasticity refers to the assumption that the variance of the errors is constant across all predicted values. This assumption is also known as the homogeneity of the variance. Homoscedasticity is an important assumption of the linear regression model, as it allows us to use certain statistical techniques and make inferences about parameters of the model. If the errors are not homoscedastic, then the results of these techniques may be invalid or misleading. If this assumption is violated, then we say that we have heteroscedasticity. Heteroscedasticity refers to the situation in which the variance of the error terms in a linear regression model is not constant across all the predicted values. So we have a varying variance. In other words, the assumption of homoscedasticity in that case is violated, and we say we have a problem of heteroscedasticity. Heteroscedasticity can be a real problem in linear regression analysis because it can lead to invalid or misleading results. For example, the standard error estimates and the confidence intervals for the parameters may be incorrect, which means that also the statistical test may have incorrect type 1 error rates. So you might recall when we were discussing the linear regression as part of the fundamentals to statistics section of this course, is that we looked into the output that comes from a Python, and we saw that we are getting estimates as part of the output, as well as standard errors, then the t-test, so the student t-test, and then the corresponding p-values and the 95% confidence intervals. So whenever there is a heteroscedasticity problem, the coefficient might still be accurate, but then the corresponding standard error, the student t-test, which is based on the standard error, and then the p-value as well as the confidence intervals may not be accurate. So you might get the good and reasonable coefficients, but then you don't know how to correctly evaluate them. You might end up discovering that you might end up stating that certain independent variables are statistically significant because their coefficients are statistically significant since their p-values are small. But in the reality, those p-values are misleading because they are based on the wrong statistical tests and they are based on the wrong standard errors. You can check for this assumption by plotting the residuals and see whether there is a funnel-like graph. If there is a funnel-like graph, then you have a constant variance. But if there is not, then you won't see this funnel-like this shape that indicates that your variances are constant. And if not, then we say we have a problem of heteroscedasticity. If you have a heteroscedasticity, you can no longer use the OLS and the linear regression. And instead, you need to look for other more advanced econometrical regression techniques that do not make such a strong assumption regarding the variance of your residuals. So you can, for instance, use the GLS, the FGLS, the GMM, and this type of solutions will help to solve the heteroscedasticity problem, and they will not make a strong assumption regarding the variance in your model. The fifth and the final assumption in linear regression is the assumption about no perfect multicollinearity. This assumption states that there are no exact linear relationships between the independent variables. Multicollinearity refers to the case when two or more independent variables in your linear regression model are highly correlated with each other. This can be a problem because it can lead to unstable and unreliable estimates of the parameters in the model. Perfect multicollinearity happens when the independent variables are perfectly correlated with each other, meaning that one variable can be perfectly predicted from the other ones. And this can cause the estimated coefficient in your linear regression model to be infinite or undefined, and can lead your errors to be entirely misleading when making predictions using this model. If perfect multicollinearity is detected, it may be necessary to remove one, if not more, problematic variables such that you will avoid having correlated variables in your model. And even if the perfect multicollinearity is not present, multicollinearity at a high level can still be a problem if the correlations between the independent variables are high. In this case, the estimates of the parameters may be imprecise, and the model may be entirely misleading and will result in less reliable predictions. So to test for the multicollinearity assumption, you have different solutions. You have different options. The first way you can do that is by using the Dickey-Fuller test. Dickey-Fuller test is a formal statistical and econometrical test that will help you to identify which variables cause a problem and whether you have a perfect multicollinearity in your linear regression model. You can plot a heat map, which will be based on the correlation metrics corresponding to your features. Then you will have your correlations per pair of independent variables plotted as a part of your heat map. And then you can identify all the pair of features that are highly correlated with each other. And those are problematic features, one of which should be removed from your model. And in this way, by showing the heat map, you can also showcase to your stakeholders why you have removed certain variables from your model. Whereas explaining a Dickey-Fuller test is much more complex because it involves more advanced econometrics and linear regression explanation. So if you're wondering how you can perform this Dickey-Fuller test and you want to prepare the questions related to perfect multicollinearity, as well as how you can solve the perfect multicollinearity problem in your linear regression model, then head towards the interview preparation guide included in this part of the course in order to answer such questions and also to see the 30 most popular interview questions you can expect from this section in the interview preparation guide. Now let's look into an example coming from the linear regression in order to see how all those pieces of the puzzle come together. So let's say we have collected the data on a class size and a test scores for a sample of students. And we want to model the linear relationship between the class size and the test scores using a linear regression model. So as we have just one independent variable, we are dealing with a simple linear regression. And the model equation would be as follows. So you can see that the test scores is equal to beta 0 plus beta 1 multiplied by class size plus epsilon. So here the class size is the single independent variable that we got in our model. The test score is the dependent variable. The beta 0 is the intercept or the constant. The beta 1 is the coefficient of interest, as this is the coefficient corresponding to our independent variable. And this will help us to understand what is the impact of a unit change in the class size on the test score. And then finally, we are including in our model an error term to account for the mistakes that we are definitely going to make when estimating the dependent variable, the test scores. The goal is to estimate the coefficient beta 0 and beta 1 from the data and use the estimated model to predict the test scores based on the class size. So once we have the estimates, we can then interpret them as follows. The y-intercept, the beta 0, represents the expected test scores when the class size is 0. It represents the base score that the student would have obtained if the class size would have been 0. Then the coefficient for the class size, the beta 1, represents the change in the test scores associated with the 1 unit change in the class size. The positive coefficient would imply that 1 unit change in the class size would increase the test scores, whereas the negative coefficient would imply that the 1 unit change in the class size will decrease the test scores correspondingly. We can then use this model with OLS estimate in order to predict the test scores for any given class size. So let's go ahead and implement that in Python. If you're wondering how this can be done, then head towards the resources section as well as the part of the Python for data science, where you can learn more about how to work with pandas data frames, how to import the data, as well as how to fit a linear regression model. So the problem is as follows. We have collected the data on the class size and we have this independent variable. So as you can see here, we have the students underscore data, and then we have the class size, and this is our feature. And then we want to estimate the y, which is the test score. So here is the code, a sample code that will fit a linear regression model. We are keeping here everything very simple. We are not splitting our data into train and test, and then fitting the model on the training data and making the predictions with the test score. But we just want to see how we can interpret the coefficients. So keeping everything very simple. So you can see here that we are getting an intercept equal to 63.17, and the coefficient corresponding to our single independent variable class size is equal to minus 0.40. What this means is that each increase of the class size by 1 unit will result in the decrease of the test scores with 0.4. So there is a negative relationship between the two. Now, the next question is whether there is a statistical significance, whether the coefficient is actually significant, and whether the class size has actually a statistically significant impact on the dependent variable. But all those are things that we have discussed as part of the fundamentals to statistics section of this course, as well as we are going to look into a linear regression example when we are going to discuss the hypothesis testing. So I would highly suggest you to stop in here to revisit the fundamentals to statistics section of this course to refresh your memory in terms of linear regression, and then check also the hypothesis testing section of the course in order to look into a specific example of linear regression when we are discussing the standard errors, how you can evaluate your OLS estimation results, how you can use the student t-test, the p-value, and the confidence intervals, and how you can estimate them. In this way, you will learn for now only the theory related to the coefficients, and then you can add on the top of this theory once you have learned all the other sections and the other topics in this course. Let's finally discuss the advantages and the disadvantages of the linear regression model. So some of the advantages of the linear regression model are the following. The linear regression is relatively simple and easy to understand and to implement. Linear regression models are well suited for understanding the relationship between a single independent variable and a dependent variable. Also, linear regression can help you handle multiple independent variables and can estimate the unique relationship between each independent variable and the corresponding dependent variable. Linear regression model can also be extended to handle more complex models, such as polynomials, interaction terms, allowing for more flexibility in the modeling the data. Also, linear regression model can be easily regularized to prevent overfitting, which is a common problem in modeling as we saw in the beginning of this section. So you can use, for instance, ridge regression, which is an extension of linear regression. You can use lasso regression, which is also an extension of linear regression model. And then finally, linear regression models are widely supported by software packages and libraries, making it easy to implement and to analyze. And some of the disadvantages of the linear regression are the following. So the linear regression models make a lot of strong assumptions regarding, for instance, the linearity between independent variables and the dependent variables, while the true relationship can actually be also nonlinear. So the model will not then be able to capture the complexity of the data, so the nonlinearity, and the predictions will be inaccurate. Therefore, it's really important to have a data that has a linear relationship for linear regression to work. Linear regression also assumes that the error terms are normally distributed and also homoscedastic. Error terms are independent across observations. Violations of this strong assumption will lead to biased and inefficient estimates. Linear regression is also sensitive to outliers, which can have a disproportionate effect on the estimate of the regression coefficients. Linear regression does not easily handle categorical independent variables, which often require additional data preparation or the use of indicator variables or using encodings. Finally, linear regression also assumes that the independent variables are exogenous and not affected by the error terms. If this assumption is violated, then the result of the model may be misleading.
Imagine you have a friend, Alex, who collects stamps. Every month, Alex buys a certain number of stamps, and you notice that the amount Alex spends seems to depend on the number of stamps bought. Now, you want to create a little tool that can predict how much Alex will spend next month based on the number of stamps bought. This is where linear regression comes into play. In technical terms, we're trying to predict the dependent variable amount spent based on the independent variable number of stamps bought. Below is some simple Python code using scikit-learn to perform linear regression on a created dataset. The linear regression analysis was carried out through a structured process using Python's NumPy and Matplotlib libraries, as well as scikit-learn's linear regression class. Initially, the libraries were imported to facilitate numerical computations and data visualization. This foundational step ensures that all necessary functions and methods are available for executing the analysis. Subsequently, the data was organized with stamps and bought serving as the independent variable and amount is spent as the dependent variable. The stamps array was reshaped into a two-dimensional array using reshape. This modification was necessary because the scikit-learn library requires input features in a specific format. Once the data was appropriately formatted, a linear regression model was instantiated from the linear regression class and then trained with the fit method. By passing the reshaped stamps, bought, and amount spent arrays to this method, the model learned the relationship between the number of stamps bought and the corresponding amount spent. The trained model was then used to predict the expenditure for a hypothetical future scenario where 10 stamps are bought. This was accomplished using the predict method, which was called with an input array representing 10 stamps. The model used its learned parameters to estimate the outcome based on this input. For visualization, the original data points and the regression line were plotted using Matplotlib. The scatter function was used to plot the data points in blue, illustrating the actual amount spent for different quantities of stamps bought. The regression line, plotted in red using the plot function, demonstrated the predicted relationship as learned by the model. Finally, the prediction for 10 stamps was displayed using a print statement. This demonstrated how the model's predictions can be interpreted and used, providing a specific numerical estimate for the amount likely to be spent on stamps in the given scenario. This complete process from data preparation through training to prediction, showcases how linear regression can be applied to derive insights from real-world data effectively. Let's go through some of the concepts and variables we are using in this chapter. Sample data. The term stamps is bought refers to the number of stamps Alex bought each month, and amount spent represents the corresponding money spent. Creating and training model. We use linear regression from scikit-learn to create and train our model using fit predictions. The trained model is then used to predict the amount Alex will spend for a given number of stamps. In the code, we predict the amount for 10 stamps. Plotting. We plot the original data points in blue and the predicted line in red to visually understand our model's prediction capability. Displaying prediction. Finally, we print out the predicted spending for a specific number of stamps, 10 in this case. This graph illustrates the outcome of a simple linear regression analysis, which seeks to capture the relationship between two variables, the number of stamps purchased and the total expenditure incurred. The red line depicted in the graph is known as the regression line, representing the best fit through the plotted green data points. The slope of this regression line is particularly telling. It quantifies the increase in total cost associated with each additional stamp purchased. Such insights are invaluable for budgeting purposes or for forecasting future expenses based on past purchasing behavior. Each of the green data points on the graph corresponds to an actual purchase event, where both the quantity of stamps bought and the precise amount spent are known. The close clustering of these points around the regression line strongly supports the presence of a linear relationship between the number of stamps purchased and the total expenditure. This alignment suggests that the model has effectively captured the underlying trend in the data, offering a reliable basis for predictions. Employing simple linear regression in scenarios like this provides a clear and quantifiable understanding of how one variable affects another. In the realm of data analysis, this method serves as a powerful tool, enabling analysts to draw significant conclusions and make informed decisions based on the observed relationships between variables. The simplicity yet robustness of linear regression make it an indispensable technique in the toolkit of anyone seeking to extrapolate future behavior from historical data. Now let's go through some other examples where linear regression is used. 1. Real estate pricing. Linear regression is widely used in real estate to predict house prices based on various features such as square footage, number of bedrooms, number of bathrooms, age of the house, and location. For instance, a regression model can help determine how much an additional bathroom adds to the house's value. For example, a real estate company uses linear regression to understand how the proximity to city centers affects the market price of properties. They find that for each mile closer to the city center, house prices increase by an average of $10,000. 2. Credit scoring. Financial institutions often employ linear regression to predict the creditworthiness of individuals based on historical financial data, including income levels, existing debts, and past repayment histories. For example, a bank may use linear regression to determine how an applicant's credit score changes with variations in their debt-to-income ratio. This helps in deciding whether to approve a loan application. 3. Supply chain costs. Linear regression can analyze and predict costs associated with different components of the supply chain, such as transportation, labor, and materials based on factors like distance, fuel prices, and labor rates. For example, a manufacturing company uses linear regression to predict logistics costs as a function of fuel price fluctuations and shipping distance to better manage their budget and set product prices. 4. Healthcare. In healthcare, linear regression could be used to predict patient outcomes based on treatment methods, dosage levels, and patient demographics. For example, a medical research team applies linear regression to study the relationship between dosage of a new drug and patient recovery rate. The findings indicate that increasing the drug dose by 1 unit enhances recovery rates by 5%. 5. Academic performance. Educational institutions might use linear regression to predict student performance based on study habits, attendance rates, and previous grades. For example, a university conducts a study using linear regression to understand how the number of hours spent studying per week impacts students' GPA. The analysis reveals that every additional hour of study per week correlates with an increase of 0.05 in GPA. 6. Energy consumption. Energy companies can use linear regression to forecast consumption levels based on factors like temperature, time of the year, and economic activity. For example, an energy utility uses linear regression to model how electricity usage increases with rising temperatures during summer months. The model helps the company prepare for peak. We will demonstrate how to use logistic regression to predict Jenny's book preferences. We have a data set where each entry records the number of pages in the books Jenny read and whether she liked them. Step 1. Import libraries. We start by importing NumPy to manage our data, Matplotlib for visualization, and Sklern's logistic regression and accuracy score for building and evaluating our model. Step 2. Prepare the data. We begin by setting up our data set. Pages holds the number of pages in each book as an independent variable, and likes records Jenny's reaction as a dependent binary variable, 1 for like and 0 for dislike. It's essential to reshape pages into a 2D array since scikit-learn's model expects features in this format. This preparation ensures our model can interpret the data correctly. Step 3. Create and train the model. We define a logistic regression model and train it with our dataset using the fit method. This method optimizes the model's parameters to best explain the relationship between the number of pages and Jenny's preferences. Training involves finding the statistical parameters that minimize prediction error, effectively learning from the data. Step 4. Make predictions. After training, we use the predict method to estimate Jenny's reaction to a book with 260 pages. This part of the code shows how the trained model applies what it has learned to new data. Step 5. Plotting. We visually present the data and model predictions. We plot the data points in green, displaying actual likes and dislikes. The model's predicted probabilities are shown in red, giving a visual representation of the likelihood of liking books of various page lengths. Specific markers highlight the query point at 260 pages, helping to contextualize the prediction visually. Step 6. Displaying prediction. Finally, we display the prediction result directly from our model using a print statement. This tells us if Jenny is predicted to like or dislike the book based on the number of pages, illustrating the practical application of our logistic regression model. Conclusion. This process illustrates how logistic regression can be used to make predictions based on historical data, providing insights that can be applied in various fields beyond just reading preferences. Now let's go over the results produced by our code. The slope of the red line. Not linear change. The slope of the red line is positive, indicating an upward curve as we move along the x-axis, representing the number of pages. This is crucial because it means the relationship between page count and Jenny's liking isn't a simple straight line increase. In other words, each additional page doesn't increase her enjoyment by the same amount. The sigmoid's effect. The S-shaped curve, typical of logistic regression, means that the change in probability is more pronounced for certain ranges of page length. There might be zones where adding more pages drastically increases the likelihood of liking the book. In contrast, other zones might show very little increase in probability despite many more pages. This is different from linear regression, where the slope remains constant and the change is directly proportional. Reasoning behind the slope. This curve's shape could suggest some underlying patterns in Jenny's preferences. Short is not sweet. Very short books might not be her cup of tea, as the stories could feel underdeveloped. The sweet spot. There might be a middle range of page counts where the probability jumps significantly, indicating her favorite type of book length. Too long. Oh, too much. Perhaps extremely long books start to have a diminishing return on her enjoyment. Green dots, model accuracy, proximity matters. The fact that the green dots, representing actual books Jenny has read, are clustered tightly around the red line is a very good sign. It signifies that the model's predictions closely align with Jenny's real-world preferences. Data validation. This clustering demonstrates the model has successfully picked up on the underlying pattern between page number and Jenny's like-dislike reactions. Consequently, we can have more confidence in its predictions for new books. Exceptions. If some green dots were far away from the line, that would be a cause for concern. It would mean the model is consistently mispredicting in those regions and might need refinement. The threshold line, 0.5, decision time. The line at 0.5 is where we translate the continuous probability values into the practical like or dislike recommendations for Jenny. Not set in stone, while 0.5 is a common threshold, it's not mandatory. Depending on how much we prioritize avoiding false positives, like predictions that turn out to be dislikes, or false negatives, dislike predictions when Jenny would have actually enjoyed the book, we might move this threshold higher or lower. Customizing for Jenny. If Jenny indicates she generally likes to try books even if she's not super sure, we might lower the threshold. This gives her more recommendations even if the certainty of her liking them is slightly lower. This logistic regression model reveals that Jenny's book preferences are influenced by page count in a non-linear way, and it has successfully learned the underlying pattern to provide more informed recommendations. Let's explore in what other sections logistic regression is used. We'll explore how logistic regression can be used to predict customer churn for a subscription-based company. Churn, or the act of customers canceling their subscriptions, poses a significant challenge for such companies. Logistic regression, with its binary outcome prediction capabilities, is an ideal choice for this scenario. The problem at hand is straightforward. The company wants to proactively identify customers who are at high risk of canceling their subscriptions, also known as churning. Logistic regression is particularly suitable for this task because it deals with binary outcomes, where a customer either churns, one, or continues their subscription. How logistic regression is used. Data gathering. The company starts by collecting historical data on various aspects of customer behavior and demographics. This includes usage patterns such as frequency and feature engagement, support interactions such as tickets opened and types of complaints, plan types distinguishing between basic and premium subscriptions, demographic information like age, location, etc. Model training. The collected data is divided into training and testing sets. A logistic regression model is then trained using the training data. During training, the model learns how different factors such as usage patterns and demographics relate to the probability of churn. Scoring new customers. Once the model is trained, it can be used to score new customers. Each customer's data is fed into the trained model, which generates a probability score between 0 and 1, indicating their likelihood of churning. Proactive action. Customers with high churn probabilities are identified and receive targeted attention. Interventions may include offering special deals, personalized outreach, or addressing common pain points known to lead to churn. Imagine Sarah, who loves cooking and trying various fruits. She's noticed that the fruits she enjoys tend to fall into certain size and sweetness ranges. Could she predict whether she'll like a new fruit based on these characteristics? Linear discriminant analysis, LDA, is the perfect tool to help her out. LDA is a powerful technique for classifying things based on several features. Think about how facial recognition software can identify individuals. In Sarah's case, we can use LDA to find patterns in the size and sweetness of fruits she's liked or disliked in the past. LDA will search for a way to create a sort of like versus dislike boundary based on these features. Imagine each fruit as a point on a graph where the x-axis is size and the y-axis is sweetness. LDA tries to draw the best possible line to separate the like and dislike fruits. Of course, some overlap might happen. Maybe there are some small fruits she surprisingly loves. LDA aims to find the line that does the best possible job of separating the groups overall. LDA is great when you have multiple features to consider at once. Sarah could try looking at size or sweetness alone, but LDA lets her combine this information for potentially better predictions. So let's go through the code now. First, we need to ensure that we have all the necessary tools at our disposal. We'll be using Python for our coding tasks and will import the powerful libraries NumPy for numerical operations and Matplotlib PyPlot for data visualization. Additionally, we'll utilize scikit-learn's linear discriminant analysis module for implementing LDA. Now, let's create a sample dataset. We'll curate a dataset consisting of 8 fruits, each characterized by 2 features, size and sweetness. These features will serve as our inputs, while the corresponding labels will indicate whether each fruit is liked, 1, or disliked, 0. This dataset will form the foundation for training our predictive model. With our dataset ready, it's time to build our predictive model using linear discriminant analysis. We'll create an instance of an LDA model object and proceed to train it using the features, size and sweetness, and corresponding labels from our sample dataset. We'll select a new fruit with a size of 2.5 and a sweetness of 6 as our test case. Using these feature values, the model will predict whether Sarah would like this fruit or not. This prediction will provide valuable insights into the model's decision-making process and its ability to generalize to unseen instances. To visualize the results of our analysis, we'll plot the sample data set on a scatter plot. In this plot, fruits that are liked by Sarah will be represented by blue markers, while disliked fruits will be marked in yellow. Additionally, we'll highlight the new fruit being predicted with a distinct red X marker, providing a clear visual representation of its classification. After making the prediction, we'll display the outcome. We'll print a statement indicating whether Sarah is likely to enjoy the new fruit based on the model's classification decision. This insight will offer valuable information on how the model interprets the given features and arrives at its prediction. Here are several considerations we should make, which shows a line graph depicting fruit enjoyment based on size and sweetness. The x-axis represents size, the y-axis represents sweetness, and the data points are colored in orange, like, and blue, dislike. Here are some observations you can make. Class separation. There appears to be some separation between the orange, like, and blue, dislike data points. This suggests that size and sweetness may be useful factors in predicting whether Sarah will enjoy a particular fruit. Overlap between classes. There's also some overlap between the two classes, particularly in the region of larger and sweeter fruits. This indicates that size and sweetness alone may not perfectly predict Sarah's preferences. Other factors not considered here might also influence her enjoyment. Here are additional considerations we should make. Sample size. The number of data points is not visible in the image. A larger data set might provide a clearer picture of the class separation and improve the model's generalizability. Non-linear relationships. The graph assumes a linear relationship between size, sweetness, and enjoyment. If the true relationship is more complex, a model like LDA might not capture it perfectly. Overall, the data suggests a potential link between fruit size, sweetness, and Sarah's preferences. LDA is a promising technique to explore for building a classification model, but it's important to consider potential limitations and the need for more data if available. Where decision trees take root. Decision trees, with their intuitive branching structure, find use across various industries and problem domains. Let's dive into some key areas where they prove particularly effective. Business and finance. Customer segmentation. Analyze customer data to identify groups with similar behaviors or purchasing patterns for targeted marketing strategies. Fraud detection. Identify patterns in transactions that may indicate fraudulent activity. Credit risk assessment. Evaluate the creditworthiness of loan applicants based on their financial history and other factors. Operations management. Optimize decision-making in areas like inventory management, logistics, and resource allocation. Healthcare, medical diagnosis, support. Assist in diagnosing diseases by guiding clinicians through a series of questions and tests based on patient symptoms and medical history. Treatment planning. Help determine the most suitable treatment options based on patient characteristics and disease severity. Disease risk prediction. Identify individuals at high risk of developing certain health conditions based on factors like lifestyle, family history, and medical data. Science and engineering, fault diagnosis. Isolate the cause of malfunctions or failures in complex systems by analyzing sensor data and system logs. Classification in biology. Categorize species based on their characteristics or DNA sequences. Remote sensing. Analyze satellite imagery to classify land cover types or identify areas affected by natural disasters. Customer service. Troubleshooting guides. Create interactive decision trees to guide customers through troubleshooting steps for products or services. Chatbots. Power automated chatbots that can categorize customer inquiries and provide appropriate responses, reducing wait times and improving support efficiency. Other applications. Game playing. Design AI opponents in games that can make strategic decisions. Logistic regression is a popular approach for performing classification when there are two classes. But when the classes are well separated or the number of classes exceeds 2, the parameter estimates for the logistic regression model are surprisingly unstable. Unlike logistic regression, LDA does not suffer from this instability problem when the number of classes is more than 2. If n is small and the distribution of the predictors x is approximately normal in each of the classes, LDA is again more stable than the logistic regression model. Noah is a botanist who has collected data about various plant species and their characteristics, such as leaf size and flower color. Noah is curious if he could predict a plant species based on these features. Here, we'll utilize random forest and ensemble learning method to help him classify plants. Technically, we aim to classify plant species based on certain predictive variables using a random forest model. The bias-variance trade-off. The key challenge in machine learning lies in finding the right balance between bias and variance. Generally, reducing bias increases variance and vice versa. Complex models tend towards low bias and high variance, while simpler models tend towards the opposite. The ideal model finds a sweet spot between underfitting, high bias, and overfitting, high variance. a balance that depends heavily on the nature of your specific problem and the trade-off you're willing to make between flexibility and stability. Naive Bayes versus logistic regression. Naive Bayes is known for high bias. It assumes features are independent, which often isn't true. However, its simplicity makes it less prone to overfitting, low variance, and computationally fast to train. On the other hand, logistic regression is more flexible, low bias, and can model complex decision boundaries. This comes at the risk of overfitting, high variance, especially with many features or little regularization. When to choose which? If you prioritize speed and simplicity, naive Bayes might be a good starting point. When your data relationships are unlikely to be simple and independent, logistic regression's flexibility becomes valuable. However, if you choose logistic regression, you need to actively manage overfitting, potentially using techniques like regularization. For plotting purposes, and scikit-learn's logistic regression and linear discriminant analysis for classification tasks. Step 2. Generating synthetic data. Next, we define a function called generateData to create synthetic data for our classification experiment. The function generates data points from 3 initial classes, each centered at 0, 0, 3, 0, and 6, 0. For each class, random data points are generated around the respective center using a Gaussian distribution. Step 3. Data generation and model fitting. We generate a dataset with 40 samples per class using the generateData function. Then we fit logistic regression and LDA models to this dataset. Step 4. Analyzing the results. After fitting the models, we print the coefficients for both logistic regression and LDA for the initial 3 classes. These coefficients provide insights into the decision boundaries learned by each model. Step 5. Adding an extra class. We then introduce a new class to our dataset by generating additional data points centered at 9, 0. We append this new class to our dataset and update the corresponding labels accordingly. Step 6. Refitting the models. Following the addition of the new class, we refit both logistic regression and LDA models to the updated dataset with 4 classes. Step 7. Analyzing the results for 4 classes. Finally, we print the coefficients for both models after fitting them to the dataset with 4 classes. This allows us to observe how the decision boundaries change with the inclusion of the new class. The provided code serves to elucidate the intricate concepts of bias, variance, and the bias-variance trade-off by juxtaposing naive Bayes and logistic regression classifiers on a synthetic dataset. Here's a cohesive explanation of the code's functionality. To begin, the script generates a synthetic dataset comprising 2 classes arranged in circular patterns. The make circles function from scikit-learn is employed for this purpose, creating data that challenges the assumptions of naive Bayes due to its nonlinear separability. Following data generation, the script proceeds to train 2 distinct classifiers. Firstly, a Gaussian naive Bayes model is trained on the dataset. This choice aligns with the high bias, low variance characteristics of naive Bayes, given its simplicity and assumption of feature independence. Secondly, a logistic regression model is trained with regularization, CMA 1.0. Regularization is introduced to combat overfitting, a concern for logistic regression due to its flexibility, potentially leading to higher variance. And the script visualizes their decision boundaries. Through plots showcasing the decision boundaries of both models, it becomes evident that naive Bayes delineates a simpler linear boundary, while logistic regression captures the data set's nonlinearity. Furthermore, the script calculates the accuracy of each model on a held-out test set, facilitating a comparative analysis of their performance. A deeper understanding of the bias-variance trade-off emerges from this comparison. Naive Bayes exhibits higher bias due to its simplifying assumptions, resulting in a less complex decision boundary. On the contrary, logistic regression's flexibility enables it to learn the nonlinear pattern with lower bias potential, albeit at the risk of overfitting. The importance of contextual considerations becomes apparent. While logistic regression often boasts lower bias, naive Bayes' simplicity and computational efficiency may render it preferable in certain contexts. Tom is a movie enthusiast who watches films across different genres and records his feedback, whether he liked them or not. He has noticed that whether he likes a film might depend on two aspects: the movie's length and its genre. Can we predict whether Tom will like a movie based on these two characteristics using naive Bayes? Technically, we want to predict a binary outcome, like or dislike, based on the independent variables, movie length and genre. Let's delve into the code's functionality. The initial step involves importing essential libraries necessary for the code's operations. NumPy facilitates numerical operations, while Matplotlib aids in visualization. Additionally, the Gaussian naive Bayes implementation from scikit-learn is imported to utilize its functionalities. Following the imports, the script defines sample data representing movie features and corresponding likes. Each movie is characterized by its length in minutes and a genre code. Notably, genres are numerically encoded, with 0 signifying action, 1 representing romance, and so forth. This structured representation prepares the data for subsequent analysis. Moving forward, a Gaussian naive Bayes model is instantiated. This model serves as the predictive engine, leveraging its inherent assumptions about feature independence to classify movie likes. Subsequently, the model is trained using the provided movie features and their associated likes. Once the model is trained, it is ready to make predictions. A new movie is defined with its length and genre code. Leveraging the trained naive Bayes model, predictions are made regarding whether Tom would like this movie based on its features. This step demonstrates the practical application of the trained model in making real-world predictions. The script proceeds to visualize the dataset through a scatter plot. Each existing movie is plotted based on its length and genre code, with liked movies depicted in one color and disliked movies in another. Additionally, the new movie is plotted with a distinct marker, providing visual context to aid interpretation. The provided code serves to elucidate the intricate concepts of bias, variance, and the bias-variance trade-off by juxtaposing naive Bayes and logistic regression classifiers on a synthetic dataset. Here's a cohesive explanation of the code's functionality. To begin, the script generates a synthetic dataset comprising two classes arranged in circular patterns. The make circles function from scikit-learn is employed for this purpose, creating data that challenges the assumptions of naive Bayes due to its nonlinear separability. Following data generation, the script proceeds to train two distinct classifiers. Firstly, a Gaussian naive Bayes model is trained on the dataset. This choice aligns with the high bias, low variance characteristics of naive Bayes, given its simplicity. Here are a few observations and conclusions we can make. Clear separation. We can see that there is a clear separation between the like and dislike clusters. This indicates that the naive Bayes model has successfully found a distinct boundary based on the movie length and genre features. The strong separation suggests these features are powerful predictors of preference. Prediction confidence. Since the new movie, Red X, falls squarely within a cluster, we can have a high degree of confidence in the model's prediction. Further exploration. Even with good separation, movies lying close to the boundary deserve closer examination. They may offer insights into less predictable cases and help refine the model further. Overlapping clusters. If the like and dislike groups overlap significantly, it suggests that movie length and genre alone may not be enough to accurately predict preferences in all situations. Model limitations. In cases of overlap, naive Bayes might be too simplistic. Exploring more sophisticated models like decision trees or support vector machines could improve accuracy. Need. More data, a larger and more diverse data set, or the inclusion of additional features, e.g., star ratings, director, could help uncover clearer patterns in situations where the current features aren't sufficient. Genre, significance. If distinct clusters form based on genre codes, it means the naive Bayes model recognizes genre as a strong indicator of preference. Personalized recommendations. This genre-based insight can be used to tailor recommendations. If a user consistently enjoys a particular genre, movies within that genre should be prioritized, even if their length deviates from the usual pattern. Caveats. It's important to remember that genre preferences are subjective and might have naturally mixed reactions within a given genre. Where decision trees take root. Decision trees, with their intuitive branching structure, find use across various industries and problem domains. Let's dive into some key areas where they prove particularly effective. Business and finance. Customer segmentation. Analyze customer data to identify groups with similar behaviors or purchasing patterns for targeted marketing strategies. Fraud detection. Identify patterns in transactions that may indicate fraudulent activity. Credit risk assessment. Evaluate the creditworthiness of loan applicants based on their financial history and other factors. Operations management. Optimize decision-making in areas like inventory management, logistics, and resource allocation. Healthcare, medical diagnosis, support. Assist in diagnosing diseases by guiding clinicians through a series of questions and tests based on patient symptoms and medical history. Treatment planning. Help determine the most suitable treatment options based on patient characteristics and disease severity. Disease risk prediction. Identify individuals at high risk of developing certain health conditions based on factors like lifestyle, family history, and medical data. Science and engineering, fault diagnosis. Isolate the cause of malfunctions or failures in complex systems by analyzing sensor data and system logs. Classification in biology. Categorize species based on their characteristics or DNA sequences. Remote sensing. Analyze satellite imagery to classify land cover types or identify areas affected by natural disasters. Customer service. Troubleshooting guides. Create interactive decision trees to guide customers through troubleshooting steps for products or services. Chatbots. Power automated chatbots that can categorize customer inquiries and provide appropriate responses, reducing wait times and improving support efficiency. Other applications. Game playing. Design AI opponents in games that can make strategic decisions based on the state of the game. E-commerce. Personalized product recommendations based on user browsing behavior and past purchases. Human resources. Identify key factors influencing employee retention and make informed decisions. Why decision trees thrive. Here, decision trees excel in these scenarios due to several factors. Interpretability. The decision-making process is transparent, allowing humans to understand the reasoning behind the model's predictions. Handles diverse data, accommodates both numerical and categorical features. Nonlinear relation. Alex is intrigued by the relationship between the number of hours studied and the scores obtained by students. Alex collected data from his peers about their study hours and respective test scores. He wonders, Can we predict a student's score based on the number of hours they study? Let's leverage decision tree regression to uncover this. Technically, we're predicting a continuous outcome test score based on an independent variable, study hours, complex patterns. This is like trying to fit a curved dataset with a straight line. In contrast, a low bias model is more flexible, allowing it to potentially match intricate trends in the data. Noah is a botanist who has collected data about various plant species and their characteristics, such as leaf size and flower color. Noah is curious if he could predict a plant species based on these features. Here, we'll utilize random forest and ensemble learning method to help him classify plants. Technically, we aim to classify plant species based on certain predictive variables using a random forest model. The bias-variance trade-off. The key challenge in machine learning lies in finding the right balance between bias and variance. Generally, reducing bias increases variance and vice versa. Complex models tend towards low bias and high variance, while simpler models tend towards the opposite. The ideal model finds a sweet spot between underfitting, high bias, and overfitting, high variance. A balance that depends heavily on the nature of your specific problem and the trade-off you're willing to make between flexibility and stability. Naive Bayes versus logistic regression. Naive Bayes is known for high bias. It assumes features are independent, which often isn't true. However, its simplicity makes it less prone to overfitting, low variance, and computationally fast to train. On the other hand, logistic regression is more flexible, low bias, and can model complex decision boundaries. This comes at the risk of overfitting, high variance, especially with many features or little regularization. When to choose which. If you prioritize speed and simplicity, naive Bayes might be a good starting point. When your data relationships are unlikely to be simple and independent, logistic regression's flexibility becomes valuable. However, if you choose logistic regression, you need to actively manage overfitting, potentially using techniques like regularization. The provided code serves to elucidate the intricate concepts of bias, variance, and the bias-variance trade-off by juxtaposing naive Bayes and logistic regression classifiers on a synthetic dataset. Here's a cohesive explanation of the code's functionality. To begin, the script generates a synthetic dataset comprising two classes arranged in circular patterns. The make circles function from scikit-learn is employed for this purpose, creating data that challenges the assumptions of naive Bayes due to its nonlinear separability. Following data generation, the script proceeds to train two distinct classifiers. Firstly, a Gaussian naive Bayes model is trained on the dataset. This choice aligns with the high bias, low variance characteristics of naive Bayes, given its simplicity and assumption of feature independence. Secondly, a logistic regression model is trained with regularization. Regularization is introduced to combat overfitting, a concern for logistic regression due to its flexibility, potentially leading to higher variance. Once the models are trained, the script visualizes their decision boundaries. Through plots showcasing the decision boundaries of both models, it becomes evident that naive Bayes delineates a simpler linear boundary, while logistic regression captures the data set's nonlinearity. Furthermore, the script calculates the accuracy of each model on a held-out test set, facilitating a comparative analysis of their performance. A deeper understanding of the bias-variance trade-off emerges from this comparison. Naive Bayes exhibits higher bias due to its simplifying assumptions, resulting in a less complex decision boundary. On the contrary, logistic regression's flexibility enables it to learn the nonlinear pattern with lower bias potential, albeit at the risk of overfitting. The importance of contextual considerations becomes apparent. While logistic regression often boasts lower bias, naive Bayes' simplicity and computational efficiency may render it preferable in certain contexts. Model selection hinges on factors such as dataset characteristics, computational constraints, and the relative significance of interpretability versus raw predictive performance. It's crucial to acknowledge the limitations and caveats of the presented example. The observed results may vary on different datasets or with alternative hyperparameter configurations. Additionally, while decision boundary visualization aids comprehension, accuracy metrics are equally essential for comprehensive model evaluation. Finally, the script underscores the significance of continuous learning in machine learning. It advocates for a methodical approach involving experimentation with diverse models, rigorous evaluation, and judicious selection based on problem-specific requirements and performance metrics. Tom is a movie enthusiast who watches films across different genres and records his feedback, whether he liked them or not. He has noticed that whether he likes a film might depend on two aspects: the movie's length and its genre. Technically, we want to predict a binary outcome, like or dislike, based on the independent variables, movie length and genre. Alex is intrigued by the relationship between the number of hours studied and the scores obtained by students. Alex collected data from his peers about their study hours and respective test scores. He wonders, can we predict a student's score based on the number of hours they study? Let's leverage decision tree regression to uncover this. Technically, we're predicting a continuous outcome test score based on an independent variable, study hours. Let's dissect the code to understand its functionality. Importing libraries. We begin by importing necessary libraries. NumPy assists in numerical operations, Matplotlib facilitates visualization, and Decision Tree Regressor from scikit-learn is utilized for decision tree regression. Sample data definition. Following the library imports, the code defines sample data. This data includes the number of hours studied and the corresponding test scores achieved. Each entry pairs a study hour with its corresponding test score, forming the dataset for training the regression model. Creating and training the model, a decision tree. Regression model is instantiated with a maximum depth set to 3. This parameter controls the maximum number of levels within the decision tree. Subsequently, the model is trained using the provided study hours and their corresponding test scores. Prediction. After training, the model is capable of making predictions. An example, study hour 5.5 hours is chosen, and the model predicts the test score corresponding to this input based on its training. Plotting the decision tree. The code then generates a visualization of the decision tree regression model. This visualization elucidates the decision-making process of the model, utilizing the provided features, study hours, plotting study hours versus test scores. Another plot is created to illustrate the relationship between study hours and test scores. This scatter plot displays the actual data points, while the regression line portrays the predictions made by the decision tree regression model. Additionally, the predicted test score for the new study hour is highlighted, displaying prediction. Finally, the code prints out the predicted test score for the specified study hour. Now here are some key features. Sample data. Study.hours contains hours studied, and test scores contains the corresponding test scores. Creating and training model. We create a decision tree regressor with a specified maximum depth to prevent overfitting and train it with .fit using our data. Plotting the decision tree. Plot tree helps visualize the decision-making process of the model, representing splits, based on study hours. Prediction and plotting. We predict the test score for a new study hour value, 5.5 in this example. Visualize the original data points, the decision tree's predicted scores, and the new prediction. Now, here are a few conclusions we can make from the decision tree regressor visualization and the study hours versus test scores plot. Observations from the plot: linear progression with step function. The orange line representing the predicted scores demonstrates a clear step function, a typical characteristic of decision tree regressors. This indicates that the model provides constant predictions within certain ranges of study hours, changing abruptly at specific thresholds where new rules, splits, apply. Prediction accuracy. The red dots, actual scores, mostly align with the orange step function, predicted scores, suggesting that the decision tree model does a good job of capturing the general trend in the data. The close alignment also indicates that the model handles the nonlinear relationship between study hours and test scores well, within the constraints of its maximum depth. Specific prediction. The plot marks a prediction for 5.5 hours of study, green X. This specific prediction falls on the step increase, suggesting that additional study hours beyond a certain threshold significantly improve the predicted test score, according to the model's training data. Conclusions. Model fit. The decision tree appears well fitted to the range of data presented, without signs of overfitting or underfitting. The choice of maximum depth seems appropriate, balancing model complexity and generalization. Utility of decision tree for educational data. Decision trees are useful for educational data like study hours and test scores because they can easily model thresholds, e.g., minimum hours needed to achieve a certain score, that are intuitive for educational planning and interventions. Implications for students and educators. This model can help in setting realistic study goals based on expected outcomes. For instance, educators can advise students about the probable benefit of studying an additional hour based on the model's predictions. Potential for refinement. While the current model provides valuable insights, further refinement with additional features like type of study material, individual student baseline performance, etc., could enhance prediction accuracy. Testing the model on more diverse datasets or incorporating ensemble methods like random forests could provide a more robust analysis and mitigate any variance not captured by a single decision tree. Visualization and interpretation. The stepwise visualization aids in understanding how additional study hours could lead to increments in test scores, which is valuable for explaining model behavior to non-technical stakeholders. Where decision trees take root. Decision trees, with their intuitive branching structure, find use across various industries and problem domains. Let's dive into some key areas where they prove particularly effective. Business and finance. Customer segmentation. Analyze customer data to identify groups with similar behaviors or purchasing patterns for targeted marketing strategies. Fraud detection. Identify patterns in transactions that may indicate fraudulent activity. Credit risk assessment. Evaluate the creditworthiness of loan applicants based on their financial history and other factors. Operations management. Optimize decision-making in areas like inventory management, logistics, and resource allocation. Healthcare, medical diagnosis, support, assist in diagnosing diseases by guiding clinicians through a series of questions and tests based on patient symptoms and medical history. Treatment planning. Help determine the most suitable treatment options based on patient characteristics and disease severity. Disease risk prediction. Identify individuals at high risk of developing certain health conditions based on factors like lifestyle, family history, and medical data. Science and engineering, fault diagnosis. Isolate the cause of malfunctions or failures in complex systems by analyzing sensor data and system logs. Classification in biology. Categorize species based on their characteristics or DNA sequences. Remote sensing. Analyze satellite imagery to classify land cover types or identify areas affected by natural disasters. Customer service. Troubleshooting guides. Create interactive decision trees to guide customers through troubleshooting steps for products or services. Chatbots. Power automated chatbots that can categorize customer inquiries and provide appropriate responses, reducing wait times and improving support efficiency. Other applications. Game playing. Design AI opponents in games that can make strategic decisions based on the state of the game. E-commerce. Personalized product recommendations based on user browsing behavior and past purchases. Human resources. Identify key factors influencing employee retention and make informed decisions. Why decision trees thrive. Here, decision trees excel in these scenarios due to several factors. Interpretability. The decision-making process is transparent, allowing humans to understand the reasoning behind the model's predictions. Handles diverse data, accommodates both numerical and categorical features. Nonlinear relationships, can capture complex nonlinear patterns within data. Versatility, applicable for both classification, predicting a class label, and regression. Meet Lucy, a fitness coach who is curious about predicting her clients' weight loss based on their daily calorie intake and workout duration. Lucy has data from past clients but recognizes that individual predictions might be prone to errors. Let's utilize bagging to create a more stable prediction model. Technically, we'll predict a continuous outcome, weight loss, based on two independent variables, daily calorie intake and workout duration, using bagging to reduce variance in predictions. Let's now go through the code. Importing libraries. We begin by importing the necessary libraries. NumPy is imported as NP to facilitate numerical operations. Matplotlib.pyplot is imported as PLT for visualization purposes, and Gaussian NB is imported from scikit-learn to implement the Gaussian naive Bayes classifier. Sample data definition. Moving on, the code defines sample data representing movie features and their corresponding likes. The movie's features array contains pairs of movie length in minutes and genre codes, where each genre is encoded numerically, e.g., 0 for action, 1 for romance. The movie's likes array denotes whether each movie is liked, 1, or disliked, 0. Creating and training the model. A Gaussian naive Bayes model is instantiated using Gaussian NB, creating an instance named model. This model is then trained using the fit method with movies features as the input features and movies likes as the target labels. Prediction. Following training, the model is ready to make predictions. An example, new movie, is defined with a length of 100 minutes and a genre code of 1. This new movie is represented as a NumPy array named new movie. The model's predict method is then employed to predict whether Tom will like or dislike this new movie. Plotting. To visualize the movie data, the code generates a scatter plot using plt.scatter. Existing movies are plotted using circles, marker O, with their length on the x-axis and genre code on the y-axis. Liked movies are depicted in one color, while disliked movies are depicted in another. Additionally, the new movie is plotted with a different marker, a red X, to highlight its position, displaying prediction. Finally, the code prints a message indicating whether Tom will like the new movie. If the predicted like value is 1, the message states that Tom will like the movie. Otherwise, it suggests that he will not. Here are several key features. Clients. Data contains daily calorie intake and workout duration, and weight loss contains the corresponding weight loss. Train test split. We split the data into training and test sets to validate the model's predictive performance. Creating and training model. We instantiate bagging regressor with decision tree regressor as the base estimator and train it using .fit with our training data. Prediction and evaluation. We predict weight loss for the test data, evaluating prediction quality with mean squared error, MSE. Visualizing one of the base estimators. Optionally, visualize one tree from the ensemble to understand individual decision-making processes, keeping in mind an individual tree may not perform well, but collectively they produce stable predictions. Here's a breakdown of the key points. True weight loss. This range, 2 to 4.5 pounds, represents the actual weight loss experienced by the clients in the test set. Predicted weight loss. This range, 3.1 to 3.96 pounds, represents the model's predictions for weight loss in the test set. Mean squared error, MSE, 0.75. This metric measures the average squared difference between the predicted weight loss and the true weight loss. A lower MSE generally indicates better model performance. In simpler terms, the model predicts weight loss somewhat accurately, but there are deviations between the predictions and the actual weight loss experienced by the clients. On average, the model's predictions were off by 0.75 pounds squared. In our previous explorations of machine learning, we've come to recognize the inherent strengths and limitations of individual models. Some models are masters of simplicity, offering quick interpretable results, while others thrive in handling complex, high-dimensional data sets. Yet, all models are susceptible to the twin challenges of bias and variance. This is where bagging enters as a powerful ally, leveraging the wisdom of crowds to forge better predictive frameworks. Applications of bagging regression problems. Imagine you're attempting to predict housing prices within a bustling city. Factors like square footage, location, number of bedrooms, and countless others collectively influence the price. A single linear regression model might struggle to capture the intricate relationships between these features. Bagging comes to the rescue. By training multiple regressors, like decision trees, on diverse samples of the data and averaging their predictions, we reduce variance and improve accuracy. Classification quests. Perhaps you're tasked with classifying customer reviews as positive or negative. A lone naive Bayes classifier might make oversimplified assumptions about word independence, resulting in subpar performance. Bagging empowers us to assemble an ensemble of classifiers. Each member of the ensemble casts a vote, and the majority vote often yields a superior classification decision, mitigating the shortcomings of any single model. Image recognition. The vast world of image recognition presents unique challenges with high-dimensional data. Convolutional neural networks, CNNs, while remarkably powerful, can fall prey to overfitting. With bagging at our disposal, we can create a council of independently trained CNNs, where each network focuses on distinct subsets of the image data. Aggregating their predictions instills robustness and can significantly improve classification results. Harnessing the power of diversity. The cornerstone of bagging lies in cultivating diversity within its ensemble. By constructing models on varying bootstrapped samples of the original dataset, each model develops slightly different biases. This clever strategy combats bias through its collective approach. Moreover, the random nature of sampling reduces variance, particularly when working with unstable algorithms like decision trees. Real-world examples. Healthcare. In medical diagnosis, where precision is paramount, bagging is widely used. Ensembles of models trained on patient data often lead to enhanced accuracy in identifying diseases, contributing to better healthcare decision-making. Finance. Financial institutions employ bagging for critical tasks such as fraud detection and risk assessment. Aggregated models built with bagging techniques are frequently more efficient at detecting anomalies and spotting fraudulent patterns, aiding in the protection of valuable assets. Environmental science. Bagged models are leveraged in tasks ranging from land cover classification to climate modeling. The ability to create more stable and reliable predictions from diverse datasets and models proves invaluable when tackling complex environmental challenges. Remember, while bagging empowers us with stronger predictive prowess, it's not a magic bullet. Random forests provide an improvement over bagged trees by way of a small tweak that decorrelates the trees. As in bagging, we build a number of decision trees on bootstrap training samples, but when building these decision trees, each time a split in a tree is considered, a random sample of M predictors is chosen as split candidates from the full set of P predictors. The split is allowed to use only one of those M predictors. A fresh and random sample of M predictors is taken at each split, and typically we choose MP. That is, the number of predictors considered at each split is approximately equal to the square root of the total number of predictors. This is also the reason why random forest is called random. The main difference between bagging and random forests is the choice of predictor subset size M decorrelates the trees. Using a small value of M in building a random forest will typically be helpful when we have a large number of correlated predictors. So if you have a problem of multicollinearity, RF is a good method to fix that problem. So unlike in bagging, in the case of random forest, in each tree split, not all P predictors are considered, but only randomly selected M predictors from it. This results in not similar trees being decorrelated, and due to the fact that averaging decorrelated trees results in smaller variance, random forest is more accurate than bagging. Noah is a botanist who has collected data about various plant species and their characteristics, such as leaf size and flower color. Noah is curious if he could predict a plant species based on these features. Here, we'll utilize random forest and ensemble learning method to help him classify plants. Technically, we aim to classify plant species based on certain predictive variables using a random forest model. Let's walk through the provided code step by step. Importing libraries. The code starts by importing necessary libraries such as NumPy for numerical operations, Matplotlib for visualization, Random Forest Classifier from scikit-learn for random forest classification, Train Test Split for splitting the data, and Classification Ds report for evaluating classification performance. Data preparation. The code defines two NumPy arrays, plants age and features containing the features of plants, leaf size and flower color, and plants or species containing the corresponding species labels. Each row in plants features represents a plant, and the corresponding entry in plants species denotes its species, 0 or 1. Train test split. The dataset is split into training and testing sets using the train test split function. This ensures that the model is trained on a portion of the data and evaluated on an unseen portion. The split ratio is set to 75% training data and 25% testing data. Model initialization and training. A random forest classifier model is initialized with 10 estimators, trees, and a random state of 42 for reproducibility. The initialized model is then trained using the training data, X-train and Y-train. Random forests build multiple decision trees and combine their predictions to improve generalization performance. prediction and evaluation. The trained model is used to make predictions, y or spread, on the test data, x to test. These predictions are then evaluated using the classification force report function, which generates a detailed report including precision, recall, F1 score, and support for each class. Displaying prediction and evaluation. The classification report containing evaluation metrics is printed to the console, providing insights into the model's performance. Visualization. 2 visualizations are generated to gain insights into the data and model. Scatter plot of species. This plot visualizes the distribution of plants' features, leaf size, and flower color for each species. Different marker shapes and colors represent different species, making it easier to distinguish between them. Feature importance. This horizontal bar plot visualizes the importance of each feature, leaf size, and flower color in predicting plant species. Features with higher importance values contribute more to the model's decision-making process. Interpreting the scatter plot. The scatter plot shows the distribution of plant data points based on their leaf size and flower color coded. The different marker colors, green and red, represent the 2 plant species, 0 and 1. Partial separation. There appears to be some separation between the green and red data points, suggesting that leaf size and flower color might be partially effective in distinguishing between the 2 plant species. Overlap. We can also observe some overlap between the green and red clusters, particularly towards the center of the plot. This overlap indicates that some plants might have similar leaf size and flower color features, regardless of species. This overlap may lead to some classification errors by the random forest model. Potential challenges. The overlap between the 2 species in the scatter plot suggests that the model might struggle to accurately classify plants that fall in these overlapping areas. Overall, the scatter plot provides a visual representation of the data that can be helpful in interpreting the performance of the random forest model. Key points from the bar chart. The bar chart depicts the feature importances for leaf size and flower color. The height of the bar represents the feature's importance. In this case, the bar for flower color is considerably higher than the one for leaf size. Interpretation. This visualization confirms what we might have inferred from the scatter plot. Flower color carries more weight in the model's decision-making process for plant species classification. This is likely because the flower color data seems to have a clearer separation between the 2 species, green and red dots, in the scatter plot. Overall conclusions. The random forest model partially leverages both leaf size and flower color for classification, but flower color appears to be the more dominant feature. The model's performance might be limited by the overlap between the 2 species in the data, particularly for plants with similar leaf size and flower color values. Random forests, a versatile machine learning algorithm, find applications across various domains, including finance and banking, healthcare, e-commerce, marketing, and more. Finance and banking. In fraud detection, random forests excel in spotting irregular patterns in transactions, leveraging features such as transaction amount, location, frequency, and merchant type to flag potential fraudulent activities. For credit risk assessment, these models evaluate borrowers' creditworthiness by analyzing factors like income, debt-to-income ratio, credit history, and employment status, predicting the likelihood of default accurately. Additionally, in stock market prediction, random forests leverage historical stock prices, company fundamentals, news sentiment, and market trends to forecast future prices, though this remains challenging. Healthcare. In medical diagnosis, random forests classify patients based on various medical data like test results, symptoms, and patient history, aiding healthcare providers in making informed decisions. For drug discovery, and development, researchers utilize these models to identify potential drug candidates by analyzing molecular structures, gene expression data, and existing drug information. Furthermore, in personalized medicine, random forests help tailor treatments to individual patients by considering factors like genetics, medical history, and lifestyle, enabling predictions of patient response to specific therapies or medication dosages. E-commerce and marketing. Customer segmentation benefits from random forests as they group customers based on purchase history, browsing behavior, demographics, etc., facilitating targeted marketing and personalization efforts. For product recommendations, these models analyze customer purchase patterns, product ratings, and search history to offer relevant product suggestions, thereby enhancing user experience and boosting sales. Moreover, in churn prediction, random forests identify customers at risk of leaving by examining usage patterns, service interactions, and demographic data, allowing for proactive retention strategies. Other notable areas: random forests find applications in environmental science, aiding tasks like land cover classifications using satellite imagery, monitoring deforestation, and assessing climate change impact. In image analysis, they assist in image classification tasks such as facial recognition, object detection in self-driving cars, and analyzing medical imaging scans. Furthermore, in network intrusion detection, random forests help identify suspicious network traffic patterns by analyzing features like source and destination IP addresses, protocols used, and packet sizes, contributing to cybersecurity efforts. It's important to note that while random forests are generally robust to overfitting due to their ensemble nature, careful feature selection and hyperparameter tuning are crucial for optimal performance. Additionally, random forests work well with both categorical with missing values or outliers. Like bagging, which averages correlated decision trees, and random forest, which averages uncorrelated decision trees. Boosting aims to improve the predictions resulting from a decision tree. Boosting is a supervised machine learning model that can be used for both regression and classification problems. Unlike bagging or random forest, where the trees are built independently from each other using one of the B bootstrapped samples, copy of the initial training date. In boosting, the trees are built sequentially and dependent on each other. Each tree is grown using information from previously grown trees. Boosting does not involve bootstrap sampling. Instead, each tree fits on a modified version of the original data set. It's a method of converting weak learners into strong learners. In boosting, each new tree is a fit on a modified version of the original data set. So, unlike fitting a single large decision tree to the data, which amounts to fitting the data hard and potentially overfitting, the boosting approach instead learns slowly. Given the current model, we fit a decision tree to the residuals from the model. That is, we fit a tree using the current residuals rather than the outcome y as the response. We then add this new decision tree into the fitted function in order to update the residuals. Each of these trees can be rather small, with just a few terminal nodes, determined by the parameter d in the algorithm. Now let's have a look at three most popular boosting models in machine learning. The first ensemble algorithm we will look into today is AdaBoost. Like in all boosting techniques, in the case of AdaBoost, the trees are built using the information from the previous tree, and more specifically part of the tree which didn't perform well. This is called the weak learner decision stump. This decision stump is built using only a single predictor and not all predictors to perform the prediction. So AdaBoost combines weak learners to make classifications, and each stump is made by using the previous stump's errors. Here is the step-by-step plan for building an AdaBoost model. Step 1. Initial weight assignment. Assign equal weight to all observations in the sample where this weight represents the importance of the observations being correctly classified. 1 times n, all samples are equally important at this stage. Step 2. Optimal predictor selection. The first stump is built by obtaining the RSS in case of regression or Gini index entropy in case of classification for each predictor. Picking the stump that does the best job in terms of prediction accuracy, the stump with the smallest RSS or Gini entropy is selected as the next tree. Step 3. Computing stumps. Weight based on stumps. We increase the weight of the observations which have been incorrectly predicted and decrease the remaining observations which had higher accuracy or have been correctly classified, so that the next stump will have higher importance of correctly predicted the value of this observation. Step 5. Building the next stump based on updated weights, using weighted Gini index to choose the next stump. Step 6. Combining B stumps. Then all the stumps are combined while taking into account their importance, weighted sum. Imagine a scenario where we aim to predict house prices based on certain features like the number of rooms and age of the house. For this example, let's generate synthetic data where num rooms, the number of rooms in the house age, the age of the house in years. Price. The price of the house in $1,000, importing libraries. The code starts by importing necessary libraries. NumPy for numerical operations, pandas for data manipulation, matplotlib for visualization, and specific modules from scikit-learn for machine learning tasks like model selection, ensemble learning, and evaluation metrics. Data generation. Synthetic data is generated to mimic a real-world scenario. Random numbers are generated to represent the number of rooms in a house, num rooms, the age of the house age, and noise. The price of the house price is then calculated based on a linear relationship with the number of rooms, age of the house, and added noise. Data visualization. The generated data is visualized using scatter plots. 2 scatter plots are created, one showing the relationship between the number of rooms and the house price, and the other showing the relationship between the age of the house and the house price. This visualization helps in understanding the distribution and relationships between features and the target variable, price. Data splitting. The data is split into training and testing sets using the train-test-split function from scikit-learn. This step is essential for training the model on one subset of data, training set, and evaluating its performance on another subset, testing set. Model initialization and training. An AdaBoost regressor model is initialized with specific parameters like the number of estimators, decision trees set to 100, and a random seed for reproducibility. The model is then trained using the training data X-train and Y-train. Model evaluation. Once trained, the model makes predictions on the test data X-test. The mean squared error, MSE, and root mean squared error, RMSE, metrics are calculated to evaluate the model's performance compared to the actual house prices, Y-test. Result visualization. The actual house prices, Y-test, and the predicted prices are visualized using a scatter plot. The plot also includes a diagonal line representing perfect predictions. This visualization aids in assessing how closely the model's predictions align with the actual prices. The scatter plot provided shows 2 key relationships, number of rooms versus price. This is represented by the green data points. There appears to be a positive correlation, meaning as the number of rooms increases, the price of the house also tends to increase. This is likely because houses with more rooms are generally larger and more expensive. House age versus price. This is represented by the red data points. The relationship here is less clear. There might be a slight negative correlation where newer houses, lower house age, tend to be more expensive. However, the data points are scattered, making it difficult to draw a definitive conclusion. Additional points to consider. The data points themselves show some variation around the general trends. This indicates that there might be other factors influencing house price besides the number of rooms and house age, e.g., location, amenities. It's important to note that this is simulated data, and real estate prices can be influenced by many complex factors. Overall, the scatter plot suggests that the number of rooms has a positive correlation with house price, while the relationship between house age and price is less clear-cut. The scatter plots you saw provide valuable insights into the data, but AdaBoost plays a crucial role in uncovering the underlying relationship between features, number of rooms, house age, and price. Here's how: capturing complex relationships. The data exhibits some scatter around the general trends, suggesting the price isn't perfectly explained by just number of rooms and house age. AdaBoost excels in handling such scenarios. It's an ensemble method that combines multiple weak decision trees into a stronger final model. These decision trees can effectively capture nonlinear patterns in the data, providing a more nuanced understanding of the price-feature relationship than a single linear model. Focus on informative features. While both scatter plots offer clues, AdaBoost goes beyond simply visualizing correlations. It analyzes the data to determine which features, number of rooms, house age, are most informative for predicting price. By focusing on these features during the decision tree creation process, AdaBoost prioritizes the factors that have the strongest influence on price. Iterative refinement. AdaBoost works in a staged manner. It trains a series of weak decision trees, each focusing on correcting the errors of the previous one. By visualizing the data, we can get a general sense of the trends, but AdaBoost iteratively refines its understanding through these multiple stages, ultimately leading to a more accurate prediction model. In essence, the scatter plots provide a starting point for understanding the data, but AdaBoost acts as a powerful tool to leverage that initial understanding and build a more robust model that captures the complexities of the price-feature relationship. AdaBoost and gradient boosting are very similar to each other, but compared to AdaBoost, which starts the process by selecting a stump and continuing to build it by using the weak learners from the previous stump, gradient boosting starts with a single leaf instead of a tree of a stump. The outcome corresponding to this chosen leaf is then an initial guess for the outcome variable. Like in the case of AdaBoost, gradient boosting uses the previous stump's errors to build a tree, but unlike in AdaBoost, the trees that gradient boost builds are larger than a stump. That's a parameter where we set a max number of leaves. To make sure the tree is not overfitting, gradient boosting uses the learning rate to scale the gradient contributions. Gradient boosting is based on the idea that taking lots of small steps in the right direction, gradients, will result in lower variance for testing data. The major difference between the AdaBoost and gradient boosting algorithms is how the two identify the shortcomings of weak learners, for example, decision trees. While the AdaBoost model identifies the shortcomings by using high-weight data points, gradient boosting performs the same by using gradients in the loss function, where x was precise a. E needs a special mention as it is the error term. The loss function is a measure indicating how good a model's coefficients are at fitting the underlying data. A logical understanding of loss function would depend on what we are trying to optimize. Early stopping. The special process of tuning the number of iterations for an algorithm, such as GBM and random forest, is called early stopping, a phenomenon we touched upon when discussing the decision trees. Early stopping performs model optimization by monitoring the model's performance on a separate test data set and stopping the training procedure once the performance on the test data stops improving beyond a certain number of iterations. It avoids overfitting by attempting to automatically select the inflection point where performance on the test dataset starts to decrease, while performance on the training dataset continues to improve as the model starts to overfit. In the context of GBM, early stopping can be based either on an out-of-bag sample set, OOB, or cross-validation, CV. Like mentioned earlier, the ideal time to stop training the model is when the validation error has decreased and started to stabilize before it starts increasing due to overfitting. To build GBM, follow this step-by-step process. Step 1. Train the model on the existing data to predict the outcome variable. Step 2. Compute the error rate using the predictions and the real values. Pseudo-residual. Step 3. Use the existing features and the pseudo-residual as the outcome variable to predict the residuals again. Step 4. Use the predicted residuals to update the predictions from step 1 while scaling this contribution to the tree with a learning rate hyperparameter. Step 5. Repeat steps 1 to 4, the process of updating the pseudo-residuals and the tree while scaling with the learning rate to move slowly in the right direction until there is no longer an improvement or we come to our stopping rule. The idea is that each time we add a new scaled tree to the model, the residuals should get smaller. Let's break down the provided code step by step. Model initialization and training. The code initializes a gradient boosting regressor model, model GBM, with specific parameters such as the number of estimators, trees set to 100, learning rate set to 0.1, maximum depth of each tree set to 1, and a random seed for reproducibility. This model is then trained using the training data X.train and Y.train. Gradient boosting builds an ensemble of weak learners, decision trees in this case, sequentially, with each tree learning from the errors made by the previous ones. Predictions. After training, the model is used to make predictions on the test data X-test. The predict method is applied to model GBM, and the predicted house prices are stored in the variable predictions. Model evaluation. To assess the model's performance, the mean squared error, MSE, and root, mean squared error, RMSE, metrics are calculated. These metrics quantify the average square difference between the actual house prices, YY test, and the predicted prices, predictions. Lower values indicate better model performance. The calculated MSE and RMSE are then printed to the console using formatted strings. Result visualization. Finally, the code generates a scatter plot to visualize the relationship between the actual house prices, Y-test, and the predicted prices, predictions. The scatter plot displays the actual prices on the x-axis and the predicted prices on the y-axis. Additionally, a diagonal dashed line is drawn to represent perfect predictions, where actual prices equal predicted prices. This visualization helps in assessing how closely the model's predictions align with the actual prices, providing insights into the model's accuracy and potential areas for improvement. Now, if we compare this result with the result that we got before with AdaBoost, we can say the following. Scatter plot. Characteristics. Both plots follow a similar structure with predicted prices on the y-axis and actual prices on the x-axis. Points represent individual predictions, with ideal predictions lying on a dashed diagonal line indicating where predicted prices equal actual prices. Performance indication. AdaBoost. The points are spread around the diagonal but show a trend of underestimating higher values, as seen from the concentration of points below the line as actual prices increase. GBM. The points are more tightly clustered around the diagonal line throughout the range of values, suggesting that GBM predicts both low and high prices with better accuracy than AdaBoost. Algorithm effectiveness. The GBM model generally appears to perform better, given the closer clustering of points around the identity line. This indicates a more accurate prediction across the range of house prices. The AdaBoost plot shows greater deviation from the line, especially at higher price points, suggesting less consistency in prediction accuracy across the price spectrum. Data distribution. Both models handle the full range of data from about 150 to 500 in units consistent across both models, but the GBM seems to manage the upper range more effectively. Overall, from these plots, we can infer that GBM provides a more accurate and consistent prediction for house prices compared to AdaBoost, particularly at higher price points where AdaBoost tends to underestimate values. One of the most popular boosting or ensemble algorithms is extreme gradient boosting, XGBoost. The difference between the GBM and XGBoost is that in the case of XGBoost, the second-order derivatives are calculated second-order gradients. This provides more information about the direction of gradients and how to get to the minimum of the loss function. Remember that this is needed to identify the weak learner and improve the model by improving the weak learners. The idea behind XGBoost is that the second-order derivative tends to be more precise in terms of finding the accurate direction. Like the AdaBoost, XGBoost applies advanced regularization in the form of L1 or L2 norms to address overfitting. Unlike AdaBoost, XGBoost is parallelizable due to its special caching mechanism, making it convenient to handle large and complex data sets. Also, to speed up the training, XGBoost uses an approximate greedy algorithm to consider only a limited amount of thresholds for splitting the nodes of the trees. To build an XGBoost model, follow this step-by-step process. Step 1. Fit a single decision tree. In this step, the loss function is calculated, for example NDCG, to evaluate the model. Step 2. Add the second tree. This is done such that when this second tree is added to the model, it lowers the loss function based on first and second order derivatives compared to the previous tree, where we also used learning rate ATA. Step 3. Finding the direction of the next move. Using the first degree and second degree derivatives, we can find the direction in which the loss function decreases the largest. This is basically the gradient of the loss function with regard to the output of the previous model. Step 4. Splitting the nodes. To split the observations, XGBoost uses an approximate greedy algorithm, about 3 approximate weighted quantiles usually, quantiles that have a similar sum of weights. For finding the split value of the nodes, it doesn't consider all the candidate thresholds, but instead it uses the quantiles of that predictor only. Optimal learning rate can be determined by using cross-validation and grid search. Imagine you have a dataset containing information about various houses and their prices. The dataset includes features like the number of bedrooms, bathrooms, the total area, the year built, and so on. And you want to predict the price of a house based on these features. Let's dissect the provided code step by step. Model initialization and training. The code starts by importing the XGBoost library. Import XGBoost as XGB. XGBoost is a powerful implementation of gradient boosting machines. Next, an XGBoost regressor model XGB, is initialized with specific parameters. The objective is set to Reggie squared error, indicating that the model aims to minimize the mean squared error loss function. Additionally, the number of estimators, trees, is set to 100, and a seed value of 42 is specified for reproducibility. The initialized model is then trained using the training data XXCtrain and YTtrain. XGBoost builds an ensemble of decision trees sequentially, optimizing a specified loss function. Predictions. After training, the trained model JOX XGB is used to make predictions on the test data XTOS test. The predict method is applied to the model, and the predicted house prices are stored in the variable predictions. Model evaluation. The code proceeds to evaluate the model's performance using two common metrics: mean squared error, MSE, and root mean squared error, RMSE. These metrics quantify the average squared difference between the actual house prices, y-cost test, and the predicted prices predictions. Lower values indicate better model performance. The calculated MSE and RMSE are then printed to the console using formatted strings. Result visualization. Lastly, the code generates a scatter plot to visually compare the actual house prices y-test with the predicted prices predictions. The scatter plot displays the actual prices on the x-axis and the predicted prices on the y-axis. Additionally, a diagonal dashed line is drawn to represent perfect predictions where actual prices equal predicted prices. This visualization aids in assessing the model's accuracy by examining how closely the predicted prices align with the actual prices, providing insights into the model's performance. Now, let's compare AdaBoost, GBM, XGBoost. Here's how they compare. AdaBoost. The AdaBoost plot shows predictions that tend to underestimate the actual prices, especially as the values increase. This is evident from the larger number of points lying below the diagonal line in the higher price ranges. The overall fit to the diagonal is less tight, suggesting higher prediction errors or bias, particularly for higher priced houses. GBM. The GBM model produces predictions that are generally closer to the diagonal across all price ranges. This indicates better accuracy and consistency in predicting both lower and higher priced houses compared to AdaBoost. The points in the GBM plot are more tightly clustered around the diagonal, indicating lower variance in prediction errors. XGBoost. The XGBoost plot also shows a tight clustering of points around the diagonal, similar to GBM. This suggests a high level of accuracy. Unlike GBM, the XGBoost plot seems to slightly overestimate the lowest priced houses while matching or slightly underestimating the highest priced houses, but still maintains a close adherence to the diagonal line. Summary of comparison: accuracy and consistency. Both GBM and XGBoost exhibit high accuracy with their predictions closely clustered around the diagonal line, showing their effectiveness in both lower and higher price predictions. AdaBoost, however, shows more variance and a tendency to underestimate, particularly at higher price points. Performance at different price ranges. GBM and XGBoost handle extremes in prices better than AdaBoost, which struggles with underestimation as prices increase. General predictive performance. XGBoost and GBM are quite comparable, with slight differences in how they handle the very low and very high ends of the price spectrum. AdaBoost appears to be less reliable, especially for higher priced properties. From these observations, GBM and XGBoost seem more suitable for scenarios where precise and consistent predictions across a wide range of house prices are critical. AdaBoost might be more prone to prediction errors, particularly in higher price brackets.
Hi, I'm Vahe, and in this project, we will learn how to understand your customers better, track sales patterns, and show those results. If you like working with data or own a store, this video will show you how to use the information to make better choices and get better results. You will split your customers into smaller groups based on how they shop. This helps you send the right messages to the right people and give them offers they will like. Loyal customers are the best. You will use data to find your biggest supporters and those who are ready to spend more. Then you can reward your best customers with programs that fit their shopping habits. This makes them happy and stops them from going to other stores. We will use data to guess what people will buy and when they will buy it. We will find sales patterns among different items and figure out what cool new products people will want. This lets you always have the right stuff at the right time. You won't have too many items, everything will sell, and customers will be surprised by how well you know what they need. we will look at how sales change throughout the year. This helps you plan for busy times, catch slowdowns early, and know exactly when to have big sales. We will use location data and what people say about you to find places where sales are going well and where you could grow. We will even show it all on the map. This helps you spend your advertising money wisely, find great spots for new stores, and even choose the perfect things to sell in each place. So, let's get started. Alright, let's now go over the data set we'll be using. So, we are using the Superstore sales data set, and it has 9,800 rows, and the columns: order ID, order date, ship date, shipping mode, standard class, second class, or other classes, and the customer ID with them, customer name, the segment, meaning who bought the product, whether the consumer, a corporate, or a home office, and the clients mainly come from the United States, and it's also specified from which city of the United States they come from. So we shall import this to our Google Colab and start working on it. Okay, so let's now import the necessary Python libraries. We'll import pandas as PD. We'll also import NumPy as MP, import matplotlib pyfile, we import seaborn as SNS. So let's also import the data frame we'll be using. Copy path. Perfect. So this is how it looked like on Kaggle, and this is also how it looked like when we have imported. So let's now look up the data frames to the larger info. So everything seems to be consistent but the postal code. It seems that 11 postal codes are missing. Okay, so what we can do is to fill in those null values. Okay, so as you can see, we have replaced the no postal codes, customers that didn't have any postal code, and we have put a 0 inside it. All right, so let's now move on to checking for duplicates. If df.duplicated.sum bigger than 0 dash print. So let's now see if there are actually duplicates, and if there are duplicates, we will print duplicates exist, and if there are not, we'll print null duplicates found. Alright, so as you can see, there exists no duplicate. So let's move on to customer segmentation. Let's first create a variable named types of customers, and let's extract out of our data frame called segment. As you can see from our data frame, we have a married segment within our data. This segment includes a list of the types of customers in our data frame. We have both consumer and corporate customers. So let's get started with customer segmentation. The main problem is that many large businesses struggle to understand the contribution and importance of their various customer segments. They often lack precise information about their main buyers, relying on intuition rather than data. This leads to misallocation of resources, resulting in revenue loss and decreased customer satisfaction. For example, if your store primarily caters to consumers, it's crucial to tailor your marketing and customer satisfaction efforts to resonate with their needs and preferences. By focusing your resources on understanding and catering to your consumer base, you can avoid misallocating resources to large corporates. This ensures you're providing a satisfying customer experience for your primary demographic, ultimately leading to increased customer loyalty and revenue growth. And you can create a pie chart or bar graph from it to clearly illustrate the revenue contribution of each customer segment. And this will allow us to tailor more of our marketing resources, our customer satisfaction resources towards. Once you've completed customer segmentation, the next step depends on your strategic goals. Here are a few ways to proceed. Focus on your most valuable segment. If your existing customer segmentation reveals a particularly profitable segment, such as consumers, tailor your marketing, product offerings, and customer service to deepen your engagement with that group. Target new segments. If you want to attract more corporates or home offices, you'll need to understand their unique needs and pain points. Start by researching these segments. What are their challenges? What solutions would appeal to them? Develop tailored messaging and consider offering specialized products or services to attract these new customer types.
All right, so let's get started. So this will extract the types of customers from our data frame. Perfect. So it's consumer, corporate, and home office. Those are all the variables that are in our data frame. All right. So let's count the unique values in our segment, and we'll do this by number of customers. So what this meaning does is it counts unique values in our segment and resets the index to turn them into a column. And then we can correct the renaming of columns. So we want to give our segment the name as like total customer or type of customer. I will go with the type of customer. So we will say number of customers is equal to number of customers that I'll rename, and want to call the column, which is the name segment. We want to rename it to type of customer. And now if you want to print that, print number of customers. There are 5,101 consumers, and for corporates there are like 2,953 corporate buyers, and 1,746 home offices. And if we want to create a pie chart out of this, we can plot it by saying plot.pie, number of customers, and want to base a pie chart on the count, and want to label number of customers, total customers. Perfect. All right, so as you can see, we had to rename it type of customer, total customer. So you can see that from this pie chart, our main consumer segment is 52%. 30% of our orders come from corporates and 18% from home offices. You can see who we have to exactly focus on, which are consumers.
While consumers hold the majority, focusing solely on them overlooks significant potential within the corporate and home office segments. Let's explore how to balance resource allocation for all three segments to maximize growth. To gain even deeper insights, we should integrate our customer data with sales figures. This analysis will help us identify which segments generate the most revenue per customer, average order value, and overall profitability, customer lifetime value. Additionally, we can segment customers by purchase frequency and basket size to understand their buying behavior within each segment. Here are some additional questions to consider for a more comprehensive analysis. Customer acquisition cost, CAC. How much does it cost to acquire a customer in each segment? Customer satisfaction. How satisfied are customers in each segment? Churn rate. What is the rate at which customers leave in each segment? By analyzing these factors alongside revenue and customer lifetime value, we can create a customer segmentation model that prioritizes segments based on their overall value and growth potential.
We can also plot a bar graph for the total sales for each customer type and group the data by the segment column and calculate the total sales for each segment. And you want to do this so right now you don't see the exact sales numbers. The bar chart, you can see the exact sales numbers for each customer type. So let's plot it. So there are around 1.2 million from our consumers, and we have around 600 or 700,000 from our corporates. We can also plot a bar graph from this, which means plotted bar sales per segment, customer type of customer, sales per segment, total sales.
This bar chart effectively illustrates the distribution of sales across our customer segments. Consumers account for the largest portion of sales, 1.2 million, followed by corporates, 1.0 million, and home offices, 0.8 million. While the chart is clear, a deeper analysis can help us optimize our marketing efforts. Customer lifetime value, CLTV. Calculate the CLTV of each segment to identify which segments generate the most revenue over time. This will help prioritize customer segments for marketing efforts. For example, if you find that the home office segment has a higher CLTV than the consumer segment, you may want to invest more resources in marketing campaigns targeting home office customers, market research, conduct market research to understand the specific needs and preferences of each customer segment. This will inform the development of targeted marketing campaigns. For instance, you might discover that consumers in your data are price sensitive, while corporate customers are more interested in bulk discounts and reliable service. You can use this knowledge to tailor your marketing messages to each segment. Average order value. Analyze average order value by segment to identify opportunities to increase revenue per customer. Let's say your analysis reveals that corporate customers have a higher average order value than consumers. You could develop marketing campaigns that encourage consumers to purchase bundles or higher priced products to increase their average order value. Customer acquisition cost, CAC. How much does it cost to acquire a customer in each segment? Knowing CAC can help determine the return on investment, ROI, for marketing efforts. Here's an example. Let's say it costs $100 to acquire a new corporate customer, but only $20 to acquire a new consumer customer. If the CLTV, customer lifetime value, of a corporate customer is significantly higher than the CLTV of a consumer customer, then spending $100 to acquire a corporate customer may still be profitable. However, if the CLTV of the corporate customer is only slightly higher than the CLTV of the consumer customer, you may want to focus your marketing efforts on acquiring more consumers because the cost of acquisition is much lower. Customer satisfaction. How satisfied are customers in each segment? Understanding satisfaction levels can help identify areas for improvement and reduce churn. Here's an example. You can conduct surveys or collect customer feedback to understand satisfaction levels. If you find that corporate customers are less satisfied than consumer customers, you may want to investigate the reasons for their dissatisfaction and make changes to improve their experience. This could involve improving your customer service, offering more competitive pricing for corporate customers, or developing products or services that better meet the needs of corporate customers.
We can also create a pie chart for our sales, which you can do by call it pie, sales, per segment, total sales, and we name it labels is equal to sales per segment, type of customer. 51% of our sales come from our consumers, 30% from our corporates, and 19% from home offices. Alright, so let's now move on to the customer loyalty. As a business, you want to make sure that your most loyal customers stay happy. This will make sure that those customers keep on coming back, keep on bringing new people, and also placing new orders. So you will decrease the cost on acquisition of new customers because there will be already existing customers. And you'll also be able to make sure that your revenue either stays at the same level or increases by keeping your most loyal customers happy. And you want to do that as a business. Now, we can do this by either the following ways. We can rank the most loyal customers by the amount of orders they have placed or the total they have spent. You have analyzed your data, pinpointing your 30 most loyal customers. This represents a significant opportunity to strengthen these relationships and maximize their lifetime value. Here is a powerful approach. Design a targeted email specifically for those high-value segments. Proactively offer personalized support with inquiries such as, "How can we assist you today?" This demonstrates your commitment to their success, proactively addressing potential issues
and fostering a deep sense of loyalty. Loyalty programs. Consider a tiered loyalty program that offers exclusive rewards tailored to your most valuable customers. This includes earlier access to new products, personalized discounts, or even point-based reward systems, personalized experiences. Leverage your data insights to go beyond email. Consider personalized website recommendations, targeted promotions based on past purchase history, or even handwritten thank you notes for high-value customers. Customer feedback loops. Make sure your top customers feel heard. Implement surveys or invite them to participate in exclusive focus groups. This demonstrates you value their input and are actively using feedback to improve the customer experience. Community building. Depending on your business model, fostering a community among your most loyal customers can create a sense of belonging. This could involve access to online forums, exclusive events, or opportunities to network with like-minded individuals. Now, this strategy extends beyond customer satisfaction. Prioritizing the experience of your top customers directly correlates with increased retention, positive referrals, and ultimately improved revenue. Now, let's dive deeper and see who are our most loyal customers. Alright, so let's now get started with that. Let's create a variable with a name. So let's first display the first 3 rows of our data frame. So as you can see, there is a row called sales, or the column called sales, and each customer has a specific ID with a specific name. So if you can count up the number of times this shows up, then you also have the number of total orders, which then you can use later however you want to. So let's start with doing that. Now let's rename the columns. We want the column order ID, which is, where is the order ID? Oh, it's right here. We want the order ID to be named total orders. Now we want to rename the columns that are equal to order ID. In this column, this must be renamed to total orders. Place is equal to true. Okay, so now let's identify the repeat customers. Customers with order frequency greater than 1. So repeat customers are equal to customers order frequency, total orders. And like I said, we want to make sure it's greater than 1. It's equal or greater than 1. Perfect. Now we want to organize this in a way that is descending. We can do that by saying repeat customer sorted are repeat customers that sort values.
Perfect. Now let's print this out. Print, repeat, customers, sorted.add 12. We want to display our top 12 customers. Reset index. So the customer with name William Brown, who is a consumer, has placed a total of 35 orders. So this is the list of your top how many customers, and as a business or as a Superstore, you can identify exactly the number of the total orders a person or a business has to place in order to be considered a loyal customer. And then according to that, you can tailor your services to it. Now, the data clearly reveals that a small group of customers place orders with considerably higher frequency, 30 plus. We have William Brown with 35 orders, and other home office customers with 34, and many consumers and one corporate with 32. So it shows clearly that we have a loyal group of customers. There is also significant potential for our home office segment. Several of our most loyal customers belong to the home office segment. Now, this implies that the home office segment has a strong potential for customers' loyalty and deserves targeted marketing efforts. It also shows that we just don't have one dominant group of loyal customers. We have home offices, consumers, and corporates. While there are many consumers, it doesn't mean that we have to focus on one segment. It means that we still have to devise a plan that caters to our multiple segments. So some recommendations. We can prioritize loyal customers, segment customers by order frequency, and we can develop exclusive offers, rewards, or early access programs tailored to our most loyal customers. So, for example, we can provide them exclusive discounts, tier reward programs, and earlier access. And we can also target more home offices, because we see that home offices keep on coming back, and we are able to satisfy few of the home offices. That means we have catered to their needs and provided a good enough service for them to keep on coming back. That means our product is great for home offices. That means we can target more home offices using content marketing, social media ads, or other type of marketing strategies. And we can also analyze the behavior with the way we provide service to these customers. And because it worked out pretty well, and if we provide this kind of service to our new coming customers, then we increase the chance that they also become a loyal customer. So those are several conclusions we can make. Now we can also identify loyal customers by sales. So this is identify them by total number of orders they have placed, but we can also use amount of sales, so the total amount, to identify them, because a person can come and place 35 orders, but if they place 35 $1 order, then obviously that's just $35. Now, this doesn't say anything about the sales amount. So ideally, you want to organize it by the sales amount to be able to identify the actual top spending and loyal customers. Or that said, when there is a significant customer, so let's say someone has spent $25,000, that can be done also in one order. So that doesn't mean that it's a repeated customer. It's just a top spender. Now, let's start with identifying our top spending customers. So let's first create a variable customer sales, go to data frame, that group by customer ID. We want their customer ID. We want to also see the name and also what type of customer they are, the segment. And we want to do it by sales, and we want to sum those all. And we then want to reset the index. And now let's identify our top spenders by having them ranked descendingly, meaning our top spenders will be ranked all the way up. Customer sales dot sort and values by equal So Sean Miller has spent the most, who is from home office, using total amount of $25,000 USD. William Brown has placed the most number of orders, which are 35, but William Brown is nowhere to be found here. The same as Sean Miller. He's a customer who has spent the most in our Superstore, but he's also nowhere to be found here. Meaning that the repeated customers doesn't really define their spending habits. So depending on the way you run your Superstore, obviously I would want our customer to come back, but I would dedicate my resources to the customers who spend the most, because those are the customers who bring the most business to me, meaning those are the customers I have to keep happy. So the total number of orders is great, but it doesn't really speak that much about their spending habits and about their value to your store. All right, let's now go over to the next chapter, which is shipping. Now, as a Superstore, you will also want to know what shipping methods customers prefer and which are the most cost-effective and reliable. And overall, knowing this impacts your customer satisfaction, and also meaning it also has a great impact on your revenue. So for example, Amazon has multiple shipping methods, but it has the most popular shipping method, which keeps the most amount of customers happy, and it also makes Amazon the most amount of money. So as a Superstore, you want to know which one of your shipping methods is the most reliable. We create the variable type of customers. So our shipping model, let's create a variable. We use the data of the data frame ship mode. We want to count those values, and of course we want to reset the index. So our standard class is the most popular it's almost like 4 times more popular. Our first class is the least, and the same day our first class is one of the least. So let's create a pie chart of this. Plotted pie shipping model. All right, so this is our class, standard class, or these are like the shipping methods. The most popular one is standard class, which is 60% of the orders use standard class shipping, and rest is like 40%. So as a Superstore or as any store, you invest in your shipping. So you end up buying some kind of deals with delivery companies like DHL, UPS, and others. And sometimes you end up recommending the wrong option to your customer. So let's say second class is fast, but it ends up costing the customer way too much. The customer ends up not buying your product, and this decreases as you can see, this hurts your store. But if you know that standard class is the most popular option, then you can have like a button saying this is our most popular option, which is standard class, and most of the time people will choose the most popular option. So this will help the Superstore save the cost of investment into these others, or dedicate the amount of resources that each class brings. And it also allows the Superstore to recommend its most popular option, which is standard class. So the problem that many superstores have, because many stores have stores in many locations, in many states, but they don't know how well each is performing. On a dashboard, for example, you could have that, but they have no idea how well each of the stores in each state are performing, and leaving them with clueless where there is an underperformance, or for example, where there is a high potential area in which they can open a new store in. So let's move on to this chapter, which is geographical analysis. So many stores have hard time in identifying high potential areas, or also identifying stores that are underperforming. So things like Walmart, Target, they have like many branches, and they will want to know how well each branch is doing. And the perfect way to do this is by counting up the number of sales for each city, the number of sales for each state, and then this will allow you to see which of the states or which of the cities is performing the best and which of them is performing the least, and dedicate your resources accordingly. So let's say if one city, the store is simply just losing money for years or for more, then you will want to adjust your strategy according to that. So maybe you will want to close the store or adjust it in a way so it starts bringing in more profit or revenue. Well, so let's get started with that. Alright, so as you can see, the most popular state is California and the least popular is New Jersey. So maybe you can go over this, and let's say in a few of these states where there is still high potential for a profitable store, you can identify, let's say in Washington, and calculate. Alright, so maybe from this you can see that Washington is performing fourth, or New Jersey is performing like the least of our top 20. From this you can conclude that you might have to work on New Jersey more to increase the order count. This also allows you to increase the revenue. Or you can see that the California is your most popular option, so you might want to keep California happy. And you can also do it per city. So city TF, city value counts, reset, next, print city that had the most top 15. So the most popular city is New York with the order count of 891, and then Los Angeles and Jackson is the least popular out of our top 15, and you can also increase this to the 25. So not only can you focus on the states, but for each state you can also focus on the city that's underperforming or overperforming. So this allows you to also dedicate your resources to the city that you want, maybe to increase your revenue or increase your potential. Or maybe there is like a city, for example, Long Beach, where there's high potential, but you are not using any of your resources. Now we can also
organize the sales per state. Let's say state sales. So previously we did it by order count, and we can also do it for state sales. We want to sum it up and then reset the index. We want to rank it according to all. Perfect. So as you can see, our most popular state is California, and then New York, and then it changes it, and then it doesn't change yet, Texas. So this is according to the sales amount, the popularity of the state according to the sales amount. And let's also sort it for her city. So most popular city is New York, LA, Seattle, San Francisco. So this is exactly the same as our previous analysis on the city. Nothing really has changed. Alright, so as a store, you want to be able to track down your most popular category of products, or your best-selling products, or sales performance across categories and subcategories, and find the sweet spots where strong categories also have top-selling subcategories, and also spot weaker subcategories within otherwise strong categories that might need improvement, or product popularity fluctuations. See if popularity is seasonal, trending up and down, and this helps to forecast the future demand. Or you can group it by location. For each location, there might be a different popular product you want to put it in a certain place to maximize your store's revenue. So let's get started with finding our top performing products or their categories. So let's first extract our products, the categories of our products from our data frame, that unique print product. So right now in our data frame, we have only 3 sorts of products. As you can see, the category, and each one has a subcategory, bookcases, chairs. But we have mainly 3 categories, which are furniture, office supplies, and technology. So let's go now over to the types of subcategory. Our product subcategory, the print product subcategory, bookcases, chairs, table, and bunch of it. Now, let's group the data by a product category and how many subcategory it has. So we want to say, for example, office supplies may have like 20 subcategories, or furniture may have 5 subcategories. So let's see how many subcategories each one has.
So there are nine first office supplies, four for furniture, four for technology. So office supplies is much more sophisticated category. Now we can also see our top performing subcategory. So let's say subcategory when you want to count the sales, we go by category. So our most popular subcategory is tech, specifically phones. It has the most amount of sales, furniture, chairs, office supplies, storage. So from this you can see our most popular subcategories and what subcategories you want to recommend them on a front page or in the store. Now let's see which one of our main categories performs or has the most amount of sales. Product category, go by. So as expected, tech is the most popular one, and then furniture and office supplies. So maybe you will have inside your store, you will have a much larger department, or not much larger, maybe a little bit larger, or maybe it's in the first row, right in front of the customers, to be able to present your most popular option immediately to your customers. Now this will allow you to, of course, increase your revenue and sales. If you want to create a pie chart for this, you can say product pie, top product category. I can organize it by sales, labels, top product category. There's already, well, it seems that tech is performing a little bit better than most, or like these two, but it's not that much different. It's not really that different. Alright, so let's now see which one of our subcategories is the most popular one. Now remember that we saw which one of our subcategories had the most amount of sales. Now let's create a bar graph out of it. We can do this by ascending false, insert the value by sales, ascending is true. And let's create a bar graph out of it. Solid bar, subcategory count sales is some category, top product subcategory, this sales. And let's pull it and summary sign find. Now this shows perfectly that our most popular option is phone and chairs. And so since this generate the most amount of sales, that means that customers are more willing to pay money for this. So you can end up spending more of your marketing resources on phones and chairs, because there is already shown that because of the amount of resources you have provided for phones and chairs, it already works. Meaning if you increase the amount of resources you spend for phones and chairs, then your sales will also increase accordingly. You can also conclude that art, envelopes, and labels aren't that popular. So maybe right now you can give a discount and get rid of those and buy less of those for the future. So you can end up buying more of the popular options, for example, phones, chairs. Or you can also investigate why they are not popular. Maybe those are like the worst envelopes you could have bought, or maybe it's not the right art you have bought. Maybe those kind of art people don't like, but if you were to choose complete other form of art, maybe customers will end up buying them. So this shows exactly how this data stores can use to optimize the sales or optimize how their resources are allocated. So you would end up making more money or more sales. Businesses love making sales. They love seeing revenue increase and profits increase. It's all lovely, but you should be able to track down your sales so that you can see in what kind of situation you are and you can adjust to that situation. And what is a better way than having a pie chart or a bar graph or just a normal graph to see how much growth or how much decline you're experiencing. For example, if you are a business and there's a declining revenue, then year over year or month over month, then you can see that there is a problem. And then you can also allocate your resources towards fixing that problem, whether that is investing more in customer preferences or investing more money into marketing or into resources that make your customers more satisfied or adapting new technologies. Those are all things that you can do whenever you see a declining revenue, but first you must be able to see it coming. And also businesses have a problem with stagnant growth. So they may grow 1 month and the next month there's like no growth or maybe there's a decline. So you want to see that as a business to be able to stabilize the growth. So continuously grow as a business. Or missed season opportunities. If a business isn't aware of how sales changes throughout the year, they could miss out on maximizing profits during peak seasons. Maybe on some seasons there's a certain product that's high in demand, but you don't have enough stock to cover it, so you end up not being able to meet the demand and losing out on revenue and profits. And those were regarding our yearly sales trends. And there's also a problem with quarterly and monthly sales. So for example, cash flow issues. Now many businesses experience cash flow issues. So that maybe one day they look at their bank and see that they are out of money and they cannot invest more in their business. Or there's also inventory imbalance or ineffective marketing. So for example, whenever you have a cash flow issue, drastic dips in sales during specific quarters or months can lead to cash crunches, making it hard to pay suppliers, employees, or ongoing expenses. Or whenever you have inventory imbalance, some periods you're overstocked and those items you have to give away. In some periods you're understocked, you are not able to meet the demand. Or maybe your marketing is ineffective. So if you spend significant amount of time in marketing and you don't reach your desired outcome, that means there's a major issue with your marketing campaign. And then you can see that from the sales you're making. So for example, if you're spending this amount of money with marketing or increased amount of marketing and there's no significant increase of sales, that means you're doing something wrong with your marketing campaign or lagging response to emerging trends. So monthly sales data can highlight new trends or drops in demand more quickly than just yearly overviews. So you can react much faster to emerging trends. For example, a certain product was released 2024 and all of a sudden it's high in demand in many countries. Then you want to be able to adjust to that demand and get the supplies for the product. But you are not able to do that if you track yearly sales or don't do any tracking at all. So those are all the problems that exist if you are not able to track down your sales, be it monthly, quarterly, or yearly. And so we are intending to solve that problem by graphing it and concluding from the results we get from our graphs. Alright, so let's get started. Now let's convert the order date column to a data frame format. The order date is equal to pd.to datetime df, order date, day first is equal to the true. Now let's group the data by years and calculate the total sales amount for each year. We can do it by yearly sales, creating the variable first, and then group by df, order date, the year sales, let's sum yearly sales is equal to yearly sales. Let's reset the index. Now I want to give the appropriate colors the appropriate name, because right now in the data frame it's not. The order date should be named year, and sales should be named total sales. Now let's print this out. So this is the amount of sales for each year in total, and we can also, let's plot the bar graph out of this. Plot the bar, yearly sales, year, yearly sales, total sales. Alright, so from this bar graph, there can be a few conclusions made. For example, there's a steady growth from 2016 to 2018 that might explain, for example, new product launches, that they are effective, or economic factors, or marketing efforts. Those are all the explanations that a person can make, but you can make these conclusions only when you have the larger data available to you. And in this data frame, we don't have the marketing costs or any other costs involved regarding this. So our conclusions are pretty limited, but what we can see is that this bar graph combined with any other bar graph, for example, marketing costs, you can make a pretty good amount of conclusions from that as a business. Now, how about totals? We can also plot this using just a normal graph, which means I will just copy it, or no, I won't. Just plot it, yearly sales, year, total sales. So this shows a little bit different. Now, I prefer this sort of graph instead of a bar graph for tracking the yearly sales, because it shows much more clearer the amount of increase with the amount of decrease. We can also focus on the quarterly sales, like I said, to be able to react to emerging trends, or to react fast to be able to react fast to any kind of change. Now let's again convert the order date to a date format, order date. From our quarterly sales, we can see that there is a steady increase of quarterly sales, and all of a sudden, July it blows up to new heights. So from this graph, we can see exactly that Q3 and Q4 did very well, and Q1 and Q2 didn't. So something might have changed. For example, a seasonal trend, or you have increased your marketing, or you have introduced a new product, or you have targeted a specific customer segment. And as a business, it's really important to know that. So you can also expect that if you follow a similar line of actions, then you might have higher demand for your products on Q3 and Q4. So you might want to overstock it. Or maybe you can analyze this further and replicate these successful strategies for future quarters. And this will make sure that a business can steadily grow and increase its revenue, which is good. And also for Q1, you can see that it starts out with pretty slow. I mean, businesses may want to start out the year more quickly, so they can investigate also. For example, is this a seasonal for the industry? Maybe on certain seasons, a certain product is not high in demand, or maybe a competitor did some kind of marketing or use some kind of a strategy to drive more customers to them. Or maybe we have changed marketing effort in our Q3, and our marketing efforts were not productive for Q1 and Q2. So maybe that's it. All right, so maybe you want to investigate this much more deeply. So not quarterly, but monthly. So let's do it now. Let's start off the same way. Call the order date column to the data time format. DF, order date, periods to daytime. All right, so from this graph, you can see that it's growing month over month beside first month of 2019 and also the third month of 2018. So this is generally an upward trend, which might suggest like a healthy sales are going on. And it looks like August and December might be your seasonal, so you might want to overstock the products there. And okay, you can also see that there are seasonal dips in third month of 2018 and also 2019 in November of 2018. So you might want to consider like seasonal promotions to stimulate off-season sales, or diversify your product service offerings to reduce the reliance on seasonal demand. And maybe you want to start deploying new marketing strategies here, or try to target new customer segments by introducing new products so that you might offset the seasonal trends. And overall, it seems pretty consistent. So it looks like that there's a healthy sales trend, so you might want to invest more in your proven strategies, which might be, for example, a certain marketing tactic, promotion, or product offering for a certain month. And like I said, for the dips, the store might try to deploy new marketing strategies or introduce new products to target new customer segments, which might offset the dip. And that said, it's important to consider the longer time frame. A year certainly has great amount of data, but it does not really accurately reveal seasonal patterns, because for 1 year that might be the case, but for another year it might just be completely the opposite. So you might want to consider a larger sales line graph, for example, maybe for 5 years, and then you can see if that's the case. And if that's the case, then this might suggest a seasonal trend. And if not, then you will act accordingly. All right, so we have covered the sales trends. We can move on to the next chapter, which is... All right, let's move on to the next chapter, which is mapping. So we want to create a map out of sales per state. So for each state, we want to color it according to the amount of sales. So if there is a high amount of sales, then it should be colored yellow. And if there is low amount of sales, then it should be colored blue. So the question is, why would someone want to do this? Now, companies looking to expand into new geographic areas face the challenge of identifying the most promising states and regions for their products or services. Now, for example, how do you know if your product will sell in a certain state? So one of the tactics that people often use is by seeing if there is a similar store like them operating in that state or in that city. And so if there is a similar store working there, and it's not a saturated market, meaning there are still plenty of amount of people who might buy your product, then it's a good idea to go there. For example, a company that manufactures athletic apparel is considering expanding its retail footprint. By analyzing total sales data by US state, they can see that states with a high concentration of fitness centers and active population, like for example California, Texas, or Florida, might be good candidates for new stores. And if there are currently no sports stores there, then it's even better. Or for example, if you're a business and you want to strategically allocate your market budget and sales team, and so you have stores all over the states, you want to optimize it for each state. Maybe one state is performing well and another state is not performing. So you might then, from the map, you might see which state is not performing well and allocate your resources accordingly to be able to maximize your return on investment by optimizing certain strategies. But if you don't know which state is not performing well, then if you don't know which state is performing well, then you have no information on
where you have to optimize. Like, for example, a national pizza chain wants to optimize its marketing spend. Now, sales data reveals that their pizzerias in the Midwest consistently outperform those on the West Coast. Now, this data suggests that they might need to allocate more marketing budget to increase brand awareness and sales in the Western states. And you might also want to do this because of competitor analysis. So staying ahead of the competition means understanding where your competitors are having the most success. Analyzing their sales patterns across states can reveal their geographic strengths and weaknesses. Now, for example, a coffee roasting company notices a competitor coffee brand is experiencing high sales in the Pacific Northwest states. Now, this could indicate the competitor has established a strong partnership with local grocery stores or launched successful marketing campaigns in that region. Now, the company can use this information to target similar grocery stores or develop competitive marketing strategies for the Pacific Northwest. So without further ado, let's get started with it. Now, I will walk you through the code, and instead of writing it, I will just walk you through it. So let's first import the plotly graph function or the library. So we initialize the plotly in our Jupyter notebook, and we also want to create a map for all 50 states, which we do this right here, and add the abbreviation column to the data frame, because right now there is not. We initialize the variable and calculate the amount of sales for each state and group it by state. And this is exactly what we need. And then we add the abbreviation to sum of sales. We do that here. And finally, we plot it. And this is how the map looks like. So the blue area are the ones with low amount of sales. And the yellow area, which California, has high amount of sales. So from this one, we can see which areas main sales come from. And according to it, you can optimize accordingly. So let's say you have a pizza chain or a pizza chain of stores, and you want to see which one of your states is performing the best and which one is performing the poorest. So you want to spend your most energy on optimizing what doesn't work. So from this, you can see California is great, so you can leave it alone. But for example, Texas is not performing that well. So you might allocate more marketing budget or more resources there to start making or to start getting more sales, because in Texas there are still many amount of people who consume pizzerias, but they are not buying. So why is that? And you can also see, so for example, if this is a completely another store, this is like relates to, for example, a retail store for sport goods, and all of these states, they've got a store in. Now from this, you can conclude that California is performing real well. So it's probably not a good idea to go there, since there might be a market situation there. But you can go, for example, to Florida. You might go to Florida and start selling similar sports goods there, because like you see, the market is still new, or the market is still not saturated. Alright, so that was that. So we can also create a bar graph out of it. From this, you can see that most of the total sales by state, California is doing the best, and North Dakota is doing the worst. And of course, now I still remember we previously categorized or showed how large each of our categories are, and we did the same for our subcategories, but we never did it in the same plot. So here we display our main category of products, which are furniture, office supplies, and technology. And for each category, we have subcategories, and based on their size, it's organized based on their size. So chairs, it seems that chairs is the largest or sells the most in our furniture category. Then it goes to tables, and we have then a small amount of bookcases and furnishings. And in our office supplies, you can see that the best storage
product is performing the best, and envelopes and labels are performing the worst. And for our tech category, phones are performing the best, and then machines, accessories, and copies. And from this, you can see that phones is overall the best subcategory. I think it's even larger than chairs. Yeah, a little larger. So this is a much better way to display if you're trying to make an argument, to display the plot. And of course, you can also do it this way. All right, and hope you guys enjoyed this project. I definitely did. And I will see you guys in the next video.
In this part, we are going to talk about a case study in the field of predictive analytics and causal analysis. So we are going to use this simple yet powerful regression technique called linear regression in order to perform causal analysis and predictive analytics. So by causal analysis, I mean that we are going to look into these correlations, causation, and we're trying to figure out what are the features that have an impact on the housing price, on the house value. So what are these features that are describing the house that define and cause the variation in the house prices? The goal of this case study is to practice linear regression model and to get this first feeling of how you can use a machine learning model, a simple machine learning model, in order to perform model training, model evaluation, and also use it for causal analysis, where you are trying to identify features that have a statistically significant impact on your response variable, so on your dependent variable. So here is the step-by-step process that we are going to follow in order to find out what are the features that define the Californian house values. So first, we are going to understand what are the set of independent variables that we have. We're also going to understand what is the response variable that we have. So for our multiple linear regression model, we are going to understand what are these techniques that we need and what are the libraries in Python that we need to load in order to be able to conduct this case study. So first, we are going to load all these libraries and we are going to understand why we need them. Then we are going to conduct data loading and data preprocessing. This is a very important step, and I deliberately didn't want you to skip this and didn't want you to give you the clean data. Because usually in normal, real hands-on data science job, you won't get a clean data. You will get a dirty data, which will contain missing values, which will contain outliers, and those are things that you need to handle before you proceed to the actual and fun part, which is the modeling and the analysis. So therefore, we are going to do missing data analysis. We are going to remove the missing data from our Californian house price data. We are going to conduct outlier detection. So we are going to identify outliers. We are going to learn different techniques that you can use, visualization techniques in Python that you can use in order to identify outliers and then remove them from your data. Then we are going to perform data visualization. So we are going to explore the data and we are going to do different plots to learn more about the data, to learn more about these outliers and different statistical techniques combined with Python. So then we are going to do correlation analysis to identify some problematic features, which is something that I would suggest you to do independent the nature of your case study, to understand what kind of variables you have, what is the relationship between them, and whether you are dealing with some potentially problematic variables. So then we will be moving towards the fun part, which is performing the multiple linear regression in order to perform the causal analysis, which means identifying the features in the Californian house blocks that define the value of the Californian houses. So finally, we will do very quickly another implementation of the same multiple linear regression in order to give you not only one, but two different ways of conducting linear regression. Because linear regression can be used not only for causal analysis, but also as a standalone, common machine learning regression type of model. Therefore, I will also tell you how you can use scikit-learn as a second way of training and then predicting the Californian house values. So without further ado, let's get started. Once you become a data scientist or machine learning researcher or machine learning engineer, there will be some cases, some hands-on data science projects where the business will come to you and will tell you, well, here we have this data, and we want to understand what are these features that have the biggest influence on this other factor. So in this specific case, in our case study, let's assume we have a client that is interested in identifying what are the features that define the house price. So maybe it's someone who wants to invest in houses. So it's someone who is interested in buying houses and maybe even renovating them and then reselling them and making a profit in that way. Or maybe in the long-term investment market, when people are buying real estate in a way of investing in it and then holding it for a long time and then selling it later, or for some other purposes. The end goal in this specific case for a person is to identify what are these features of the house that makes this house to be priced at a certain level. So what are the features of the house that are causing the price and the value of the house? So we are going to make use of this very popular data set that is available on Kaggle, and it's originally coming from scikit-learn, and it's called California Housing Prices. I'll also make sure to put the link of this specific data set both in my GitHub account under this repository that will be dedicated for this specific case study, as well as I will also point out the additional links that you can use to learn more about this data set. So this data set is derived from 1990 US Census, so United States Census, using one row per census block. So a block group or block is the smallest geographical unit for which the US Census Bureau publishes sample data. So a block group typically has a population of 600 till 3,000 people who are living there. So a household is a group of people residing within a single home. Since the average number of rooms and bedrooms in this data set are provided per household, this counts may take surprisingly large values for block groups, with few households and many empty houses, such as vacation resorts. So let's now look into the variables that are available in this specific data set. So what we have here is the MED-INC, which is the median income in block group. So this touches the financial side and financial level of the block of households. Then we have house age. So this is the median house age in the block group. Then we have average rooms, which is the average number of rooms per household. Then we have average bedroom, which is the average number of bedrooms per household. Then we have population, which is the block group population. So that's basically, like we just saw, that's the number of people who live in that block. Then we have average occup, which is basically the average number of household members. Then we have latitude and longitude, which are the latitude and longitude of this block group that we are looking into. So as you can see here, we are dealing with aggregated data. So we don't have the data per household, but rather the data is calculated and averaged, aggregated based on a block. So this is very common in data science. When we want to reduce the dimension of the data and when we want to have some sensible numbers and create this cross-sectional data. And cross-sectional data means that we have multiple observations for which we have data on a single time period. In this case, we are using as an aggregation unit the block. And we have already learned as part of the theory lectures this idea of median. So we have seen that there are different descriptive measures that we can use in order to aggregate our data. One of them is the mean, but the other one is the median. And oftentimes, especially if we are dealing with skewed distribution, so if we have a distribution that is not symmetric, but it's rather right skewed or left skewed, then we need to use this idea of median, because median is then better representation of this scale of the data compared to the mean. And in this case, we will soon see when representing and visualizing this data that we are indeed dealing with skewed data. So this is basically a very simple, a very basic data set with not too many features. So great way to get your hands on with actual machine learning use case. We will be keeping it simple, but yet we will be learning the basics and the fundamentals in a very good way, such that learning more difficult and more advanced machine learning models will be much more easier for you. So let's now get into the actual coding part. So here I will be using the Google Colab. So I will be sharing the link to this notebook combined with the data in my Python for data science repository, and you can make use of it in order to follow this tutorial with me. So we always start with importing libraries. We can run a linear regression manually without using libraries by using matrix multiplication, but I would suggest you not to do that. You can do it for fun, or to understand this matrix multiplication, the linear algebra behind the linear regression. But if you want to get hands-on and understand how you can use linear regression like you expect to do it on your day-to-day job, then do expect to use instead libraries such as scikit-learn, or you can also use the statsmodels.api libraries. In order to understand this topic and also to get hands-on, I decided to showcase this example not only in one library in scikit-learn, but also the stats models. And the reason for this is because many people use linear regression just for predictive analytics. And for that, using scikit-learn, this is the go-to option. But if you want to use linear regression for causal analysis, so to identify and interpret these features, the independent variables that have a statistically significant impact on your response variable, and then you will need to use another library, a very handy one for linear regression, which is called statsmodels.api. And from there, you need to import the SM functionality, and this will help you to do exactly that. So later on, we will see how nicely this library will provide you the outcome, exactly like you will learn on your traditional econometrics or introduction to linear regression class. So I'm going to give you all this background information like no one before, and we're going to interpret and learn everything such that you start your machine learning journey in a very proper and in a very high quality way. So in this case, first thing we are going to import is the pandas library. So we are importing pandas library as PD and then numpy library as NP. We are going to need pandas just to create a pandas data frame, to read the data, and then to perform data wrangling, to identify the missing data, outliers, so common data wrangling and data processing steps. And then we are going to use NumPy, and NumPy is a common way to use whenever you are visualizing data or whenever you are dealing with matrices or with arrays. So pandas and NumPys are being used interchangeably. So then we are going to use matplotlib and specifically the PyPlat from it. And this library is very important when you want to visualize data. Then we have Seaborn, which is another handy data visualization library in Python. So whenever you want to visualize data in Python, then matplotlib and Seaborn, they are two very handy data visualization techniques that you must know. If you like this cooler undertone of colors, then Seaborn will be your go-to option, because then the visualizations that you are creating are much more appealing compared to the matplotlib. But the underlying way of working, so plotting, scatter plot, or lines, or heat map, they are the same. So then we have the statsmodels.api, which is the library from which we will be importing the SM. That is the simple linear regression model that we will be using for our causal analysis. Here I'm also importing the from scikit-learn linear model, and specifically the linear regression model. And this one is basically similar to this one. You can use both of them, but it is a common way of working with machine learning model. So whenever you are dealing with predictive analytics, so you are using the data not for identifying features that have a statistically significant impact on the response variable, so features that have an influence and are causing the dependent variable, but rather you are just interested to use the data to train the model on this data and then test it on an unseen data, then you can use scikit-learn. So scikit-learn will be something that you will be using not only for linear regression, but also for other machine learning models. Think of Cannon, logistic regression, random forest, decision trees, boosting techniques such as light GBM, GBM, also clustering techniques like k-means, dbScan, anything that you can think of that fits in this category of traditional machine learning model, you will be able to find in scikit-learn. Therefore, I didn't want to limit this tutorial only to the SAS models, which we could do if we wanted to use, if we wanted to have this case study for specifically for linear regression, which we are doing. But instead, I wanted to showcase also this usage of scikit-learn, because scikit-learn is something that you can use beyond linear regression. So for all these other type of machine learning models. And given that this course is designed to introduce you to the world of machine learning, I thought that we will combine this also with scikit-learn, something that you are going to see time and time again when you are using Python combined with machine learning. So then I'm also importing the train and test split from the scikit-learn model selection, such that we can split our data into train and test. Now, before we move into the actual training and testing, we need to first load our data. So therefore, what I did was to here, in this sample data, so in a folder in Google Colab, I put it this housing.csv data. That's the data that you can download when you go to this specific page. So when you go here, then you can also download here that data. So download 409 gigabytes of this housing data. And that's exactly what I'm downloading and then uploading here in Google Colab. So this housing.csv in this folder, so I'm copying the path and I'm putting it here, and I'm creating a variable that holds this name, so the path of the data. So the file underscore path is the variable, string variable that holds the path of the data. And then what I need to do is that I need to take this file underscore path and I need to put it in the pd.read underscore csv, which is a function that we can use in order to load the data. So PD stands for pandas, the short way of naming pandas. PD dot and then read underscore CSV is the function that we are taking from pandas library. And then within the parentheses, we are putting the file underscore path. If you want to learn more about these basics of variable, different data structures, some basic Python for data science, then to ensure that we are keeping this specific tutorial structured, I will not be talking about that. But feel free to check the Python for Data Science course, and I will put the link in the comments below, such that you can learn that if you don't know yet, and then you can come back to this tutorial to learn how you can use Python in combination with linear regression. So the first thing that I tend to do before moving on to the actual execution stage is to look into the data, to perform data exploration. So what I tend to do is to look at the data fields, so the name of the variables that are available in the data. And that you can do by doing data.columns. So you will then look into the columns in your data. This will be the name of your data fields. So let's go ahead and do command enter.
So we see that we have longitude, latitude, housing underscore median age, we have total rooms, we have total bedrooms, population. So basically the amount of people who are living in those households and in those houses. Then we have households, then we have median income, we have median house underscore value, and we have ocean proximity. Now, you might notice that the name of these variables are a bit different than in the actual documentation of the California house. So you see here the naming is different, but the underlying explanation is the same. So here they are just trying to make it nicer and represent it in a better naming. But it is a common thing to see in Python when we are dealing with data that we have this underscores in the name abbreviation. So we have housing underscore median age, which in this case you can see that it says house age. So bit different, but their meaning is the same. This is still the median house age in the block group. So one thing that you can also notice here is that in the official documentation, we don't have this one extra variable that we have here, which is the ocean proximity. And this basically describes the closeness of the house from the ocean, which of course for some people can definitely mean increase or decrease in the house price. So basically we have all these variables, and next thing that I tend to do is to look into the actual data. And one thing that we can do is just to look at the top 10 rows of the data instead of printing the entire data frame. So when we go and execute this specific part of the code and the command, you can see that here we have the top 10 rows of our data. So we have the longitude, the latitude, we have the housing median age. You can see we are seeing some 41 year, 21 year, 52 year. Basically, the number of years that a house, the median age of the house is 41, 21, 52, and this is per block. Then we have the number of total bedrooms. So we see that we have in this block, the total number of rooms that these houses have is 7,099. So we are already seeing a data that consists of these large numbers, which is something to take into account when you are dealing with machine learning models, and especially with linear regression. Then we have total bedrooms, and we have then population, households, median income, median house value, and the ocean proximity. One thing that you can see right off the bat is that we have longitude and latitude, which have some unique characteristics. And longitude is with minuses, latitude is with pluses. But that's fine for the linear regression, because what it is basically looking is whether a variation in certain independent variables, in this case longitude and latitude, whether that will cause a change in the dependent variable. So just to refresh our memory what this linear regression will do in this case. So we are dealing with multiple linear regression because we have more than one independent variables. So we have as independent variables those different features that describe the house, except of the house price, because median house value is the dependent variable. So that's basically what we are trying to figure out. We want to see what are the features of the house that define the house price. We want to identify what are the features that cause a change in our dependent variable. And specifically, what is the change in our median house price value if we apply a 1 unit change in our independent feature? So if we have a multiple linear regression, we have learned during the theory lectures that what linear regression tries to use during causal analysis is that it tries to keep all the independent variables constant and then investigate for a specific independent variable what is this 1 unit change increase in the specific independent variable will result in what kind of change in our dependent variable. So if we, for instance, change by 1 unit our housing median age,
then what will be the corresponding change in our median household value, keeping everything else constant. So that's basically the idea behind multiple linear regression and using that for this specific use case. And in here, what we also want to do is to find out what are the data types and whether we can learn a bit more about our data before proceeding to the next step. And for that, I tend to use this info function in pandas. So given that the data is a pandas data frame, I will just do data.info and then parentheses. And then this will show us what is the data type and what is the number of null values per variable. So as we have already noticed from this header, which we can also see here being confirmed, that ocean proximity is a variable that is not a numeric value. So here you can see nearby as a value for that variable, which unlike all the other values is represented by a string. So this is something that we need to take into account because later on when we will be doing the data preprocessing and we will actually run this model, we will need to do something with this specific variable. We need to process it. So for the rest, we are dealing with numeric variables. So you can see here that longitude, latitude, all the other variables, including our dependent variable, is a numeric variable. So float 64. The only variable that needs to be taken care of is this ocean underscore proximity, which we can actually later on also see that is categorical string variable. And what this basically means is that it has these different categories. So for instance, let us actually do that in here very quickly. So let's see what are all the unique values for this variable. So if we take the name of this variable, so we copy it from this overview in here, and we do unique, then this should give us the unique values for this categorical variable. So here we go. So we have actually 5 different unique values for this categorical string variable. So this means that this ocean proximity can take 5 different values, and it can be either nearby, it can be less than 1 hour from the ocean, it can be inland, it can be near ocean, and it can be in the Iceland. What this means is that we are dealing with a feature that describes the distance of the block from the ocean. And here the underlying idea is that maybe this specific feature has a statistically significant impact on the house value, meaning that it might be possible that for some people in certain areas or in certain countries, living in the nearby the ocean will be increasing the value of the house. So if there is a huge demand for houses which are near the ocean, so people prefer to live near the ocean, then most likely there will be a positive relationship. If there is a negative relationship, then it means that people, if in that area, in California, for instance, people do not prefer to live near the ocean, then we will see this negative relationship. So we can see that if we increase if the house is in the area that is not close to ocean, so further from the ocean, then the house value will be higher. So this is something that we want to figure out with this linear regression. We want to understand what are the features that define the value of the house. And we can say that if the house has those characteristics, then most likely the house price will be higher or the house price will be lower. And linear regression helps us to not only understand what are those features, but also to understand how much higher or how much lower will be the value of the house if we have these certain characteristics and if we increase these certain characteristics by 1 unit. So next we are going to look into the missing data in our data. So in order to have a proper machine learning model, we need to do some data preprocessing. So for that, what we need to do is we need to check for the missing values in our data. And we need to understand what is this amount of null values per data field. And this will help us to understand whether we can remove some of those missing values or we need to do imputation. So depending on the amount of missing data that we got in our data, we can then understand which of those solutions we need to take. So here we can see that we don't have any null values when it comes to longitude, latitude, housing, median age, and all the other variables, except one variable, one independent variable, and that's the total bedrooms. So we can see that out of all the observations that we got, the total underscore bedrooms variable has 207 cases when we do not have the corresponding information. So when it comes to representing these numbers in percentages, which is something that you should do as your next step, we can see that out of the entire data set, for total underscore bedrooms variable, only 1.003% is missing. Now, this is really important because by simply looking at the number of times, the number of missing observations per data field, this won't be helpful for you because you will not be able to understand relatively how much of the data is missing. Now, if you have for a certain variable 50% missing or 80% missing, then it means that for majority of your house blocks, you don't have that information. And including that will not be beneficial for your model, nor will be it accurate to include it, and it will result in biased model. Because if you have for the majority of observations no information, and for certain observations you have that information, then you will automatically skew your results and you will have biased results. Therefore, if you have for the majority of your data set that specific variable missing, then I would suggest you choose just to drop that independent variable. In this case, we have just 1% of the house blocks missing that information, which means that this gives me confidence that I would rather keep this independent variable and just to drop those observations that do not have a total underscore bedrooms information. Now, another solution could also be is to, instead of dropping that entire independent variable, is just to use some sort of imputation technique. So what this means is that we will try to find a way to systematically find a replacement for that missing value. So we can use mean imputation, median imputation, or more model-based, more advanced statistical or econometrical approaches to perform imputation. So for now, this is out of the scope of this problem, but I would say look at the percentage of observations for which this independent variable has missing values. If this is low, like less than 10%, and you have a large data set, then you should be comfortable dropping those observations. But if you have a small data set, so you got only 100 observations, and for them, like 20% or 40% is missing, then consider for imputation. So try to find the values that can be used in order to replace those missing values. Now, once we have this information and we have identified the missing values, the next thing is to clean the data. So here what I'm doing is that I'm using the data that we got, and I'm using the function drop NA, which means drop the observations where the value is missing. So I'm dropping all the observations for which the total underscore bedrooms has a null value. So I'm getting rid of my missing observations. So after doing that, I'm checking whether I got rid of my missing observations. And you can see here that when I'm printing data.isNull.sum, so I'm summing up the number of missing observations, null values per variable, then now I no longer have any missing observations. So I successfully deleted all the missing observations. Now the next stage is to describe the data through some descriptive statistics and through data visualization. So before moving on towards the causal analysis or predictive analysis,
in any sort of machine learning, traditional machine learning approach, try to first look into the data, try to understand the data and see whether you are seeing some patterns. What is the mean of different numeric data fields? Do you have certain categorical values that cause an unbalanced data? Those are things that you can discover early on before moving on to the model training and testing and blindly believing to the numbers. So data visualization techniques and data exploration are a great way to understand this data that you got before using that in order to train and test machine learning model. So here I'm using the traditional describe function of pandas, so data.describe parentheses, and then this will give me the descriptive statistics of my data. So here what we can see is that in total we got 20,640 observations, and then we also have a mean of all the variables. So you can see that per variable, I have the same count, which basically means that for all variables, I have the same number of rows. And then here I have the mean, which means that here we have the mean of the variables. So per variable, we have their mean, and then we have their standard deviation, so the square root of the variance. We have the minimum, we have the maximum, but we also have the 25th percentile, the 15th percentile, and the 75th percentile. So the percentile and quantiles, those are statistical terms that we often use. And the 25th percentile is the first quantile. The 15th percentile is the second quantile, or the median. And the 75th percentile is the third quantile. So what this basically means is that this percentiles help us to understand what is this threshold when it comes to looking at the observations that fall under the 25th percent and then above the 25%. So when we look at this standard deviation helps us to interpret the variation in the data at the unit, so scale of that variable. So in this case, the variable is median house value, and we have that the mean is equal to 206,000 approximately. So more or less that range, and 206K. And then the standard deviation is 115K. What this means is that in the data set, we will find blocks that will have the median house value that will be 206K plus 115K, which is around 321K. So there will be blocks where the median house value is around 321K. And there will also be blocks where the median house value will be around 91K. So 206,000 minus 115K. So that's the idea behind standard deviation, this variation in your data. So next we can interpret the idea of this minimum and the maximum of your data and your data fields. The minimum will help you to understand what is this minimum value that you have per data field, numeric data field, and what is the maximum value. So what is the range of values that you are looking into? In case of the median house value, this means what is this minimum median house value per block? And in case of maximum, what is this highest value per block when it comes to the median house value? So this can help you to understand when we look at this aggregated data, so the median house value, what are the blocks that have the cheapest houses when it comes to their valuation, and what are the most expensive blocks of houses. So we can see that the cheapest block, where in that block the median house value is 15K, so 14,999, and the house block with the highest valuation when it comes to the median house value. So the median valuation of the houses is equal to $500,001, which means that when we look at our blocks of houses,
that the median house value in these most expensive blocks will be maximum 500K. So next thing that I tend to do is to visualize the data. I tend to start with the dependent variable. So this is the variable of interest, the target variable or the response variable, which is in our case the median house value. So this will serve us as our dependent variable. And what I want you to do is to upload this histogram in order to understand what is the distribution of median house values. So I want to see that when looking at the data, what are the most frequently appearing median house values, and what are these type of blocks that have unique, less frequently appearing median house values. By plotting this type of plots, you can see some outliers, some frequently appearing values, but also some values that go and are lying outside of the range. And this will help you to identify and learn more about your data and to identify outliers in your data. So in here, I'm using the Seaborn library. So given that earlier I already imported these libraries, there is no need to import here. What I'm doing is that I'm setting the grid, so which basically means that I'm saying the background should be white, and I also want this grid. So this means this grid behind. Then I'm initializing the size of the figure. So PLT, this comes from Matplotlib PyPlot. And then I'm setting the figure. The figure size should be 10 by 6. So this is the 10 and this is the 6. Then we have the main plot. So I'm using the histplot function from Seaborn. And then I'm taking from the clean data, so from which we have removed the missing data, I'm picking the variable of interest, which is the median house value. And then I'm saying upload this histogram using the forest green color. And then I'm saying the title of this figure is distribution of median house values. Then I'm also mentioning what is the X label, which basically means what is the name of this variable that I'm putting on the X axis, which is the median house value. And what is the Y label? So what is the name of the variable that I need to put on the Y axis? And then I'm saying plt.show, which means show me the figure. So that's basically how in Python the visualization works. We first need to write down the actual figure size, and then we need to set the function and the right variable, so provide the data to the visualization. Then we need to put the title, we need to put the X label, Y label, and then we need to say, show me the visualization. And if you want to learn more about this visualization techniques, make sure to check the Python for Data Science course, because that one will help you to understand slowly and in detail how you can visualize your data. So in here, what we are visualizing is the frequency of these median house values in the entire data set. What this means is that we are looking at the number of times each of those median house values appear in the data set. So we want to understand, are there certain median house values that appear very often, and are there certain house values that do not appear that often? So those can be maybe considered outliers. Because we want in our data only to keep those most relevant and representative data points. We want to derive conclusions that hold for the majority of our observations and not for outliers. We will be then using that representative data in order to run our linear regression and then make conclusions. When looking at this graph, what we can see is that we have a certain cluster of median house values that appear quite often. And those are the cases when this frequency is high. So you can see that we have, for instance, houses in here, in all this block, that appear very often. So for instance, the median house value of about 160, 170K, this appears very frequently. So you can see that the frequency is above 1,000. Those are the most frequently appearing median house values. And there are cases when so you can see in here, and you can see in here houses that whose median house value is not appearing very often. So you can see that their frequency is low. So roughly speaking, those houses, they are unusual houses. They can be considered as outliers. And the same holds also for these houses, because you can see that for those, the frequency is very low, which means that in our population of houses, so Californian house prices, you will most likely see houses, blocks of houses, whose median value is between, let's say, 17K up to, let's say, 300 or 350K. But anything below and above this is considered as unusual. So you don't often see houses that are, so house blocks that have a median house value less than 70 or 60K. And then also houses that are above 370 or 400K. So do consider that we are dealing with 1990 a year data and not the current prices, because nowadays Californian houses are much more expensive. But this is the data coming from 1990. So do take that into account when interpreting this type of data visualizations. So what we can then do is to use this idea of interquantile range to remove these outliers. What this basically means is that we are looking at the lowest 25th percentile. So we are looking at this first quantile, so 0.25, which is the 25th percentile. And we are looking at this upper 25th percent, which means the third quantile or the 75th percentile. And then we want to basically remove those. By using this idea of 25th percentile and 75th percentile, so the first quantile and the third quantile, we can then identify what are the observations, so the blocks that have a median house value that is below the 25th percentile and above the 75th percentile. So basically, we want to get the middle part of our data. So we want to get this data for which the median house value is above the 25th percentile. So above all the median house values, that is above the lowest 25%. And then we also want to remove this very large median house values. So we want to keep in our data the so-called normal and representative blocks. Blocks where the median house value is above the lowest 25% and smaller than the largest 25%. What we are using is this statistical term called interquantile range. You don't need to know the name, but I think it would be just worth to understand it, because this is a very popular way of making a data-driven removal of the outliers. So I'm selecting the 25th percentile by using the quantile function from pandas. So I'm saying find for me the value that divides my entire block of observations, so block observations, to observations for which the median house value is below the 25th percentile and above the 25th percentile. So what are the largest 75% and what are the smallest 25th percent when it comes to the median house value, and we will then be removing this 25th percent. So that I will do by using this Q1. And then we will be using the Q3 in order to remove the very large median house values, so the upper 25th percentile. And then in order to calculate the interquantile range, we need to pick the Q3 and subtract from it the Q1. So just to understand this idea of Q1 and Q3, so the quantiles better, let's actually print this Q1 and this Q3. So let's actually remove this part for now and then run it. So as you can see here, what we are finding is that the Q1, so the 25th percentile or first quantile, is equal to $119,500. So it basically is a number in here. What it means is that we have 25% of the observations, the smallest observations, have a median house value that is below the $119,500. And the remaining 75% of our observations have a median house value that is above the $190,500. And then the Q3, which is the third quantile or the 75th percentile, it describes this threshold, the value, where we make a distinction between the lowest median house values, the first 75th percent of the lowest median house values versus the most expensive, so the highest median house values. So what is this upper 25% when it comes to the median house value? So we see that that distinction is $264,700. So it is somewhere in here, which basically means that when it comes to these blocks of houses, the most expensive ones with the highest valuation, so the 25% top rated median house values, they are above $264,700. That's something that we want to remove. So we want to remove the observations that have a smallest median house value and the largest median house values. And usually it's a common practice when it comes to the interquantile range approach to multiply the interquantile range by 1.5 in order to obtain the lower bound and the upper bound. So to understand what are the thresholds that we need to use in order to remove the blocks, so observations from our data where the median house value is very small or very large. So for that, we will be multiplying the IQR, so interquantile range, by 1.5. And when we subtract this value from Q1, then we will be getting our lower bound. When we will be adding this value to Q3, then we will be using and getting this threshold when it comes to the upper bound. And we will be seeing that after we clean these outliers from our data, we end up getting smaller data. So this means that previously we had 20K, so 20,433 observations, and now we have 19,369 observations. So we have roughly removed like about 1,000 or a bit over 1,000 observations from our data. So next, let's look into some other variables, for instance, the median income. And one other technique that we can use in order to identify outliers in the data is by using the box plot. So I wanted to showcase these different approaches that we can use in order to visualize the data and to identify outliers such that you will be familiar with different techniques. So let's go ahead and plot the box plot. And box plot is a statistical way to represent your data. So, the central box represents the interquantile range. So that is the IQR, and with the bottom and the top edges, they indicate the 25th percentile, so the first quantile, and the 75th percentile, so the third quantile, respectively. The length of this box that you see here, this dark part, is basically the 50% of your data for the median income. And this median line inside this box, this is the one with contrasting color that represents the median of the data set. So the median is the middle value when data is sorted in an ascending order. Then we have this whiskers in our box plot. And this line of whiskers extends from the top and the bottom of the box and indicate this range for the rest of the dataset, excluding the outliers. They are typically this 1.5 IQR above and 1.5 times IQR below the Q1, something that we also saw just previously when we were removing the outliers from the median house value. So in order to identify the outliers, you can quickly see that we have all these points that lie above the 1.5 times IQR above the third quantile, so the 75th percentile. And that's something that you can also see here. And this means that those are blocks of houses that have unusually high median income. That's something that we want to remove from our data. And therefore, we can use the exactly the same approach that we used previously for the median house value. So we will then identify the 25th percentile or the first quantile, so Q1, and then Q3, so the third quantile or the 75th percentile. Then we will compute the IQR, and then we will be obtaining the lower bound and the upper bound using this 1.5 as a scale. And then we will be using this lower bound and upper bound to then use these filters in order to remove from the data all the observations where the median income is above the lower bound and all the observations that have a median income below the upper bound. So we are using lower bound and upper bound to perform double filtering. We are using two filters in the same row, as you can see, and we are using this parenthesis and this end functionality to tell to Python, well, first look that this condition is satisfied, so the observations have a median income that is above this lower bound, and at the same time, it should hold that the observation, so the block, should have a median income that is below the upper bound. And if this block, this observation in the data satisfies to two of these criteria, then we are dealing with a good point, a normal point, and we can keep this. And we are saying that this is our new data. So let's actually go ahead and execute this code. In this case, we can see too high, as all our outliers lie in this part of the box plot. And then we will end up with the clean data. I'm taking this clean data, and then I'm putting it under data just for simplicity. And this data now is much more clean, and it's better representation of the population, something that ideally we want, because we want to find out what are the features that describe and define the house value, not based on this unique and rare houses, which are too expensive, or which are in the blocks that have very high income people, but rather we want to see the true representation, so the most frequently appearing data. What are the features that define the house value of the prices for common houses and for common areas, for people with average or with normal income? That's what we want to find. So the next thing that I tend to do when it comes to especially regression analysis and causal analysis is to plot the correlation heat map. So this means that we are getting the correlation matrix, pairwise correlation score, for each of this pair of variables in our data. So when it comes to the linear regression, one of the assumptions of the linear regression that we learned during the theory part is that we should not have a perfect multicollinearity. What this means is that there should not be a high correlation between pair of independent variables. So knowing one should not help us to automatically define the value of the other independent variable. And if the correlation between these two independent variables is very high, it means that we might potentially be dealing with multicollinearity. That's something that we do want to avoid. So heat map is a great way to identify whether we have this type of problematic independent variables and whether we need to drop any of them or maybe multiple of them to ensure that we are dealing with proper linear regression model and the assumptions of linear regression model is satisfied. Now, when we look at this correlation heat map, here we use the CBurn in order to plot this. As you can see here, the colors can be from very light, so white, till very dark green, where the light means there is a strong negative correlation, and very dark green means that there is a very strong positive correlation. So we know that correlation Pearson correlation can take values between -1 and 1. -1 means very strong negative correlation. 1 means very strong positive correlation. And usually when we are dealing with correlation of the variable with itself, so a correlation between longitude and longitude, then this correlation is equal to 1. So as you can see on the diagonal, we have therefore all the 1s because those are the pairwise correlation of the variables with themselves. And then in here, all the values under the diagonal are actually equal to the mirror of them in the upper diagonal, because the variable between, so the correlation between the same two variables, independent of how we put it, so which one we put first and which one the second, is going to be the same. So basically correlation between longitude and latitude and correlation latitude and longitude is the same. So now we have refreshed our memory on this. Let's now look into the actual number and this heat map. So as we can see here, we have this section where we have variables, independent variables that have a low positive correlation with the remaining independent variables. So you can see here that we have this light green values, which indicate a low positive relationship between pair of variables. One thing that is very interesting here is the middle part of this heat map, where we have these dark numbers. So the numbers below the diagonals are something we can interpret, and remember that below diagonal and above diagonal is basically the mirror. We here already see a problem because we are dealing with variables which are going to be independent variables in our model that have a high correlation. Now, why is this a problem? Because one of the assumptions of linear regression, like we saw during the theory section, is that we should not have a multiple collinearity. So multicollinearity problem. When we have perfect multicollinearity, it means that we are dealing with independent variables that have a high correlation. Knowing a value of one variable will help us to know automatically what is the value of the other one. And when we have a correlation of 0.93, which is very high, or 0.98, this means that those two variables, those two independent variables, they have a super high positive relationship. This is a problem because this might cause our model to result in very large standard errors and also not accurate and not generalizable model. That's something we want to avoid. And we want to ensure that the assumptions of our model are satisfied. Now, we are dealing with independent variable, which is total underscore bedrooms and households, which means that number of total bedrooms per block and the households is highly correlated, positively correlated. And this is a problem. So ideally, what we want to do is to drop one of those two independent variables. And the reason why we can do that is because those two variables, given that they are highly correlated, they already explain similar type of information. So they contain similar type of variation, which means that including the two, it doesn't make sense. On one hand, it's violating the model assumptions, potentially. And on the other hand, it's not even adding too much value because the other one already shows similar variation. So the total underscore bedrooms basically contains similar type of information as the households. So we can as well, so we can better just drop one of those two independent variables. Now, the question is which one? And that's something that we can define by also looking at other correlations in here. Because we have total bedrooms having a high correlation with households, but we can also see that the total underscore rooms has a very high correlation with our households. So this means that there is yet another independent variable that has a high correlation with our households variable. And then this total underscore rooms has also a high correlation with the total underscore bedroom. So this means that we can decide which one has more frequently high correlation with the rest of independent variables. And in this case, it seems like that the largest two numbers in here are the this one and this one. So we see that the total bedroom has a 0.93 as correlation with the total underscore rooms. And at the same time, we also see that total bedrooms has also very high correlation with the household, so 0.98, which means that total underscore bedrooms has the highest correlation with the remaining independent variables. So we might as well drop this independent variable. But before you do that, I would suggest to do one more quick visual check, and it is to look into the total underscore bedroom correlation with the dependent variable to understand how strong of a relationship does this have on the response variable that we are looking into. So we see that the total underscore bedroom has this one, 0.05 correlation with the response variable, so the median house value. When it comes to the total rooms, that one has much higher. So I'm already seeing from here that we can feel comfortable excluding and dropping the total underscore bedroom from our data in order to ensure that we are not dealing with perfect multicollinearity. So that's exactly what I'm doing here. So I'm dropping the total bedrooms. So after doing that, we no longer have this total bedrooms as the column. So before moving on to the actual causal analysis, there is one more step that I wanted to show you, which is super important when it comes to the causal analysis and some introductory econometrical stuff. So when you have a string categorical variable, there are a few ways that you can deal with them. One easy way that you will see on the web is to perform one-hot encoding, which basically means transforming all these string values. So we have a near bay, less than 1 hour ocean, inland, near ocean, Iceland, to transform all these values to some numbers, such that we have for the ocean proximity variable values such as 1, 2, 3, 4, 5. One way of doing that can be something like this. But a better way when it comes to using this type of variables in linear regression is to transform this string category type of variable to what we're calling dummy variables. So dummy variable means that this variable takes two possible values, and usually it is a binary Boolean variable, which means that it can take two possible values, 0 and 1, where 1 means that the condition is satisfied and 0 means condition is not satisfied. So let me give you an example. In this specific case, we have that the ocean proximity has 5 different values, and ocean proximity is just a single variable. Then what we will do is we will use the get_dummies function in Python from pandas in order to go from this one variable to 5 different variables per each of this category, which means that now we will have new variables that will basically be whether it is near bay or not, whether it's less than 1 hour from the ocean variable, whether it's inland, whether it's near ocean, or whether it's an island. This will be separate binary variables, a dummy variable, that will take values 0 and 1, which means that we are going from one string categorical variable to 5 different dummy variables. And in this case, each of those dummy variables that you can see here, we are creating 5 dummy variables, each for each of those 5 categories. And then we are combining them. And from the original data, we will then be dropping the ocean proximity data. So on one hand, we are getting rid of the string variable, which is a problematic variable for linear regression when combined with the scikit-learn library, because scikit-learn cannot handle this type of data when it comes to linear regression. And B, we are making our job easier when it comes to interpreting the results. So interpreting linear regression for causal analysis is much more easy when we have dummy variables than when we have a one string categorical variable. So just to give you an example, if we are creating from this string variable 5 different dummy variables, and those are those 5 different dummy variables that you can see in here. So this means that if we are looking at this one category, so let's say ocean underscore proximity under inland, it means that for all the rows where we have the value equal to 0, it means this criteria is not satisfied, which means that ocean proximity underscore inland is equal to 0, which means that the house block we are dealing with is not from inland. So that criteria is not satisfied. And otherwise, if this value is equal to 1, so for all these rows when the ocean proximity inland is equal to 1, it means that the criteria is satisfied and we are dealing with house blocks that are indeed in the inland. One thing to keep in mind when it comes to transforming a string categorical variable to a set of dummies is that you always need to drop at least one of the categories. And the reason for this is because we learned during the theory that we should have no perfect multicollinearity. This means that we cannot have 5 different variables that are perfectly correlated. And if we include all these values and these variables, it means that when we know that the block of houses is not near the bay, is not less than 1 hour ocean, is not inland, is not near the ocean, automatically we know that it should be the remaining category, which is inland. So we know that for all those blocks, the ocean proximity underscore Iceland will be equal to 1. And that's something that we want to avoid because that is the definition of perfect multicollinearity. So to avoid one of the OLS assumptions to be violated, we need to drop one of those categories. So we can see in here that's exactly what I'm doing. I'm saying, so let's go ahead and actually drop one of those variables. So let's see first what is the set of all variables we got. So we got less than 1 hour ocean, inland, Iceland, new bay, and then new ocean. Let's actually drop one of them. So let's drop the Iceland. And that we can do very simply by, let me see. If it's not allowing me to add a code in here. So we are doing data is equal to, and then data dot drop, and then the name of the variable within the quotation marks, and then x is equal to 1. So in this way, I'm basically dropping one of the dummy variables that I created in order to avoid the perfect multicollinearity assumption to be violated. And once I go ahead and print the columns, now we should see this column disappearing. Here we go. So we successfully deleted that variable. Let's go ahead and actually get the head. So now you can see that we no longer have a string in our data, but instead we got 4 additional binary variables out of a string categorical variable with 5 categories. All right, now we are ready to do the actual work. When it comes to the training of a machine learning model or statistical model, we learned during the theory that we always need to split that data into train and test set. That is the minimum. In some cases, we also need to do train, validation, and test such that we can train the model on the training data and then optimize the model on the validation data and find out what is the optimal set of hyperparameters. And then use this information to apply this fitted and optimized model on an unseen test data. We are going to skip the validation set for simplicity, especially given that we are dealing with a very simple machine learning model as linear regression. And we're going to split our data into train and test. And here, what I'm going to do is first I'm creating this list of the name of variables that we are going to use in order to train our machine learning model. So we have a set of independent variables and a set of dependent variables. So in our multiple linear regression, here is the set of independent variables that we will have. So we have longitude, latitude, housing median edge, total rooms, population, households, median income, median house value, and then four different dummy variables that we built from the categorical variable. Then I am specifying that the target variable is, the response variable or the dependent variable is the median house value. This is the value that we want to target, because we want to see what are the features and what are the independent variables out of this set of all features that have a statistically significant impact on the dependent variable, which is the median house value, because we want to find out what are these features describing the houses in the block that cause a variation in the target variable, such as the median house value. So here we have x is equal to, and then from the data, we are taking all the features that have the following names. And then we have the target, which is the median house value, and that's the column that we are going to subtract and select from the data. So we are doing data filtering. So here we are then selecting, and what I'm using here is the train test split function from the scikit-learn. So you might recall that in the beginning we spoke and imported this model selection library, and from the scikit-learn model selection we imported the train _test split function. Now this is the function that you are going to need quite a lot in machine learning, because this is a very easy way to split your data. So in here, the arguments of this function is first the matrix or the data frame that contains the independent variables, in our case x. So here you fill in x, and then the second argument is the dependent variable, so the y. And then we have test size, which means what is the proportion of observations that you want to put in the test, and what is the proportion of observation that you don't want to put basically in the training. If you are putting 0.2, it means that you want your test size to be 20% of your entire 100% of data, and the remaining 80% will be your training data. So if you provide 0.2 to this argument, then the function automatically understands that you want this 80-20 division, so 80% training and then 20% test size. And then finally, you can also add the random state, because the splitting is going to be random. So the data is going to be randomly selected from the entire data, and to ensure that your results are reproducible, and the next time you are running this notebook, you will get the same results. And also to ensure that me and you get the same results, we'll be using a random state. And the random state of 111 is just a random number that I liked and decided to use here. So when we go and use this and run this command, you can see that we have a training set size 15K and then test size 38K. So when you look at these numbers, you will then get a verification that you are dealing with 20% versus 80% thresholds. So then we go and we do the training. One thing to keep in mind is that here we are using the SM library, an SM function that we imported from the statsmodels.api. So this is one function that we can use in order to conduct our causal analysis and to train a linear regression model. So for that, what we need to do, so when we are using this library doesn't automatically add the first column of ones in your set of independent variables, which means that it only goes and looks at what are the features that you have provided, and those are all the independent variables. But we learned from the theory that when it comes to linear regression, we always are adding this intercept, so the beta 0. If you go back to the theory lectures, you can see this beta 0 to be added to both to the simple linear regression and to the multiple linear regression. This ensures that we look at this intercept and we see what is this average, in this case, median house value, if all the other features are equal to 0. So Therefore, given that this specific stats models.api is not adding this constant column to the beginning for intercept, it means that we need to add this manually. Therefore, we are saying sm.add_constant to the x train, which means that now our x table or x data frame adds a column of ones to the features. So let me actually show you before doing the training, because I think this is also something that you should be aware of. So if we do here a pause, so I'm going to do x_train_constant, and then I'm also going to print the same feature data frame before adding this constant, such that you see what I mean. So as you can see here, this is just the same set of all columns that form the independent variables, the features. So then when we add the constant, now after doing that, you can see that now we have this initial column of ones. This is done such that we can have beta 0 at the end, which is the intercept, and we can then perform a valid multiple linear regression. Otherwise, you don't have an intercept, and this is just not what you're looking for. Now, the scikit-learn library does this automatically. Therefore, when you are using this stats models.api, you should add this constant, and then use the scikit-learn without adding the constant. And if you're wondering why to use this specific model, as we already discussed about this, just to refresh your memory, we are using the stats models.api because this one has this nice property of visualizing the summary of your results. So your p-values, your t-tests, your standard errors, something that you definitely are looking for when you are performing a proper causal analysis and you want to identify the features that have a statistically significant impact on your dependent variable. If you are using a machine learning model, including linear regression, only for predictive analytics, so in that case, you can use the scikit-learn without worrying about using stats models.api. So this is about adding a constant. Now we are ready to actually fit our model or train our model. Therefore, what we need to do is to use sm.ols. So OLS is the ordinary least squares estimation technique that we also discussed as part of the theory. And we need to provide first the dependent variable, so y_train, and then the feature set, which is x_train_constant. So then what we need to do is to do dot fit parenthesis, which means that take the OLS model and use the y_train as my dependent variable and x_train_constant as my independent variable set, and then fit the OLS algorithm and linear regression on this specific data. If you're wondering why y-train or x-train and what is the difference between train and test, ensure to go and revisit the training theory lectures, because there I go in detail into this concept of training and testing and how we can divide the data into train and test. And this y and x, as we have already discussed during this tutorial, is simply this distinction between independent variables defined by x and the dependent variable defined by y. So y-train, y-test is the dependent variable data for the training data and test data. And then x-train, x-test is simply the training data features, so x-train, and then test data features, x-test. We need to use x-train and y-train to fit our data, to learn from the data. And then once it comes down to evaluating the model, we need to use the fitted model from which we have learned using both the dependent variable and the independent variable set, so y-train, x-train. And then once we have this model that is fitted, we can apply this to an unseen data, x_test. We can obtain the predictions, and we can compare this to the true y, so y_test, and to see how different the y_test is from the y predictions for this unseen data, and to evaluate how model is performing this prediction. So how model is managing to identify the median house values and predict median house values based on the fitted model and on an unseen data, so X_test. So this is just a background info and some refreshment. And now, in this case, we are just fitting the data on the training dependent variable and then training independent variable added a constant. And then we are ready to print the summary. Now, let's interpret those results. First thing that we can see is that all the coefficients and all the independent variables are statistically significant. And how can I see this? Well, if we look in here, we can see the column of p-values. This is the first thing that you need to look at when you're getting these results of a causal analysis and linear regression. So here we are seeing that the p-value is very small. And just to refresh our memory, p-value says what is this probability that you have obtained too high of a test statistics given that this is just by random chance. So you are seeing statistically significant results, which is just by random chance and not because your null hypothesis is false and you need to reject it. So that's one thing. In here, you can see that we are getting much more. So first thing that you can do is to verify that you have used a correct dependent variable. So you can see here that the dependent variable is a median house value. The model that is used to estimate those coefficients in your model is the OLS. The method is the least squares. So least squares is simply the technique that is the underlying approach of minimizing the sum of squared residuals, so the least squares. And the dates that we are running this analysis is the 26th of January of 2024. So we have the number of observations, which is the number of training observations, so the 80% of our original data. We have R-squared, which is the matrix that showcases what is the goodness of fit of your model. So R-squared is a matrix that is commonly used in linear regression specifically to identify how good your model is able to fit your data with this linear regression line. And the R-squared, the maximum of R-squared is 1 and the minimum is 0. 0.58, in this case, approximately 59, it means that all your data that you got and all your independent variables, so those are all the independent variables that you have included, they are able to explain 59%, so 0.59, out of the entire set of variation. So 59% of variation in your response variable, which is the median house value, you are able to explain with a set of independent variables that you have provided to the model. Now, what does this mean? On one hand, it means that you have a reasonable enough information, so anything above 0.5 is quite good, which means that more than half of the entire variation in your median house value you are able to explain. But on the other hand, it means also that there is approximately 40% of variation, so information about your house values that you don't have in your data. This means that you might consider going and looking for extra additional information, so additional independent variables, to add on the top of the existing independent variables in order to increase this amount and to increase the amount of information and variation that you are able to explain with your model. So the R-squared, this is like the best way to explain what is the quality of your regression model. Another thing that we have is the adjusted R-squared. Adjusted R-squared and R-squared in this specific case, as you can see, they are the same, so 0.59. This usually means that you are fine when it comes to amount of features that you are using. Once you overwhelm your model with too many features, you will notice that the adjusted R-squared will be different than your R-squared. So adjusted R-squared helps you to understand whether your model is performing well only because you are adding too many of those variables or because really they contain some useful information. Because sometimes the R-squared, it will automatically increase just because you are adding too many independent variables. But in some cases, those independent variables, they are not useful. So they are just adding to the complexity of the model and possibly overfitting your model, but not providing any added information. Then we have the F statistics here, which corresponds to the F test. And F test, it comes from statistics. You don't need to know it, but I would say check out the Fundamentals to Statistics course if you do want to know it, because it means that you are testing whether all these independent variables all together, whether they are helping to explain your dependent variables, so the median house value. And if the F statistics is very large, or the p-value of your F statistics is very small, so 0.00, it means that all your independent variables jointly are statistically significant, which means that all of them together helped you explain your median house value and have a statistically significant impact on your median house value, which means that you have a good set of independent variables. So then we have the log likelihood. Not super relevant in this case. You have the AIC, BIC, which stand for archaic information criteria and Bayesian information criteria. Those are also not necessary to know for now, but once you advance in your career in machine learning, it might be useful to know at high level. For now, think of it like a value that helps you understand this information that you gain when you are adding this set of independent variables to your model. But this is just optional. Ignore it if you don't know it for now. Okay, let's now go into the fun part. So in this meta part of the summary table, we got first the set of independent variables. So we have our constant, which is the intercept. We have the longitude, latitude, housing, median age, total rooms, population, households, median income, and the 4 dummy variables that we have created. Then we have the coefficients corresponding to those independent variables. Those are basically the beta 0, beta 1 hat, beta 2 hat, etc., which are the parameters of the linear regression model that our OLS method has estimated based on the data that we have provided. Now, before interpreting these independent variables, the first thing you need to do, as I mentioned in the beginning, is to look at this p-value column. This showcases the set of all independent variables that are statistically significant. And usually this table that you will get from statsmodels.api is at a 5% significance level. So the alpha, the threshold of statistical significance, is equal to 5%. And any p-value that is smaller than 0.05, it means you are dealing with statistically significant independent variable. Now, the next thing that you can see here in the left is the t-statistics. This p-value is based on a t-test. So this t-test is simply stating, as we have learned during the theory, and you can also check the Fundamentals to Statistics course from Lunar Tech for more detailed understanding of this test. But for now, this t-test states a hypothesis whether each of these independent variables individually has a statistically significant impact on the dependent variable. And whenever this t-test has a p-value that is smaller than the 0.05, it means you are dealing with statistically significant independent variable. In this case, we are super lucky. All our independent variables are statistically significant. Then the question is whether we have a positive statistical significance or negative. That's something that you can see by the signs of these numbers. So you can see that longitude has a negative coefficient, latitude negative coefficient, housing median age positive coefficient, etc. Negative coefficient means that this independent variable causes a negative change in the dependent variable. So more specifically, when we look, for instance, the, let's say, which one should we look? Let's say the total underscore rooms. When we look at the total underscore rooms and it's minus 2.67, it means that when we look at this total number of rooms and we increase the number of rooms by 1 additional unit, so 1 more room added to the total underscore rooms, then the house value decreases by minus 2.67. Now you might be wondering, but how is this possible? Well, first of all, the value, the coefficient is quite small. So on one hand, it's not super relevant, as we can see. The relationship between them is not super strong because the margin of this coefficient is quite small. But on the other hand, you can explain that at some point when you are adding more rooms, it just doesn't add any value. And in fact, in some cases, just decreases the value of the house. This might be the case. At least this is the case based on this data. We can see that if there is a negative coefficient, then 1 unit increase in that specific independent variables all else constant, will result in this case, for instance, in case of the total rooms, 2.67 decrease in the median house value, everything else constant. We are also referring to this as ceteris paribus in econometrics, which means that everything else constant. So one more time, let's refresh our memory on this. So ensure that we are clear on this. If we add one more room to the total number of rooms, then the median house value will decrease by $2.67. And this when the longitude, latitude, house median age, population, households, median income, and all the other criteria are the same. So if we have, for instance, this negative value, this means that we are getting a decrease in the median house value if we have an increase by 1 unit in our total number of rooms. Now let's look at the opposite case when the coefficient is actually positive and large, which is the housing median age. This means is if we have two houses, they have exactly the same characteristics. So they have the same longitude, latitude, they have the same total number of rooms, population, housing, households, median income. They are the same in terms of the distance from the ocean. Then if one of these houses has one more additional year added on the median age, so housing median age, so it's 1 year older, then the house value of this specific house is higher by $846. So this house, which has one more additional median age, has $846 higher median house value compared to the one that has all these characteristics, except it has just the house median age that is 1 year less. So one more additional year in the median age will result in 846 increase in the median house value, everything else constant. So this is regarding this idea of negative and then positive and then the margin of coefficient. Now let's look at one dummy variable and explain the idea behind it and how we can interpret it. And it's a good way to understand how these dummy variables can be interpreted in the context of linear regression. So one of the independent variables is the ocean proximity inland. And the coefficient is equal to minus 2.108 e plus 0.5. This simply means minus 210K approximately. And what this means is that if we have two houses, they have exactly the same characteristics, so their longitude, latitude is the same, house median age is the same, they have the same total number of rooms, population, households, median income. All these characteristics for these two blocks of houses is the same, with a single difference that one block is located in the inland when it comes to ocean proximity, and the other block of houses is not located in the inland. So in this case, the reference, so the category that we have removed from here was the Iceland, you might recall. So if the block of houses is in the inland, that their value is on average smaller and less by 210K when it comes to the median house value compared to the block of houses that has exactly the same characteristics but is not in the inland. So for instance, is in the Iceland. So when it comes to these dummy variables where there is also an underlying referenced variable which you have deleted as part of your string categorical variable, then you need to reference your dummy variable to that specific category. This might sound complex. It is actually not. I would say it's just a matter of practicing and trying to understand what is this approach of dummy variable. It means that you either have that criteria or not. In this specific case, it means that if you have two blocks of houses with exactly the same characteristics and one block of houses is in the inland and the other one is not in the inland, for instance, is in the Iceland, then the block of houses in the inland will have on average 210,000 less median house value compared to the block of houses that is in the, for instance, in the Iceland when it comes to the ocean proximity. Which kind of makes sense because in California, people might prefer living in the Iceland location, and the houses might have more demand when it comes to the Iceland location compared to the inland locations. So the longitude has a statistically significant impact on the median house value. Latitude, house median age has an impact and causes a statistically significant difference in the median house value if there is a change in the median age. The total number of rooms have an impact on the median house value, and the population has an impact, households, median income, as well as the proximity from the ocean. And this is because all their p-values is 0, which means that they are smaller than 0.05. And this means that they all have a statistically significant impact on the median house value in the Californian housing market. Now, when it comes to the interpretation of all of them, we have interpreted just few for the sake of simplicity and ensuring that this entire case study doesn't take too long. But what I would suggest you to do is to interpret all of the coefficients here, because we have interpreted just the housing median age and the total number of rooms, but you can also interpret the population as well as the median income, and we have also interpreted one of those dummy variables, but feel free also to interpret all the other ones. So by doing this, you can also even build an entire case study paper in which you can explain in 1 or 2 pages the results that you have obtained. And this will showcase that you have an understanding of how you can interpret the linear regression results. Another thing that I would suggest you to do is to add a comment on the standard error. So let's now look into the standard errors. We can see a huge standard error that we are making. And this is the direct result of the 4th assumption that was violated. Now, this case study is super important and useful in the way that it showcases what happens if some of your assumptions are satisfied and if some of those assumptions are violated. So, in this specific case, the assumption related to the errors having a constant variance is violated. So we have a heteroscedasticity issue, and that's something that we are seeing back in our results. And this is a very good example of the case that even without checking the assumptions, you can already see that the standard error is very large. And you can see here that given that the standard error is large, this already gives a hint that most likely our heteroscedasticity is present and our homoscedasticity assumption is violated. Do keep in mind this idea of large standard errors that we just saw, because we are going to see that this becomes a problem also for the performance of the model, and we will see that we are obtaining a large error due to this. And one more comment when it comes to the total rooms and the housing median age. In some cases, the linear regression results might not seem logical, but sometimes there actually is an underlying explanation that can be provided. Or maybe your model is just overfitting or biased. That's also possible. And that's something that you can do by checking your OLS assumptions. And before going to that stage, I wanted to briefly showcase to you this idea of predictions. So we have now fitted our model on the training data, and we are ready to perform the predictions. So we can then use our fitted model, and we can then use the test data, so X test, in order to perform the predictions. So to use that data to get new median house values for the blocks of houses for which we are not providing the corresponding median house price. So on the unseen data, we are applying our model that we have already fitted, and we want to see what are these predicted median house values, and then we can compare these predictions to the true median house values that we have, but we are not yet exposing them. And we want to see how good our model is doing a job of estimating and finding these unknown median house values for the test data. So for all the blocks of houses for which we have provided the characteristics in the X test, but we are not providing the Y test. So as usual, like in case of training, we are adding a constant with this library, and then we are saying model.fitted, model underscore fitted, so the fitted model, and then dot predict and providing the test data. And those are the test predictions. Now, once we do this, we can then get the test predictions, and if we print those, you can see that we are getting a list of house values. Those are the house values for the blocks of houses which were included as part of the testing data, so the 20% of our entire data set. Like I mentioned just before, in order to ensure that your model is performing well, you need to check the OLS assumptions. So during the theory section, we learned that there are a couple of assumptions that your model should satisfy and your data should satisfy for OLS to provide unbiased and efficient estimates, which means that they are accurate, their standard error is low, something that we are also seeing as part of the summary results, and your estimates are accurate. So the standard error is a measure that showcases how efficient your estimates are, which means do you have a high variation? Can the coefficients that you are showing in this table vary a lot, which means that you don't have accurate coefficients, and your coefficients can be all the way from one place to the other. So the range is very large, which means that your standard error will be very large, and this is a bad sign. Or you are dealing with an accurate estimation, and it's more precise estimation. And in that case, the standard error will be low. And unbiased estimate means that your estimates are a true representation of the pattern between each pair of independent variable and the response variable. If you want to learn more about this idea of bias, unbiased, and then efficiency, ensure to check the Fundamentals to Statistics course at LunarTech, because it explains very clearly these concepts in detail. So here I'm assuming that you know, or maybe you don't even need it, but I would suggest you to know at high level at least. Then let's quickly do the checking of OLS assumptions. So the first assumption is the linearity assumption, which means that your model is linear in parameters. One way of checking that is by using your already fitted model and your predicted model, so the Y test, which are your true median house values for your test data, and then test predictions, which are your predicted median house values for non-seen data. So you are using the true values and the predicted values in order to plot them, and then to also plot the best fitted line in an ideal situation when you would make no error and your model would give you the exact true values, and then see how well your how linear is this relationship. Do we actually have a linear relationship? Now, if the observed versus predicted values, where the observed means the real test Y's and the predicted means the test predictions, if this pattern is kind of linear and matching this perfect linear line, then you have assumption 1 that is satisfied. Your linearity assumption is satisfied, and you can say that your data and your model is indeed linear in parameters. Then we have the second assumption, which states that your samples should be random. And this basically translates that the expectation of your error terms should be equal to 0. And one way of checking this is by simply taking the residuals from your fitted model. So model underscore fitted and then dot residuals. So you take the residuals, you obtain the average, which is a good estimate of your expectation of errors. And then this is the mean of residuals, so the average residuals, where the residuals is the estimate of your true error terms. And then here what I do is I just round up to the 2 decimals behind the point. This means that we are getting this average amount of errors, or the estimate of the errors, which we are referring as residuals. And if this number is equal to 0, which is the case, so the mean of the residuals in our model is 0, it means that indeed the expectation of the error terms, at least the estimate of it, expectation of the residuals, is indeed equal to 0. Another way of checking the second assumption, which is that the model is based on a random sample, and the sample we are using is random, which means that the expectation of the error terms is equal to 0, is by plotting the residuals versus fitted values. So we are taking the residuals from the fitted model, and we are comparing to the fitted values that comes from the model. And we are looking at this graph, this scatter plot, which you can see in here. And we're looking whether this pattern is symmetric around the threshold of 0. So you can see this line kind of comes right in the middle of this pattern, which means that on average, we have residuals that are across 0. So the mean of the residuals is equal to 0. And that's exactly what we were calculating also here. Therefore, we can say that we are indeed dealing with a random sample. This plot is also super useful when it comes to the fourth assumption that will come a bit later. So for now, let's check the third assumption, which is the assumption of exogeneity. So exogeneity means that each of our independent variables should be uncorrelated from the error terms. So there is no omitted variable bias, there is no reverse causality, which means that the independent variable has an impact on the dependent variable, but not the other way around. So dependent variable should not have an impact and should not cause the independent variable. So for that, there are a few ways that we can deal with this. One way is just straightforward to compute the correlation coefficient between each of these independent variables and the residuals that you have obtained from your fitted model. That's just simple technique that you can use in a very quick way to understand what is this correlation between each pair of independent variable and the residuals, which are the best estimates of your error terms. And in this way, you can understand whether there is a correlation between your independent variables and your error terms. Another way you can do that, and this is more advanced and a bit more towards the econometrical side, is by using this test, which is called the Durbin-Wu-Hausmann test. So this Durbin-Wu-Hausmann test is a more professional, more advanced way of using an econometrical test to find out whether you have exogeneity, so exogeneity assumption is satisfied, or you have endogeneity, which means that one or multiple of your independent variables is potentially correlated with your error terms. I won't go into detail of this test. I'll put some explanation here, and also feel free to check any introductory to econometrics course to understand more on this Durbin-Wu-Hausmann test for exogeneity assumption. The fourth assumption that we will talk about is the homoscedasticity. Homoscedasticity assumption states that the error terms should have a variance that is constant, which means that when we are looking at this variation that the model is making across different observations, that when we look at them, the variation is kind of constant. So we have all these cases when in observations for which the residuals are a bit small, in some cases a bit large, we have this mirror when it comes to this figure with what we are calling heteroscedasticity, which means that homoscedasticity assumption is violated. Our error terms do not have a variation that is constant across all the observations, and we have a high variation and different variations for different observations. So we have the heteroscedasticity issue. We should consider a bit more flexible approaches like GLS, FGLS, GMM, all a bit more advanced econometrical algorithms. So the final part of this case study will be to show you how you can do this all, but for machine learning, traditional machine learning side, by using the scikit-learn. So in here, I'm using the standard scaler function in order to scale my data. Because we saw in the summary of the table that we got from the stats models.api that our data is at a very high scale because the median house values are those large numbers. The median age of the house is in these very large numbers. That's something that you want to avoid when you are using the linear regression as a predictive analytics model. When you are using it for interpreting purposes, then you should keep the scales because it's easier to interpret those values and to understand what is the difference in the median price of the house when you compare different characteristics of the blocks of houses. But when it comes to using it for predictive analytics purposes, which means that you really care about the accuracy of your predictions, then you need to scale your data and ensure that your data is standardized. One way of doing that is by using the standard scaler function in the scikit-learn.preprocessing. The way I do it is that I initialize the scaler by using the standard scaler and then parentheses, which I just imported from this scikit-learn library. And then I am taking the scaler, I'm doing .fit_transform xtrain, which basically means take the independent variables and ensure that we scale and standardize the data. And standardization simply means that we are standardizing the data that we have to ensure that some large values do not wrongly influence the predictive power of the model. So the model is not confused by the large numbers and finds a wrong variation, but instead it focuses on a true variation in the data based on how much the change in one independent variable causes a change in the dependent variable. Here, given that we are dealing with a supervised learning algorithm, the xtrain scaled will be then containing our standardized features, so independent variables, and then x-test scaled will contain our standardized test features, so the unseen data that the model will not see during the training, but only during prediction. And then what we will be doing is that we will also use the y-train, and y-train is the dependent variable in our supervised model. And y-train corresponds to the training data. So we will then first initialize the linear regression here, so linear regression model from scikit-learn. And then we will initialize the model. This is just an empty linear regression model. And then we will take this initialized model and then we will fit them on the training data. So x_trained_scale. So this is the trained features. And then the dependent variable from training data, so y-train. Do note that I'm not scaling the dependent variable. This is a common practice because you don't want to standardize your dependent variable. Rather than you want to ensure that your features are standardized, because what you care about is about the variation in your features and to ensure that the model doesn't mess up when it's learning from those features, less when it comes to looking into the impact of those features on your dependent variable. So then I am fitting the model on this training data, so features and then dependent variable. And then I'm using this fitted model, the LR, which already has learned from these features and dependent variable during supervised training. And then I'm using the x-test scale, so the test standardized data, in order to perform the prediction. So to predict the median house values for the test data, unseen data. And you can notice that here, in no places I'm using y-test. Y-test I'm keeping to myself, which is the dependent variable true values, such that I can then compare to these predicted values and see how well my model was able to actually get the predictions. Now, let's actually also do one more step. I'm importing from the scikit-learn the matrix such as mean squared error, and I'm using the mean squared error to find out how well my model was able to predict those house prices. So this means that we have, on average, we are making an error of $59,000 when it comes to the median house prices, which dependent on what we consider as large or small, this is something that we can look into. So, like I mentioned in the beginning, the idea behind linear regression using in this specific course is not to use it in terms of pure traditional machine learning, but rather than to perform causal analysis and to see how we can interpret it. When it comes to the quality of the predictive power of the model, then if you want to improve this model, this can be considered as a next step. You can understand whether your model is overfitting, and then the next step could be to apply, for instance, the lasso regularization, so lasso regression, which addresses the overfitting. You can also consider going back and removing more outliers from the data. Maybe the outliers that we have removed was not enough, so you can also apply that factor. Then another thing that you can do is to consider a bit more advanced machine learning algorithms, because it can be that although the regression assumption is satisfied, but still using a bit more flexible models like random forest, decision trees, or boosting techniques will be a bit more appropriate, and this will give you higher predictive power. Consider also working more with this scaled version or normalization of your data.
Interested in machine learning or data science? Then this course is for you. Today we will build a movie recommender system using feature selection, count vectorization, cosine similarity, and at the end of the video we will create a web app using Scrimblets. Building projects is one of the most effective ways to thoroughly learn a concept and develop essential skills. This guide will walk you through building a movie recommendation system that's tailored to user preferences. We will leverage a vast 10,000 movie dataset as our foundation. While the approach is intentionally simple, it establishes the core building blocks common to the most sophisticated recommendations in the industry. Think Netflix, Spotify, or others. We will harness the power and versatility of Python to manipulate and analyze our data. The Pandas library will streamline data preparation, and scikit-learn will provide robust machine learning algorithms like count vectorizer and cosine similarity. User experience is key, so we will design an intuitive web application for effortless movie selection and recommendation display. At the end of the video, develop a data-driven mindset, understand the essential steps in building a recommendation system. We will master core machine learning techniques, dive into data manipulation, feature engineering, and machine learning for user recommendations, and create a user-centered solution to deliver a seamless experience for personalized movie suggestions. So let's get started. Alright, so let's now go over the dataset we'll be using. For the movie recommender system, we are using the TMDB movies dataset from Kaggle. This dataset is crucial for developing a system that recommends films tailored to your preferences and introduces you to new titles. We selected this dataset for its comprehensive movie data. It includes ID, which is essential for movie identification, title, genre, origin of language, and many other features. But the key features that we will focus on are ID and title, the genre and overview, and to add on top of this, we will combine the tags of overview and genre together. So we have selected this dataset because of how big it is. It has around 10k top-rated TMDB movies, and it has, as you see, many features. So let's move on to the next chapter, which is feature engineering. Okay, so now let's go over the features that we'll be using. Features in a recommender system are essentially the data points you use to make decisions about what to recommend. These features help in identifying similarities between movies, which is crucial for generating personalized recommendations. For your system to be effective, it's vital to select features that offer meaningful insights into the content of the movies and the preferences of the users. So you have to be careful with what features you choose, and for our movie recommender system, we will focus on several key features. ID. This serves as a unique identifier for each movie, crucial for indexing and retrieving movie information accurately. Title. The most basic yet essential feature enabling users to identify movies by their names. Genre. This categorizes movies into different parts, facilitating recommendations based on content similarity and user preferences. The genre plays a pivotal role in personalization. And of course, the overview, offering a brief summary of the movie's plot. The overview acts as a rich source for content-based filtering through NLP. So we will be using the overview combined with genre. You create a very comprehensive descriptor for each movie. Therefore, you're able to recommend movies more accurately. Now, combining the overview with the genre into a single tags feature gives us a fuller picture of each movie. This combination helps the system to better analyze and find movies that are similar in theme, story, or style. So, for example, let's consider a movie like Inception. Its overview might be like a thief who steals corporate secrets through dream-sharing technology, who is tasked with planting an idea into the mind of a CEO. Now, the genre could be listed as action, science fiction, adventure. However, if you combine this with the text, which is action, science fiction, and adventure, you get a more fuller pictures, which is action, science fiction, adventure, thief, corporate secrets, dream-sharing technology, planting an idea or a CEO, which might recommend you a movie like The Matrix. But the main point is that when you combine the overview with the text, you get a much more sophisticated feature that you can convert to a much more sophisticated numerical data point that you can use to better recommend movies. And before using the overview and genre data for the Lord of the Rings, for example, you would remove the and all. Now we pre-process the selected features because there are many movies that include stop words in their title or in their genre or overview, and those are words that don't contribute anything to the title, and therefore we pre-process them and remove them and clean out data. So those are, for example, words such as the, and, in, his, and other words as well. So we have done our feature selection, and now let's move on to content-based versus collaborative-based recommender systems. Alright, let's explore now the key recommender systems that are currently being used by Netflix, Amazon, and other big tech. So there are two main recommender systems, which are content-based and collaborative filtering recommender systems. Now let's start with a content-based recommender system. Now, a content-based recommender system only uses the features and the overview of the movies that you have liked to recommend similar movies. So let's say you talk with a friend and you say, I liked Iron Man because of its features, such as the director, the genre it has, and or the overview. It will recommend similar movies based on those features. So it won't use any other data, for example, what other people have liked, or what her rating is of other movies, or what rating you have given to other movies. It's just based solely on the features of the movies that you have liked previously. So for example, if you've enjoyed Inception, a content-based system, I suggest Interstellar, because both movies share a similar director and a complex narrative structure, genre, and overview. Now, let's go on to a collaborative filtering recommender system. So in Netflix, you often see, for example, if you have watched and enjoyed Stranger Things, Netflix might often recommend The Witcher to you because other users who liked Stranger Things also enjoyed The Witcher. Now, what's important to note here is that it doesn't use the features or the overview or the other informative data points. It only uses what other users have liked, what other users that have similar preferences like you have also liked. So that's the difference. This recommendation is made based on the viewing habits and the preferences of a larger group of viewers with similar taste to yours. Now, this method doesn't rely on item features but on the wisdom of the crowd. It uses patterns of ratings or interactions from many users to predict what an individual might like. For example, if users who like the Avengers also enjoyed the Guardians of the Galaxy, you might receive a recommendation for Guardians of the Galaxy if you like the Avengers. And while both systems are effective on their own, if you could combine them, that would enhance the accuracy of the recommender system. So for example, you start off with content-based recommender system, but once you start getting more data, you can also use collaborative filtering recommender system to provide more accurate recommendations. In this session, we will focus on the crucial element of transforming text into numerical vectors. So our models aren't able to be trained on text, but they are able to be trained on numerical vectors, which means that we have to convert our text into a vector. So to do that, we use Count Vectorizer. This method simplifies text analysis by ignoring the order of words, instead focusing on the frequency. By translating text into numerical data, we'll be able to classify documents, a vital function that allows our systems to process and organize large amounts of text data efficiently. We aim to provide a straightforward, practical understanding of this essential technique so that we can move on to our next chapter, which is cosine similarity. To provide a more targeted example, let's say we are considered 3 movie overviews, which is an action-packed adventure, and adventure movies inspire me, and we both love hard racing adventures. So if we count the words that we are using here, which is fun, action, hack, adventure, movies, inspire me, we both love hard racing. So we use the following words in our sentences. Now for our action-packed adventure, we use fun once, action-packed adventure, we use it as well. But for the rest, we don't use any of them. So our vector is 1, 1, 1, 0, 0, 0, 0, 0. And this is our vector. Now for the second example, which is fun adventure movies inspire me, we use no fun, we use no action pack, we use adventure once, we use movies once, we use inspire once, and we use me once, and the rest we don't use it as well, which means we get the vector is 0, 0, 1, 1, 1, 1, 0, 0, 0, 0. So this is our second vector. And you can do the same for we both love hard racing adventures, but I think you get the idea. So this step is key as it transforms statutory information into a numerical format, a vector. Each movie or overview is hence converted into a vector in a high dimensional space where each unique word is a dimension, and the word's frequency in the overview is the value in that dimension. Now, this structure allows machine learning models to interpret the data, aiding tasks such as genre classification, movies as an example. So let's say we have Iron Man 1, 2, 3, and the Avengers. We try to create a vector out of this. We use Iron Man 1, so we have the use of words Iron Man 1, 2, 3. So for example, if we have Iron Man 1, you can expect the following vector 1, 1, 1, 0, 0. We get out this 1, 1, 0, 0. 2, then you can expect for the structure to be the 1, 0. For Iron Man 3, we can expect 1, 1, 0, 0, 1. So this process of convectorization, translating movies titles into numerical vectors, is a cornerstone in the realm of text analysis. It allows us to convert unstructured text, such as movie titles, into a structured format that became later used in our machine learning algorithms. And we can extend this process to a larger and a more complex bodies of text. For instance, we could apply convectorization to movie descriptions, reviews, or even entire scripts. Irrespective of the text size or complexity, the convectorizer method remains effective. It allows us to handle a broad spectrum of text data. To understand the concept of closeness similarity to the lens of movies, let's take a simple example. Imagine we are comparing two movies based on the genres, sci-fi thriller and just sci-fi. Now, closeness similarity is the following. It's an equation of the dot product of two vectors and the multiplication of the magnitudes of the two vectors. So when we have a sci-fi thriller and we convert it to a vector, which is sci-fi and then thriller, is a 1 1, and just sci-fi is just 1 0. So when we would multiply them, we would do 1 plus 1 plus 1 times 0, and the magnitude of 1 1, which is the magnitude of A, is equal to square root or square of 1, a square of 1, and square root of it, which is 2. And for sci-fi, which is vector B, is the magnitude of a 0 square. So 1 times, so this is equal to 1 over square root of 2. Now if you take the cosine of this, you will get 0.71. So this is how similar the two movies are, the 0.71. Now let's have a more broader example. So we have Iron Man 1, and we compare it with the Avengers and Oppenheimer. Now, Iron Man 1, 2, or 3, it's an action sci-fi. Now, the Avengers is an action, sci-fi, and adventure. And Oppenheimer is drama and historical. Now, we will calculate the closeness similarity between these movies to the genre, and we will recommend movies based on their genre. So, if we try to make factors out of them, out of the genres of each movie, we have action, adventure, or you can also do action, sci-fi, adventure, drama, and historical. And then Iron Man would be 1 1 0 0 0. Avengers will be 1 1 1 0 0, and Oppenheimer will be 0 0 0 1 1. So let's calculate the similarities between Iron Man and the Avengers. Now the dot product, as I mentioned, cosine similarity is equal to dot product of the two factors divided by magnitude of A times magnitude of B. So when we take the example of Iron Man and the Avengers, we get that we get the following vectors: 1 1 0 0 0, and the Avengers, which is 1 1 1 0 0. So now when you take the dot product of this, you get 1 times 1, 1 times 1, 1 times 0, 0 0 0 0 0. Now, if we calculate the cosine similarity between the Iron Man and the Oppenheimer, that will get 0 because So as you can see, we calculate the cosine similarity using this formula. Alright, let's get started. So I have written code already, so I will just walk you through it. And let's start with step 1, which is import pandas. So since we will be using pandas, we must first import it. This is the data exploration and pre-processing part. But let's install the pandas. Okay, so let's start with the feature selection part, which means first do not list all the columns in diaphragm to identify relevant features. So these are all the columns that we have inside our data set. We are going to combine overview and genre into a column which will have the name tags. And let's run it. Perfect. Now let's run into get. Now there's a new column which is tags. Now we have an additional tags, and this is the only column that we'll be using to run our model on, which means we don't need overview and genre anymore, so we can get rid of it. We do that by saying mu data is equal to movies.drop, and we are going to drop the columns overview and genre. Perfect. As you can see, I have only ID, title, and tags. And this is great. Now aside the text cleaning part, we will import NRK and the necessary modules for our text pre-processing. Now let's run this. Because our first part, we will download the necessary modules, the NRK resources for pre-processing. Okay, let's start with cleaning the text. So first we want to make sure that it's not a string. Do that by saying if not is instance of text. Now we want to also say all movies titles or the text column must all be lowercase. We also want to remove punctuation with Q digits. We also want to tokenize it, move stopwords, and join the words back together. And now we want to delete again our clean data. Perfect. Alright, now up to the converterizer part. So let's import this and also install it, if not already installed, but it seems already installed. We apply the cream text function to a text column, and we create a new column which says text clean. So we clean the data here. Okay, so let's finish it as a converterizer. Perhaps futures is 10,000 and stop words disable English. And we also, what we say here is that our maximum number of futures are 10,000, and we must remove all the stop words that contain inside the English language vocabulary. Okay, now we're back to our words. So now we fit the text data into an array and vectorize it. Perfect. We have only good data, the ID, and
perfect. Alright, so now we can import cosine similarity and start or initializing cosine similarity. So through this line, we calculate the cosine similarity between the movies.
and based on their vector representations that we did, we already vectorized it through our count vectorizer. Now we can calculate the similarity between them, and that's you do that by initializing it and saying similarity is perfect. It is run. Now let's see if the similarity. Great. Now we click on new data.info and we have data is still the same with 10,000 IDs, 10,000 titles, and still some missing overviews or tags. Perfect. All right. Everything looks fine. Now we want to identify and print the. So here we want to see how our model has performed. So we are going to calculate, we are going to identify and print the titles of the top 5 similar movies to a given movie based on cosine similarity. And here we will do it for movie 3, movie 4. Let's say which one was movie 4. Movie 4 is The Godfather Part 2. With this function, we see if our model works. So what we want to do here is to calculate the distance between. We want to calculate the most similar or the movies that have the highest cosine similarity score with movie 4. And we want to return the reverse order of the list, meaning that the most similar movie will come on top. And we want to do this by going from 0 to 5, which means we want to only recommend 5 movies. And of course we want to then print the data of the list of 5 movies, meaning the title of the list that contains the 5 most similar movies to movie 4. Perfect. So movie 4, which is The Godfather, or something that is related to Godfather, it recommends as Godfather Part 2. Alright. So let's now create a function that will only recommend us a movie based on the title of the movie. So not the ID, but just the title. And let's see if that works. Okay, so now let's save the modified data frame and the similarity matrix for data use. We are going to use this in our web app. So let's import Pickle, and want to also download the movies list, the similarity score, and want to load the saved similarity score. And perfect. Alright, I will see you in the last part, which is building the actual web app. So as you can see, the front end will be provided to you, and the only thing you have to do is just to code the front end app.py as st, import pickle, import requests. So we have to first write a function to fetch movie poster using movie ID. Now this function will be provided to you. You can just do that by connecting the API.
Now you have to load movie data and similarity matrix. You can do it by movies is equal to pickle.load. We have done this similarly in WooColab, but now we are loading it. And we have to also do the same for similarity and for movies list. So let's now create the header for our web app. Should we see as header the recommended system. So now we have to also bring the necessary components for our streamlet. We will be creating an image carousel, and for that we must first import the components. So we will be importing necessary components to create an image carousel. So we'll be using the component from our front end and public. And as a base, we want to be able to fetch movie posters using movie ID, or there just to be a base of movies that are recommended, so that it's not empty. And it works just fine. And of course, let's display the image carousel component. And now create a drop-down menu for our movies page. And now let's create our recommend function. So what we want to do first is create. So the way we are going to do it is by first finding the index of a selected movie from our data frame based on its title. And then we are going to calculate its similarity scores against the movies. And we are going to rank it from the movie that's the most similar, meaning the highest cosine similarity score, to the lowest. And we are going to recommend 5 movies. Of course, you can recommend 90 or 50 movies. That's completely up to you. So let's now first find the index, or create a variable index. And now let's calculate it by the similarity score. Similarity score. And do that by distance. So as you can see, we'll first calculate the similarity score. We'll return the reverse order, meaning the highest ranking to the lowest. And now we want to initialize the lists, which we will do by a command movie is equal to an empty list. Command poster is equal to an empty list. ID, finalists. Recommend poster. Perfect. And it works perfectly. Alright, so let me walk you through the code to show you exactly how you can do it as well. So we first import the Streamlit, Pickle, and of course request to fetch posters for our movie IDs, the images, because we don't have it stored. And then we load our data. We load our movies list and of course the similarity score, and we grab its titles. And now we create the header of our web app. And to create a carousel, we must first bring or import components for our Streamlit. Here we initialize our carousel component. We fetch here some movie posters, images, for there to be basic list of available images, or rather movies that people can use to navigate without, it's just a basic image carousel. And then we display the image carousel component, creating of course the drop-down menus. And here's the main function of our movie recommender system, which is basically we first initialize the index of our movies or a movie. Then we calculate its distance, or rather the similarity score between all the movies, and return one that ranks the highest. So which means the movies that are the most similar will be returned. And alright, so let's now work on the main function. This is our main function, which allows us to recommend movies based on index. So here we initialize the index of the movie, then we calculate here the most similar movies in respect to our selected movie. We initialize the list of movie and poster, and here we just fill in the lists, and once everything is filled we just return it. This is the button that we will click on to recommend movies. We will have 3 or 5 columns, and each column will have a text, and it works just fine. As you can see, when we click on the recommend Iron Man. Thank you for watching this video. I hope you enjoyed creating the movie recommendation system. If you'd like to watch more of this content, then make sure to subscribe. And other than that, I will see you guys in the next video.
When you want to enter in the business, you need to at the very least show that you can work for the task that you are going to be hiring for. My starting point is like showing your data science portfolio, showing that you could actually do the work.
Right. So a strong data science portfolio, basically. You learn the data science, communication, translation skills, business acumen, all plus, but extra. But for you as a hiring manager during the hiring process, you pay attention at the projects that they have completed, unless they have already an experience. Hi, everybody. Welcome, Cornelius.
Really excited to have you here, an experienced data scientist, a top voice in the field of data science, and with wealth of knowledge here to share with you. Cornelius, you are a data science manager at Allianz. So can you walk us through your journey in the data science field and how you went through the corporate ladder?
Oh, that's a nice story, I think. So I think I will go back to the beginning first. So before I go into like all the corporate stuff. So I'm starting actually like every student, every aspirant data scientist, I want to become a data scientist. But I'm starting not majoring in any data science field. I actually majoring in a biology and evolutionary biology. My bachelor, my master, everything is all about biology. I'm a researcher at heart, obviously. But there's just like the moment like where I become a data scientist that I want to become a data scientist. So this is the moment that on the first coming where I was like in my master study. I listening at a webinar and then I tried to see what kind of a job that I could have in the future. Because like this, like as a biologist, especially in my country in Indonesia, it's kind of a little bit hard to actually finding that securing that I would say like a really money having some money in for the job like that's like financial security job because like it's a little bit harder in Indonesia. And even in work, I obviously if you go as a biologist and in here that's my passion. But then I try to find something that is still related to my biology. It's still to related that with my passion, like in research. But what could actually make some money? And that's where I actually finding something like what is called data science. So this is like when I try to search during my master time, there's look at this webinar, became data scientist, and then I try to learning about it. And, okay, they're using a statistic, they're using a machine learning things, and then they try to use data to actually solving a business problem. And then it's actually using in a business. And then I realized, okay, could be my next career move. So at that time, during my master time, even like I'm not graduate yet, I try to learn as much as possible regarding data science. I try to joining this kind of online courses. I try to join it like a community in the social media, and I try to read it as much as possible. And then when I coming back from my master to back to Indonesia, I'm focusing on self-learning again, and then I try to join like really offline classes to the data scientists. Yeah, and then I try to make a connection as much as possible from all of my previous connection that I already have. Like, could I become a data scientist in your company? Basically, how like do you feel? Yeah, and then I by a little bit hard work, so I could say like from 2018 to 2019, so it's like 1.5 year work moving from this field, from the field, and then I become a data scientist.
Super cool. That's quite an impressive journey in such short amount of time. You managed to, to go through all these different levels because, data science can be tough, especially in the beginning when you want to get your first job as a junior data scientist with almost no experience, right? And you went from biology, not a so-called traditional data science study, all the way to the fields of data science. So let's talk about that. Can you talk about some of the challenges that you overcame when you were just starting out with no experience at all?
Yeah, there's like a lot of challenges. Even like when I first start as a data scientist, I don't know anything. I know it's a little bit about programming. I know a little bit about statistics. I know like a little bit here and there. But when you're already being in the corporate, basically, because like my big job right now as a generator is like in the corporate, there's like a lot of things to be learning, especially in the business part. Yeah, you can develop like some machine learning model. I mean, like you can try to running this code, but this is it solving this business problem? Is it like really valuable to our business? Is it like really could be convincing enough to be used by the business people and the business team, or even like from the customer part to actually they want to using this kind of my model, like my study, my learning. So this is actually something that I learned during my first year, if I'm like even until now, I still relearning like what is about the business itself. Because like as a junior data scientist, we are working in the below. We are working usually in the to execute, to performing what the task is going to be.
Right.
Corporate, but in a corporate, it's a little bit different. I think like in the startup that maybe you could try to like you could like do everything as yourself, like you could be creative. But in a corporate, it's having this little bit different because everything is already being structured, everything is organized already in there, and there's already business moving there, and the business is already know what they want. The business already know what could make money in there, and then the business already know what should be. Data science and new stuff. Data scientist could be there to automate stuff, could be try to invigorate all the new thing in the business. But as the data scientist itself, if you're like a junior, we need to understand why this business process moving. So for example, like in my previous experience as junior, like one of the first modeling that I create is like this called a propensity to buy model. So this is like it's like a modeling that try to predict which customer that could be approached to buy a new insurance basically or a new product. It seems easy. It's like you just take a data of the customer and then you could try to which one is the one who buy, which one would not buy, and then you try to create a modeling that's there. But the moving part is actually there's a lot of there's a lot of puzzle pieces in there. So yeah, you have the model, but what kind of product that you actually sell? Who's the target of the customer? Who's going to execute this list? Where's the communication is going to be? So and then how long it's going to be is it a campaign? How long is it going to be? Is it going to be like a continuous or is it like just a one time? There's like so much moving part in there, and then you need to like working a lot with the business. So that's one of the part that when I was like still engineer that I relearning. But that's actually one of the things that make my career actually boosted up because I really learned so much about the business, and I also learning about the communication within this business part. Because like I said before, like you want to convince the customer. I said like customer is basically this user, the part that you want to use this model. You want I can do my job, but can you believe my job? So they're basically like that. It takes like a really good translation between our technical to the business term, basically. So I kind of present my model as like, for example, like a random forest. This is like how this is work, and this is like this is the precision. This is like a recall classification model. No, they don't.
Right.
Yeah, but what I understand is like, for example, like I create a propensity model. This kind of modeling, when we are simulated, basically, it could have to your KPI. Basically, your KPI is made, for example, like income, like increase in the revenue in the monthly. It could increase the revenue 20% compared to the normal job that you do. And then it's simulation. So that is just an example. But this is like some kind of need to be rethinking compared from our technical to how the business actually speaking. So
I always call it translation, and I think I couldn't say it even better than what you just said. It's really important, also from my experience and from what I've seen in my colleagues. Being a data scientist is not just, crunching numbers. Many people think it's just statistics or maybe some mathematics or really data. But it's like you just said, all these different skill sets that have to come together, like business acumen, what you just mentioned, and communication, translation from business, to technical terms. Because usually the product managers will never come and tell you, please make a classification model for me to classify this thing. No, they just come and say, I need to do this. And then you need to realize that, you need a classification model. Oh, you need to select those approaches. And I think you perfectly mentioned that this is this combination of different things that from one view, it might seem very easy. But when you dive deeper, you clean the data, where to collect the data, where to store it, how to process it, how to make the impact, how to measure it. So I totally understand then how you could go and grow and, go through this corporate ladder very quickly, because early on in your career, you had an opportunity to learn and gain all these different skills.
And I think also for our audience, for our aspiring data scientists, this is definitely a note to make. If they want to grow quickly in their career, they need to be prepared to work on their communication skills, on their business skills, like you did, on their translation skills, how to translate from business KPIs, OKRs to an actual data science problems. On that note, since you mentioned very interesting project, was there any particular project in your journey early on when you were a data scientist as a junior or meteor that kind of made your career to, to be, to set yourself apart from other ones and be promoted?
Yeah, precisely. Yeah, that's like this. This is actually a little accumulative. I don't say that it's just like one project, but like, maybe I could try to a little bit to the beginning. So one of the things that I also try to do during my junior time, I feel like a medical, is to take an initiative. So I not
Right.
just move. I'm not just moving like, okay, this is your project, and then it's like you need to do this and that. But even like from my junior level, I'm not trying to taking like a job like that, but it's more like I try to communicate my boss like I know this is like a really interesting project. I want to take it, or like I know this is going to be having a good business impact. So can we try to talk at the very least with the business user? This kind of project we could try to create together. So this is like try to take an initiative on my own, on my career, so I could know where I could try to move during that time. But yeah, as this is accumulated, and this is like one project that I know like during that time, that this is the project that I done, which is called the NLP project. So it's basically trying to create a prediction which of the customer email was not a spam, sorry, have complaint or not. So it's like, like the customer sometimes like really complaining, but
Right.
yeah, but it's not just a complaint. What we want to try to predict is like, is this kind of complaint could be damaging to our reputation or not. So this is like the kind of the complaint that we try to predict. So in this time, this kind of project that I undertake is something that I could say try to make or break, because like this is about a kind of a project that was done before in our company at the very least. And then I try to say to the business user and my boss that I want to take this kind of project. I know this is like could be like really useful for our business. And then yeah, I will try to take a responsibility like from managing this kind of project. And then
Right.
yeah, it's going well. And then it's like, yeah, even right now, the business users still, what's it called? I still want to try to communicate with me for any kind of project, but in their business, because I already starting with this kind of project, and then I try to initiate it, and they still try to approach me if it's like they have like some kind of a problem with another initiative that they want to do. So it starts simple. It starts just from ourselves, but this kind of awkward things will be seen. Will be seen if like our boss, by your colleague, by your any business partner, and other. So just take an initiative. I think it's like some could be like really make or break your career. Not just break, it really make your career.
Understood. So kind of be proactive. If you you are already a junior data scientist, you already have some basic skills, you have worked with some senior data scientists under supervision a couple of months. Now it's time to take initiative to look around, network and see what kind of projects are on the table, and then go and try to make something from, even if something seems boring or uninteresting, you kind of need to dig deeper like you did, right? So
Yes.
you basically identified them and said to your boss, well, can I work on this? And if this is impactful, because at the end of the day, you will always go to next level if you are doing a project, if it has a lot of impact, right?
Yes, that's true.
Yes.
And then yeah, it's also at the finalist is still from my junior level. I already, if like before, if when I become a data scientist, right? I know what I want to be. I know what I want to do. And then when I
Right.
already become what I do, I'm not stopping there. I try to making what is called a master plan, basically. Like this is going to be my career, but I need to take into my hand, basically. This is also
Right.
what my boss always said like before. Like this is like already inspired to me. Like your career is in your hand, your life is in your hand. So every kind of move that you make, you need to be responsible for that. But it's also need to be something that make you improve as a person or as your career or as anything. So that's why I always try to take initiative in there.
And it worked out, right? Because
Yes.
now you are data science manager, you are top voice in
Mhm.
data science. So it worked out well, which is
Yes.
amazing. And on that note, given your non-traditional data science background, because you
Mhm.
have background in biology, and there are many people out there from our listeners also who want to make a career change or who come from a non-traditional data science background, meaning they don't have a traditional statistics, mathematics, or data science master's degree. I wanted to ask you, such that you can tell to our audience about the impact that your unique background had on your
Mhm.
career.
Okay. It's really interesting, yeah, because as a biologist before, I'm not using much about really regarding my education, like really the specific one, for example, like a gene or like a protein. Of course, I'm not using that in my everyday life, but it's more about how I try to methodologically thinking during my time of working as a biologist, as a researcher, really how I structure my work during that time. How do I using my statistic at the very least, I still using that from my biological thinking. And what's it called? And my education part, I think like really taking part, like how I could try actually break down a lot of like in the academic, because in academics you need to like break down like, for example, like the structure of your work need to be like from the theory, and then how do you do methodology, and then how this going to be work, the result and the conclusion. So all that my experience previously, it actually helping me working as a data scientist. But of course, like I know every person having like a different background. At the very least for myself, because I'm still from the science part, this kind of risk methodology could be really useful during that time as data scientist. But I know like there could be like a people coming from the literature, for example, like coming from the philosophy, like coming from uh language, and then there's something that was really not related to programming or like really data at all. But I think like it's like could have like a different unique perspective as well in there. At the very least, when you're approaching your work, it could be like how do you approach your work during your study could be applicable during you're working at the time. But at the very least, if you have already have the basic, I think it's could be already great, even if you are not from the data science major.
So you basically used on your advantage, all your background, even if it was a
Mhm.
non-traditional data science background.
Yes.
So what would be your advice to anyone who has this non-traditional background in terms of specific steps?
Yes. Having a roadmap for me is like the best one. So I know it's like a little bit a cliche, I think I would be going to say, but having a roadmap to follow is really helpful. So there's already a lot in the online, like right now, like how to become a data scientist step to step. First, learning statistics. Second, learn Python. Third, learning the machine learning. Fourth, having like the machine learning project, data science project. Five, like try to apply, try to communicate, try to learning the presentation. This kind of step maybe seems boring, but following those steps is actually important because like it really a structured way. Because like to become a data scientist, I'm going to say like it just starts small in there, but those step like even in terms of statistics, programming, and machine learning, it's going to be connected to each other, the skill, and it's going to help you to become a data scientist that you want. So just following the roadmap that I already have, it's going to be helpful. Rather than you try to learning yourself like jumping here and there, I would just take machine learning, then I try to just learn those kind of things. But then you forget
Right.
about the statistic, then you forget about the math, or you just learning about the programming, then forget about how to present it to the business user. Just following the step one by one, and then I think it could be already good.
So in an organized way, basically, to follow the roadmap. Yeah.
Yeah.
Okay. And have a clear plan, I suppose.
Yes, having a clear plan is actually really helpful because like as this is like coming from my own experience as well because like I try to create a plan for myself to become a data scientist and then I try to follow that plan and it actually worked. But
it worked out.
it is not well. But this kind of plan that actually I think really helped at the very least for me because like I know if we are not focusing because this kind of plan actually make you focus because if you are not focusing on that thing, you could just going anywhere and then lose your way to becoming like the data scientist that you want.
Right. No, I absolutely agree with you. Having a clear plan and learn in an organized way and not just to go from one course to the other one to try to learn everything. That would be indeed the best way because otherwise everyone will be spending a ton of time on learning one skill and then there is a new skill to learn by the time they finish another one. Yes. Amazing. And when it comes to leading, because you are a data science manager and you have gone through these different steps already and you are leading teams, what, in your opinion, is that helped you to balance the two? So the technical side and leading people, how do you manage projects and people and at the same time, you thrive in your career?
Yeah, that's really hard, I could say. But this is like something that I also learned during my corporate time because leading and then try to become an individual contributor, I could already say like it's the two different things. On one side, like in the technical part, we already understand. But become a leader to the people, we need to understand how to delegate, what kind of the task, what kind of project, and then trust the other that they could actually done it. And then by trusting each other, I trust myself and I trust you as a colleague. I would say like you are also my friend. Even like you are like I'm leading you, but it's also like you are a friend that in my side. We are working together in here. We are not just like the boss and then I try to, okay, you do this, you do that, and you are okay, bye. No, but we are trying to communicate together what are the problem in here, how we could try to work together in this here. But I try to not to micromanage, like I try to jumping in there, doing every stuff like you are do, but trusting the people and the delegate to the people is actually really important. But it's coming from the learning, of course. Of course, like as an individual contributor, I still really love coding. I still love programming. I do it right now. I'm still doing it right now. I really want to jump and get like doing this modeling and stuff at any time. But trusting the others is like, it's a learning to managing this project. It could be, you could do this and then learning that I could actually doing this stuff much better when I actually already been in this spot right now. But so yeah, it's still a learning process for me. I could say like it's still a learning. It's never ending journey, I could say. But delegating to the people that I trust, having a trust basically to the other is like the key important to balancing things.
On that note, because maybe some of our listeners who are aspiring tech people and who haven't worked in the field, they don't know this concept of individual contributor, what you just mentioned. Because for anyone who doesn't know this term, we have usually these two different career paths, right? In data science, when you just join, you usually join as an individual contributor. So you work on the technical stuff. And once you go through your career, there's usually two ways to go. One is the individual career and as an individual contributor. And the other one is the managerial path, which I assume is the one that you are following because you are managing people.
Yes.
So that's about that. You mentioned working as an individual contributor and then now you are a manager, which means that you are managing people and supervising them. And on the note of the trust, because that's something that you mentioned a lot when explaining your leadership skills, the trusting in others. But how do you build trust as a data scientist when you have just joined your data science job?
Yes, it's my proof, I think, because like, that's what I do. to build the trust with my boss, with my colleague. I proved that in my job, I could actually do it. And then yeah, I try to present how my result is going to be. And then I try to proactive at my work. Trust is not built just like by you saying it, but trust is built by you are having a proof of your work. Trust is coming from the things that you already did. It's from the action itself. I know like communicating is maybe not that easy as well, but but your work is is like a promise in there during that time. So I know like as a junior data scientist, like, yeah, I can do it. I can do it. I can do it. I said I can do it like that. And I know like people that I leading is like, yeah, I can do it. But how they work? So it is that's actually that work that actually making that the proof of the trust. So as a junior data scientist, I think the best way is like, yeah, just do the work. If like it's smaller, it like as you said previously, you mentioned previously, like it might be boring stuff, it might be unassuming, it might be not leading anywhere. But those kind of work show that you could actually do the work rather than just thinking. So that's the
Get
thing.
the work done, basically.
Get the work done.
Right. That makes sense. So then you can build the trust, make sure that you help your supervisor, because that's at the end of the day, the job of the junior data scientist, to help the senior data scientists and other leaders in the team to make their life easier, whether it's unfortunately data collection, data analysis or not. And on the note of leading the teams and becoming manager, in your opinion, how can one decide whether they want to take the path towards individual contributor, so become a principal data scientist and then stay like an individual contributor, or they should consider the path towards becoming a manager, data science manager? What qualities do you need to have to go towards one path or the other?
I think it's coming from yourself, because every single person have like a different evaluation, right, about what they can want to be. Like, for example, for my side, I love both sides. I already said like I love both sides, like as an individual contributor, as they are leading. I love both of them. So I want to try to actually having like this experience as a leader as well. So because I already have really good experience as an individual contributor, that's why I try to move into that side as well, to try to be in the leadership part. But of course, like it's coming back to yourself again. What do you want to do in your future? Because like I cannot tell like for every single person that you need to be like become a manager is the best path, because it's like have the best money, or like become an individual contributor is much better, because it's like really coming to yourself, or like your comfort zone where you want to be in the future. So it need to be coming to yourself. I mean, like every single path, career way have their pro and con. It's always like that. It's just like the decision that you already make. You need to be responsible for that.
That makes sense. So what it is to be a data science manager, walk us through your kind of day-to-day, your responsibilities for the listeners to get an idea what it means to be a data science manager.
Yes, unique in my case, I would say, like still leading the team, of course, like having like a meeting, like with the teams, and then having like managing the project. What's our project right now? How is it going? And then how is the progressing? So it's like managing the progress of the work in there, and then try to balance it with the business user, what their expectation is, and then translate it into the technical. So it could be actually making those kind of progress. So it's like balancing with everybody from every side as well. So I will say like those kind of work that I usually like the day to day. So managing the people, like how are you going to be like in this week, or what going to be in this day, and then they try to, when the business user coming, how do we going to make this project successful?
Right.
So that's the day to day basically.
That makes sense. So managing people, a lot of communication, meetings. So that's definitely also part of the managerial position, that's for sure. So if you don't like meetings and you don't like communicating with product people and business people, you should not choose for that path, right?
That's true. I would say like that's the con, because like I could say like if you see my calendar, of course, like the business meeting, it could be like 8, 9, 10, 12. It could be like there's quite a lot, and then it's like suddenly there's like random meeting. What do I need to join this meeting or not? But there's a
Right.
lot of
So
things. There's a lot of many meetings already.
yeah, for sure. No, I heard that a lot. So that's something for our listeners to take into account when choosing which career path they need to go through. And on the note of the projects, because you have been leading projects and you have been also going through the corporate ladder successfully as your data science manager now at such a young age. Can you remember maybe there is like a one project, an impactful one that you end up going through? It was a tough project, but you, with your team, have completed it. And what were the main takeaways from it?
There's like so many projects, but I think what the really impactful right now, if I like we still ongoing right now, is like we try to create this kind like a claim fraud detection project. So basically, it's like every company needed like a fraud detection model. This is like really impactful to the business because like like fraud usually not happening that often. But when it happens, it could be damaging to financial, damaging to the reputation, damaging to the everybody on their business. And then, this is like a really ongoing project that need a lot of consideration, like coming from this kind of business, like this customer, like where the data set is coming from. So it's like really involving a lot of business stakeholder and then a lot of technical person to be involved. So this kind of project that we are doing, I would say like taking a lot of people come and go because like even like this is like a really hard project. But at the very least, I would say it's like making an impact because like the business the business user using it, and then they try to trust our result. But there's always a lot of room for improvement because like at the very, I said before, fraud detection could be really damaging if we could not do it properly. So we need to present those results from this client fraud to be something that could be understandable by the business. So we try to create the model as good as possible. We need to have like the explainability as good as possible. We need to integrate all the business process as good as possible. So those moving part really right now are still the project that I really remember until now, that I try to even what's it called, in another project, those kind of work that I done there, I try to implement it in the other, because it's just like this kind of complexity really need to be taken into consideration.
Okay, amazing. Sounds as a tough problem. Fraud detection, if you have a high error rate, that can seriously impact your operations. Also,
Yes.
It's about money that we are talking about after all. And on the note of money, so you have gone through these different steps. You start as a junior data scientist usually, or as an intern in data science if you don't have any background at all, and you haven't completed any projects. And then you need to go through the steps. Usually you become a mid-year data scientist, and then you become a senior data scientist, and you become then a data science manager like you are today. So what it takes to get a promotion? Is it only the technical side, building that trust, like you just said, making an impact, or you also need to actively promote yourself? Because I know it really is different from companies to companies, but there are some common qualities that differentiate data scientists who stay in the same role for many years, even if they have a very good skill set, versus the data scientists who very quickly, like yourself, go through these different steps and get promoted a lot.
Yes. I think like in the corporate, I said before, it's really depend on the businesses as well, of course. At the very least, because promotion only coming first if there's like a business set, if you want like a business position to be filled, that's the first thing. Of course, like if you want to like having like a really higher position, it might not go it as fast as mine if your company doesn't even need it. But for a
Right.
promotion, basically for a promotion that increase your money, increase your financial security, increasing that. I believe that's the most important part actually, the financial, I think, like for most of the people. Like I know like some people doesn't need to be promoted, but they just want to have like a higher salary, but they also
Right.
bigger title. But in a corporate like mine, the biggest quality that, yeah, of course, like I said before, like taking initiative. I discuss it with my manager what my career I want to be as well. I want to be like, I said it before, like, can I get a promotion?
Oh, good for
I,
you.
yeah, I also asked like at that time, like, and then they tried, and then yeah, they what's it called? Negotiate basically. Yeah, we can do it like in this term of time with your kind of proof of work. We already been everything that already I've done. I already show it because like, but I thought just like 6 months. No, I'm not saying that in 6 months I said I can be promoted. No, but I try to build it during that time. Like, but it's actually like a year that I little bit promoted to I feel like to the medium to senior. I I asked. So it's really like an initiative to encourage because you don't even know like is it like a possible or not if you are not asking. I know like some company culture is like a little bit tough to do that. Like
Right.
so like it's like really shy or like even if it's not taboo, some people are just too shy. But it's really depending on the culture in the company because like in my company culture, at the very least, my boss is like really open. It doesn't matter if you want to say you ask to be promoted or not. It's like we are open discussion. But for the company that are a little bit strict, like a little bit taboo in that part, yeah, you need to take a little bit proactive, but showing you are the best in your work, showing that if I like compared to your colleague, yeah, I am the number one in there. I will say this is a big competition. I will stay if you want to be like in the current to be moving to the later. It's still a competition at the very end of the day. If you put it as a competition, but it's like a really healthy competition. If you want to get a bigger salary in there, yeah,
Okay, amazing. So basically, don't be shy to ask, because if you don't
yeah,
ask, you might not get it. Read the room, meaning you need to know who your boss is, whether he is open or he is not open to a conversation like that. So understand the company culture, whether it's fine to promote yourself, and kind of build that negotiation skill set, right? To
yes.
negotiate for whether it's higher salary or better business title, because sometimes that's also important
Mm-hmm.
for your position in the company. But do that on time, meaning before that, show your work, and only with right cards go and promote yourself, right?
Yes. You need to have a strategy basically for that. You need
Right.
not like a plan to do that. But yeah, I know like it's take a time, take a skill like to do that. I know like not everyone could actually brave enough to do that or like having like thinking to do that. Everyone is different, but of course like you could try to copy a little bit people's strategy. I know like in online, like if you like what I said right now, if you want to copy my strategy, like even after a year, after you work hard, you already taking initiative, you ask your boss, then maybe that strategy work, you could try to copy mine if your company actually having like a little bit like mine, could be like a really
Right.
open.
Okay. So that's a very good advice, I think, to not shy away to ask and know your strategy. Plan in advance.
Yes.
On the note on that, planning and on a personal branding. So planning your personal brand. Now, Cornelius, you have a huge following. You are a top voice on LinkedIn, and
Yes.
you have about 30,000 followers on LinkedIn, right?
Almost 30,000, still almost.
Almost. Yes. So go, if you are listening now, go and follow Cornelius.
Yes.
Maybe we can get 30,000.
Yes.
So how important it is to have a personal brand as a data scientist.
Yes, it's actually very important. So I will talk outside of my work because like in the my work, of course, it's useful, but outside of my work, it gives me a lot of chances. It gives me a lot of opportunity. Like right now with you, I'm talking with you because I already have a personal branding, right? You know, LinkedIn,
Right.
you understand me. it's opening a lot of door. So I get a lot of new friends, a lot of new networking, a lot of a career opportunity that offset of my job. So try to a lot of freelancers, a lot of writings. I love writing, so I try to focusing myself as in the writing as well, because like some of the people because a content creator who actually do like a video to actually like doing a TikTok, for example, or Instagram like photo. But I love article writing. I have like a newsletter. I try to make myself personal branding in there as a data scientist who love writing, and those make my career actually having like a, I don't say it's a side hustle anymore because it's already my hustle. It's become my personal hustle that improve my income, financial security. So this
Right.
personal branding could make you having like a more career choices. It could make you a lot of choices because like this. I read a lot about people who like a businessman, an entrepreneur. They usually not only have like one source of income, they have like a multiple. They're building here and there. And I see like this coming actually from the personal branding as well. They could actually coming to have like this kind of a source of income, the multiple, because they promote themselves. Like myself, like I try to promote this as a data scientist who know some of the stuff in the data science world. And then the opportunity keep coming. That's because I'm promoting here and there, and then try to having which this choice that could actually make in the future. And the first is the door opening. Is more so. In the case that maybe someday I get laid off or something, you never know in the company. You never know what could happen. If you like in my position, like something like so insecure right now, maybe in the future something really like this, like a crisis, financial crisis, and everyone being laid off, like or even like a pandemic before, like people that who seems like a financial security suddenly getting cut off. Like I see my personal branding right now as a security measurement as well. That I could try to make it a runway in the case of something that happening as well. So that's really important.
Yeah, for sure. Because like you just mentioned, in many parts of the world, also currently, there are many data scientists that are being laid off just because of the economic structure. And like the message what you are also giving to our audience is that your personal brand will not just be something for that scenario, but also for just in general. It opens many doors for you, new opportunities, new networks, new contacts. And also in case something happens, so you are being terminated, laid off for some reason, then that will be a great way for you to have a source of income. So not to put all your eggs in one basket. That's the message you are giving, right?
Basically, yes, very precisely.
And on the note of your newsletter, because you have a popular newsletter,
yes.
And it is called Non-Brand Data. Can you tell us more about that?
Yes, at first, I just call it on non-brand data because like it's really in the early years, or I try to create a newsletter and also branding. So I try to just not want to boxing myself in those branding that I could to be a data engineering or like a data scientist, like in the NLP or stuff. So I could try. So this kind of newsletter could talk about anything, but I find this related to data. But at the moment, right now, I try to talk more about two things. Like first, more about a career, so like a business in the career in that as a data scientist, like those tips, and that's like my opinion. But and the second one is talking more about the technical stuff. So I try to also still putting my technical knowledge in my newsletter. So try talking about the Python, MLOps, and then how to integrate it. So basically, I try to combine like I still understanding the business, but understanding the programming stuff, like technical stuff in there. It's still it's basically a data science newsletter that try to make you as a career data scientist to improve your career basically.
Amazing. So if you are listening now Make sure to check the non-brand data newsletter from Cornelius. Hit the subscribe button, and you will get a lot of help with your career, how to start a data science career, and also the technical stuff, like Cornelius just mentioned.
Yes.
Also, let's talk about the coaching that you do, because you have a TopMate link. And also way to provide your knowledge, so to coach other aspiring data scientists or people who are already in the field. Can you tell us more about what kind of coaching you do?
Yes, so it's more about how you could move as a data scientist in the career. Where do you want to move? I suppose, like I said before, we want to move into more managerial, or we want to move slightly more into the individual contributor. But basically, how do you want to move as a data scientist in your career? But of course, it is also open to coaching as like from a non data scientist yet that you want to move in, breaking into a data science field, and opening for the coaching for that as well.
Amazing. So if you're looking for a coach, then make sure to get in touch with Cornelius. He might be able to help you with your career, but also the technical part.
Yes.
He's on the TopMate, so we will put the link in the description. So on the note of the personal branding, let's say you have a person who comes and asks for your coaching services, or just in general, your advice. You have a huge personal brand at the moment, huge following on LinkedIn. What would be your advice, more in actionable way, how to build a personal brand from scratch?
Yes, I will come from my personal experience. First, I'm networking first, actually, before I posting anything much about that. But I already, I don't know, before I coming up with a plan of what I want to be. I'm a data scientist. I know what I know. Then I try to building that those going to be my brand. Those going to be about data scientists in here. Then I try to having like a networking, so the first time that I posting it, my social media, the post, of course, like it's not going to be like having like a lot of followers that reading it and how like a lot of people that are noticing it. But that's why I try to actually also approaching people that actually already having like those big followers. So I have like right now my friend, like his name is Calvin, but he's already not that much active right now in the LinkedIn. But he's the first one that I helping me going to the network in the data science field, in the LinkedIn as a data scientist. And then because of his follower, I get another follower as well. And then I start to getting more and more momentum in there. So it's just like knowing my brand, then try to networking with those people who are actually already having those number, basically, I would say. It's a number game, if you will say. But and then three, it's consistent. I'm consistently still posting it from my, it's already been 5 years, I think. I'm still consistent until now, try to posting something stuff. Even if like, I know like one of the things that make people kind of shy away after they posting their first post is there doesn't have like a lot of people that might be liking them or like comment to their content. But no, I mean like just keep posting it. I mean like every single post that you have might be valuable for someone. You might thinking that this kind of post might not, this is like just too easy, like people already know. But no, maybe someone is actually reading your content and then understand, okay, this is how you do it. Okay. People do that. I'm thinking about that before. Like, okay, maybe it's like not much left, but there's suddenly people actually say thank you regarding my post, and then it's like okay, that actually make my motivator higher. But in the first, that it might not showing that much, but just keep consistent posting because it's like it take a mental. I think like take a mental fortitude to keep posting, even like your situation is not that much. But of course, it's take a strategy to improve your social media and personal branding. So what I think going to be like before having your personal brand, having the network, and then keep consistent. I think those three is already being good enough if you want to build a personal brand.
Amazing. So
if you're someone who is listening and who doesn't yet have any personal brand, following these steps will help you to gain that personal brand online, but also offline. So on that note, Cornelius, do you think that having like coaching services, having a newsletter, and having a LinkedIn following, is that enough for your personal brand? And of course, also networking. Or are there any other media or channels that you usually use in order to build your personal brand as a technical person? I'm talking about, for example, GitHub, place to store and create and showcase your code. Also to showcase how you can tell a story about data.
Yes, that's true. Like GitHub is like really those is that community for a data scientist, not even data scientist, like every programmer, to have like those project portfolio to be shown in there. But also for myself, because I am a writer previously, and I don't do my projects previously, but really after writing, I using Medium to hosting all my article. I'm still quite active there, even but right now it's a little bit more in my newsletter. But depending on your passion, I think like a strategy, you need to a little bit branching. So for example, like my site go to Medium and GitHub. But maybe for example, like for some people that would like video, maybe you could try to have like a presence in the YouTube or like in the TikTok, because I know like some friends in there. Some of my friends is actually really active in the TikTok compared to the LinkedIn. But it's really need to understand as well what your audience want to be. What you want the audience that you want. So for example, like I like LinkedIn because it's like a really professional places, like a social platform. So there's like a lot of professional communication in there. So that's why I'm really active there, try to boost my building personal brand there. But maybe your personal branding want to target more into more casual people. Then maybe X might be better places. So I know like a lot of people in the X, like a big data people in there as well. There's a lot of followers. I try to post here and there as well in X, but it's mostly actually in Bahasa Indonesia. So maybe a little bit harder for not Indonesia speaker. But but if you're just starting, try to focus on one platform first. Having like a one platform, social media, then try to build from there, then try to branching there. But like GitHub, like Medium, I think that's just the medium way, just the places to show your portfolio. So I think it's like more about where you can show your working. But if you want to, I think it's like complementing your personal branding that you're already building in the social media, like GitHub, Medium, or like some other. It's like for the portfolio. But your starting places, then try to focus there, consistent there. I think that's one important part.
I think that's an amazing advice to keep it simple, because sometimes it can be overwhelming if you have so many social media or different channels that you need to keep up with. You will just run out of time or you will burn out. So start simple. Basically, that's what you are saying, and then they will all start to complement each other. So either X or TikTok or GitHub, Medium, or different other places, LinkedIn, Facebook. So it really depends on your target profile, like you just mentioned.
Yes.
Amazing. Let's now dive deep, become a bit more technical, because data science is such a buzzword. There are people who understand data science as data analytics. There are people who understand data science as this machine learning engineer. And with the revolution of AI, now there are many people who understand data scientists as someone who is dealing with MLOps, large language models, deep learning, machine learning, so many parts that many data scientists across the world are learning and are implementing. Now, in your opinion, as a data science manager with a wealth of knowledge and experience in the field, what is for you the data scientist and what it takes to be a data scientist?
Yes, this is still a question that I actually still asking, because like data scientist, previously I said is someone who working with the data to bring a value to the business. But right now it's moving much more than that as well. So it's like data scientist is someone who bring the value to the business and making the decision for the better in the business. But I always said a business because like a data scientist always need a business to working with, because like even if you're a solopreneur data scientist, your product will be need to be promoted in some way, then have like some business value. So that's why I always said that right now data scientist not just something that gives business value, but also someone who bring a better decision in the business. But yeah, to become a data scientist, I would say it takes a lot of mental fortitude. So like taking a consistency, taking a lot, want to learn all the way, every day, every year, every time, and always consistent learning.
Right.
And then almost like programming, business, I already said it before, so I don't need to repeat it again. But yeah, just want to keep learning and keep up with the latest technology. Latest technology, I believe in myself. I believe more that it's going to change the world. It's going to change the world. Like how AI right now is going to change the world in this day. So as a data scientist, try to keep following that technology, because if we don't following that technology, we will be, as I said, being replaced basically. And as a data scientist, we have like an advantage because we are usually working for creating that AI, complementing that AI, complementing theirs.
Right.
So,
on that note, I think you already answered my question, because I wanted to ask you, do you think that AI is a buzzword? Many people think that this new era of generative AI, ChatGPT, cloud, LLMs, it's a hype. It will just go away. But you just answered that, in your opinion, it's not going away anytime soon, and it's going to make a huge impact. So can you walk us through some of the recent developments that you are aware of and you believe are going to make a huge impact, and in which industry specifically, in your opinion?
Yes. If you want to talk about technology right now, we already have like a lot of tech generation. The open AI already having like a lot of the model that really good. Like the cloud is also like really have a really great model. I use like lately all day, and then I try to I feel like even like Sora right now already try to create out just image the video. But right now, what I really see is like the business as so like the non-technical people, because right now it's like the implementation is like just like for a coding or for a little bit simple stuff. But right now, like business people start to see how useful is that. Like a lot of not just like technical people, but like a non-technical people who are trying to build a product based on that. So yeah, it's just from myself. So this past 2 weeks, I already did like a lot of stakeholder. Basically, this in Indonesia are like a big stakeholder that actually they want to try to building this kind of AI product, and they try to using this AI to simplify their business process. Basically, even like even like in Indonesia, they already see the potential that it could be used. But of course, like right now, it's our job as well, like as a data scientist, to prove that this kind of AI to be actually useful in the business world. It's not just like the business want to use it and then they try to make it effort from their side, but we as a data scientist need to make an effort as well that yes, this AI could be useful for your business, and that it could be like as a proof that these two things that combine together, business and AI, is like become big. It could be like become a game changer. So, but yeah, that's why I really confident that like AI could actually change the world, because it's not just I personally using it and then try to get a benefit from there, but also everyone that I advise like from my side is actually already starting using it and then try to implement it in their business, and then it's actually useful.
Well, that's amazing to hear, because I am trying, when I'm hearing talks about AI will replace data scientists, I feel like that's something that is highly arguable. So first, I want to take your opinion on this. Do you think AI will replace data scientists? And how can you future-proof yourself as a data scientist?
Yes, I think it's not going to replace wholly. I think it's more like about some of the job that we, not just, yes, some of the tasks that we are done. For example, like maybe bug detection or like code generation. It could be like delegated to the AI. But of course, like restructuring all the code, where is the business going to be using it, and then where it's going to be managed, it's still taking a data scientist to do that. But that's why it's the data scientist just become evolving, right? Because like those tasks could be replaced by AI. We as a data scientist need to evolve as well. We are not just need to understand how to coding it really well, but we need to understand how to manage this code better. We need to actually document it better. We need to understand where it's going to be in the business, where it's going to be used. Which of us or data scientists is going to be really using this AI. So all this latest technology, we need to understand it as well. So that is what I will say, like data science need to become a full stack, and that is like cannot be avoidable on a horizontally, basically. And like I tried, like my path as well. Like I tried to learn a lot of MLOps, machine operationalization, because I don't think it's going to be replaced by AI as well. Because it need to be the structure. It could be need to be a data scientist who do that.
Yeah, I couldn't say it better because being able to become this full stack professional that you know both the data side, the machine learning side, the deep learning, but also the recent developments in AI, kind of at least high level to know what LLM is, what LLM ops is, those cloud technologies, how they can be used, right?
Yes.
And have also the business acumen and the communication, because if the product, there's always communication, right? Business versus data scientist. There's always a need for the translation. And as long as you are able to do so and continuously develop yourself with the technology, there is no way that you will be replaced. Because by the way, the other day I was reading that currently there is an 85% gap between the demand for data science and AI professionals versus the supply. So unless you are doing a manual job, I always tend to say that unless you do something repetitively that can be replaced by AI, you are good to go.
Yes, that's
so
true.
You should definitely have a motivation to get into data science if you like it. On the note of getting into data science, because you are now in the position of hiring data scientists, so what are the skill set that you are paying attention at? Because with this recent buzz, LLMs, generative AI, many aspiring data scientists, instead of starting with fundamentals, they start with the difficult stuff. Training neural networks, understanding RNNs, attention mechanisms, transformers, diffusion models, and then try to show with this project that they are an experienced professional. What do you pay attention at when you are hiring and you are getting these different resumes?
Okay. So the first thing that I don't pay attention much, is actually where the university is or where the GPA is. Or their age is, or their how background is, like almost if you are criminal, that's a different thing. But at the very least, those kind of discriminative, I do that. So I try to make everyone equal in the field. But of course, like when you are in a business, there's like a business needs. So the first thing, of course, like filling up the business needs when it's like a hiring. And as a data scientist, that what I do, that I see for a junior data scientist, I want to see if you could actually do the work. So basically, have you already at least do some data science project, already created some data science project? And then for this data science project, how's your thought process going? How's your, what motivated you to do this kind of project? What motivated you to do this kind of code? What motivated you to present this kind of result? So those data science project is actually what I really see. Of course, like having like an internship experience, having like job experience previously really used it out. I see that as well. But of course, like I know like this a little bit harder for a junior data scientist to aspirant data science to become a junior data scientist, because like the position is like really hard to fill. So that's why I try to at the very least taking a look at the data science portfolio project. So that's the most important part that I try to take in. For the, like a communication, like a business acumen, like for translating to the business, I think those kind of skill that I think will be you learn when you are already being in a business, inside the business. But when you are to enter in the business, you need to at the very least show that you can work for the task that you are going to be hiring for. And understanding, but of course, like understanding a little bit about the business is really helpful. It's still really helpful.
It's a plus.
Yeah, it is a plus. It's a plus point. But my starter point is like showing your data science portfolio, showing that you could actually do the work. That's what that main part.
Right. So a strong data science portfolio, basically. You learn the data science, communication, translation skills, business acumen, all plus, but extra. But for you as a hiring manager during the hiring process, you pay attention at the projects that they have completed, unless they have already an experience.
Yes.
So on that note, what would you suggest, like a couple of examples of such projects that you would suggest an aspiring data scientist who have zero experience, just fresh out of college, maybe even non-relevant data science education, to put on their resume to impress you?
There's a lot. I mean, like a lot of people that are impressed me because they're so smart. But I define is like using like there's like a lot of data set, right? Like that, or you can try to find it in the Kaggle or like in UCI, those kind of little bit complex data science project. But what will really impress me if you actually could formulate a business problem from those data set, and then formulate why you've developed this kind of modeling, and then this model that you develop is actually solving, or even not using a modeling. You're actually using the data set. No, you don't need a model, but you can formulate a business problem from this data set, and then you try to using the data science technique, maybe just a clustering technique, maybe just a customer segmentation technique or dimensional reduction technique, but could actually showing that this is how I could solve the problem from my business problem that I already formulate with this data set. And then I showing you that this is like how I do it. So that's the one that really impressed me. Because like what I want to see in your data science project portfolio is basically the thought process. And usually the thought process will come in instantly when you already have like this business problem that you want to solve. But of course, like the data set that already available in the public is maybe a little bit limited. But of course, like within this limited data set, if you could be creatively thinking about a problem and then try to solve it, it would really impress me.
Right. So from end to end, basically. And also have kind of this extra skill set than just solving the problem in technical way.
Yes, solving a problem in a technical way, you can say that.
Amazing. And one last question, because we've spoken about many important topics that I believe many aspiring data scientists would be interested in. What do you see as the future of data science in the upcoming 5 years?
Well, we're going to change a lot, I think, like with this all AI development and it's like you do this data science technical stuff that everywhere. I know like in 5 years, data science will be invaluable to the business. Like I said before, AI is like a buzzword previously, but micro is a buzzword that used by the business. And if the business could actually using it bets in the company in this 5 years, if it is 5 years, they will try to hire as much as the data scientists just to making sure that this is going smoothly. And then I'm pretty sure like a business in this 5 years will be using a lot of automation from our data science technique.
Amazing.
Now, Cornelius, thank you so much for joining us today. I think your insights and all your tips were invaluable for our listeners who are interested in tech and in data science. For our listeners, make sure to follow Cornelius on LinkedIn, but also to check his newsletter, Non-Brand Data. And if you are looking for a coach, then definitely go for Cornelius. He will be able to help you. Thank you so much, Cornelius. It was really a pleasure to have you here. Thank you so much.
Thank you, Tata.
So they're going to buy a business, and that'll be the base. And then on top of that base, we're going to add other businesses to try to help it grow, exponentially faster. And I used 100% bank debt to buy those 23 companies. And the net result is a tremendous amount of shareholder value created. Tesla could have come crashing down if the lenders started saying, enough is enough.
Joining us today is Adam Coffey, who brings over 21 years of experience in building businesses. Having served as a CEO for 3 major companies supported by 9 different private equity sponsors, Adam has managed transactions worth over $2.5 billion and advised top Fortune 500 companies. During his time, Adam organized 58 business deals and significantly increased company values, achieving 5-fold returns for investors. He grew one company's value from $10 million to over $1 billion, earning him recognition as one of the most influential leaders by the Orange County Business Journal. Adam is also a best-selling author, a popular speaker, and a mentor to aspiring leaders. His extensive background includes roles in healthcare, manufacturing, and beyond. His diverse skill set also includes being a licensed contractor, a pilot, an Army veteran, and a former executive at GE for 10 years. Today, we will dive into the proven strategies that aspiring tech entrepreneurs and fresh graduates need to thrive in today's competitive landscape. We will uncover invaluable insights on how to navigate the tech world, cut through the noise, build investor trust, and secure funding, as well as forge lasting partnerships. Finally, we will learn how to plan and execute a lucrative exit that maximizes your hard-earned success. The podcast will be hosted by Vahe Asnayan, experienced software engineer and a tech entrepreneur, the co-founder of LunarTech, that is on the mission to democratize data science and AI. So without further ado, let's get started.
Welcome, Adam. We are excited to having you join us today. Now, Adam, you are a pretty big deal in private equity and in business. Done deals over like 2.5 billion. You have also advised top Fortune 100 companies and written best-selling books on business. Adam, could you please share your journey and how you got to where you are today with our audience?
Happy to. And hey, by the way, good to see you. Good to be here with all your listeners out there. I think for all of us, life is a journey, and it's a building of a set of experiences that make us who we are. As a young person, I served in the U.S. military. Service in the military taught me something about discipline, teamwork, leadership. Engineering made me a meticulous planner. I'm a pilot. Pilots don't take off unless we know where we're going. So that taught me how, as an entrepreneur, to plan an exit from the beginning, and always have an exit and a destination in mind. I spent 10 years working for Jack Welch in the Camelot era of GE, I call it. GE was the world's #1 largest company, Fortune #1 on the Fortune 500 list. Company was growing so fast, it was doubling in size every 3 years. And that really informed my thinking about growth, and GE taught me how to run a business. Then I spent 21 years as a CEO building 3 different national companies for 9 different private equity firms. Bought 58 companies, a buy and build guy, turnaround guy. And, I've got $2.5 billion in CEO exits under my belt. That kind of led me to writing books, about how to do this. I wanted to educate. I'm turning 60 here shortly. And I wanted to start thinking about, legacy and how I wanted to teach the next generation of entrepreneurs and business owners how to excel at this game, at this thing, that's been so influenced by private equity. And that kind of led me to hanging up my CEO cleats a couple years ago. I started a consulting business. I've got clients all over the globe. I help them with scaling, with doing M&A, teaching them the tricks that the big institutional investors use to create shareholder wealth. And then, I help people exit. I work with private equity firms. I work with individuals and founders. I'm having a ball. I work more hours now than I ever did when I was a CEO. So much for slowing down. I think I've actually speeded up.
Awesome. And can you share a few stories on how you acquired new businesses and grew them and sold them, like the top businesses you worked on?
Well, so usually in my world, again, I've been doing this with large institutional shareholders. And so they always start with what's called a platform company. So they're going to buy a business, and that'll be the base. And then on top of that base, we're going to add other businesses to try to help it grow, exponentially faster. So if I take my last company as an example, the company that I was hired to run, so private equity firm buys a company, it's a platform company. It has 200 million plus in revenue. They buy it with a combination of debt and equity from their fund. And then they bring me in. The company has not done well, and time to bring in the guy to turn it around, to fix it, to get it scaling again, and then start doing a buy and build. And so I then bought 23 companies over a 5-year period. I bought 8 total in the first hold period, 15 in the second. And and started bolting on these other businesses to go from being regional to national to international, depending on which company I was building at the time. And in addition to growing through M&A, also then would focus on improving the business that I started with. So usually investing in technology, trying to do my best to increase the revenues, the profitability, and of the base business. And then also a lot of effort around organic growth to get the business that was underwhelming and not doing really well to grow like it had never grown before organically. And so I've learned how to build, I'll say, a very balanced growth-oriented company. But no question that M&A is the largest component of shareholder value creation. And on that example, those 23 companies that we bought, on average, I paid 5 times for each one of the companies. They were small, they were plentiful, or smaller, plentiful, and I used 100% bank debt to buy those 23 companies. And I used the cash flow of the 23 businesses to, service the debt while I'm collecting them, buying them. And then when we go to market, we sell it. And we sold for the first time a multiple of around 14 times. And so things I was buying at 5 times, I'm now selling at 14 times. And, the net result is, a tremendous amount of shareholder value created. Then you add in the organic growth, you add in the margin improvement, and that's kind of my recipe for the perfect exit. In that case, in my first exit, the 3-year period, it was a 4x multiple of invested capital. So shareholders were happy, investors were happy, management team was thrilled. We made a ton of money, and when things go well.
So as you know, like in the tech industry, the creating wealth is the opportunity is immense. But it's also like very competitive. Like we have many fresh graduates coming straight out of university and trying to make a new business, a new startup, but they have no idea how to do this. So what strategy or what mindset would you recommend them for our ambitious tech entrepreneurs who want to get their foot in the field?
Yeah, so tech is an entirely different world. You have to get to different concepts. Software as a service, or a tech-enabled platform definitely brings a higher valuation, call it at exit. But oftentimes, from a tech startup perspective, I'd say that a lot of people out there are trying to create the new next best thing. And oftentimes, I tell people, it's like, instead of trying to create something new that doesn't yet exist, potentially solve an old problem or put a new spin on something that's already out there. And I think too often it's like we try too hard as entrepreneurs to create something new, differentiated, that the world's never seen before. And sometimes boring old problems still need help and still need solving, and they can be updated and solved in a new modern fashion. And so I think sometimes entrepreneurs overthink complexity. And so when I am talking to people about what constitutes a great company, I tell them to think about human basic needs. Think about needs versus wants. In a bad economy, in a down economy, if my business is focused on needs, I'm not going to get hurt as bad. My revenue streams will be still fairly consistent. But if my product or my service is a want, then if I'm laid off or I'm unemployed or I'm feeling a pinch from high interest rates, I can slow down, I can avoid, or I can completely ignore that spend for an extended period of time until the economy comes back. And so we have to be concerned with just the cyclicality of the broader economies, in the world. We go through up cycles, we go through down cycles, and the world can throw us curveballs like COVID. And so we have to be very thoughtful around, if we're going to start something, I want it to be needs based. So, it's like if my roof was leaking and it's raining outside and I'm in my house, and water's pouring on my head, I have to fix that whether I'm broke or not. But if I wanted to put new fancy, accessories on my big monster truck out there, if I'm unemployed and I don't have any money, then I just look at the magazine and dream about what I would do, but I don't have the money, and so I don't do it. It's a discretionary spend. So needs versus wants. Then we want subscription-based versus, I'll call it project-based. We want some type of a product that customers are going to pay us a monthly fee for. It's shocking to me if I go to my credit card statements and I look for all the monthly fees I'm paying, for Adobe Acrobat and for Google Cloud and for Apple this or that. And it's like, I spend a fortune every month in just these recurring, contracted type charges. And, that's also the key to entrepreneurial success. Once I find a customer, I want to create a recurring revenue stream. Even in games, people might have a free game, but there's in-app purchases to help augment, and so if I'm thinking from a tech perspective, needs versus wants, contracted revenue stream versus one-time use or project-based, and then I'm thinking, in a perfect world, low capital expenditure, not a lot of money to further develop or refine a product once it's created, and it's creating a profile like that leads to high profitability, high free cash flow. And with high free cash flow comes the ability to service a lot of debt, which means buyers who want to use debt as a primary funding source, they can service a lot of debt because there's a lot of cash flow. So if you can build a business with high free cash flow, that's focused on needs, not wants, and as a recurrent contracted revenue stream, you're going to do much, much better.
Yeah, no, that's a great advice. Like oftentimes entrepreneurs start working on some kind of a new project. They think they are like working on solving a problem in a certain way, but actually they're like not solving like any form of new problem, and they end up hitting like a wall where they are like, but isn't already someone else doing that when they talk to an investor?
Yeah, sometimes boring, industries, and we solve a problem there, but they're a staple, or a mainstay of an economy. We can get a lot better traction, when we solve a common problem for common people, rather than create a new problem that someone doesn't know they have yet, and then have to convince them they need our product to solve that problem.
Yeah, 100%. And with startups, like many startups like need human capital. They need like some kind of capital to be able to employ new people, to be able to invest it in marketing or in other resources. Now, building trust is very important with investors because they want to know that they are investing in someone that's trustful and they're able to not only get their money back, but also get multiple returns. So how would you advise on new people entering the field on building trust with investors?
Well, this is the age-old problem and the age-old question, right? So chicken or the egg? I have no revenue, but I need people. venture capital investor says, I don't want to give you a bunch of capital that you're going to waste, on the come. I need you to be able to prove, proof of concept and prove that you can actually create these revenue streams. So it's a very delicate balance, and it makes startups a very difficult place to be. And oftentimes I ask myself, do I want to build or do I want to buy? And I'll look at the existing market in place, and I'll say, look, if I start from scratch, I have a very high probability of failure. I have a lot of hurdles that I'm going to have to cross. And I might ask myself, is there an existing company that has the existing technology or has the existing product that I can buy that's pre-existing? And as a result, I've got a company that has revenue, customers, a history of profitability, and then it's a different game. So in the startup world, we use things like founders equity, and we try to attract people by telling them, how rich they're going to be one day down the road in the future. And that's a hard sell, and I got to tell you, I get contacted constantly with people who want to offer me founders equity to help them. And you know what? I work for cash flow. I don't work for founders equity. And when I'm sitting on the boards of companies, they give me stock anyway. So I get stock in an existing company with real revenue, real customers, and I get cash flow. And so I personally won't work in a tech type startup world where there's founders equity involved. So I think we have to be realistic, and we have to profile. So anytime I need people, my goal and objective is to hire the best people I can find for the company that I want to be in 5 years, not the company I am today. And part of my tenets include I have to pay a fair market wage. But if I can't, because I'm cash constrained, then the only tool I've got is incentive equity to try to attract people. And then my profile might change. I may not be looking for an established executive who's used to making 7 figures a year because I have no money to pay them. And so I'm looking for a different profile. It's a younger person. It's an up and coming person. It's a person with great skills, but they live in their mother's basement, or they live in an apartment and their cost structure is low. They don't yet have kids. They're not yet married. And as a result of that, I can attract them with the equity potential and the lack of cash flow because their needs are lower. It's like I'm a 7-figure, 8-figure guy every year. And so it's like I don't work for free. I don't work for equity that may or may not pay off in 10 years. I work for cash and equity, and so we have to think about the talent that we need and where are we going to find it and how are we going to attract it and retain it. And so we have to build a profile for the type of person that we think would be uniquely qualified to go on this entrepreneurial journey with us, especially when we're cash constrained in the beginning and we just don't have the right level of capital. So I need brilliance on a budget, and I'm going to look for a profile of a person who's got low cash flow needs to where my small paltry salary will at least cover their basic needs because they have cheap basic needs but brilliant skills, and they're trying to become, call it the next tech billionaire or multimillionaire. They'll believe in the journey and they'll take and use sweat equity to get there.
Now, in your experience, how do successful companies balance innovation with sustainable growth? Like, for example, we have like a lot of businesses that are innovating, but they keep on innovating and in an unsustainable way.
A small tech entrepreneur who's trying to create something that has, legs, I'll call it, something that has long-lasting ability to build a sustainable revenue and future. At some point, we have to shift entrepreneurial gears and say, it's good enough. It's good enough for now. And our focus needs to be scaling. And then the innovation or investment, we don't necessarily want to stop, but we do need to throttle back. So if I've gotten to a proof of concept, I'm out in the marketplace, there is a point where we have to be thinking about, well, if I continue to spend money I don't have, innovating, while this is important, I'm never going to build a sustainable business if I don't also keep my eye on the ball and the fact that my investors need to see a return and I need to create, revenue. And so as I get out of the gates, I get out of the market, when I start to see revenue coming in, it's like we really have to drive revenue hard and show sustainable high levels of revenue growth and the high margins that we were hoping for. And we have to demonstrate this. And so we have a lot of initial effort to call it on the technology side to innovate and create the product. Once we get out and launch, that needs to scale back, and our efforts need to be replaced by focusing on marketing and sales and building the revenue stream. We have to remember, in order to build the best business in the world, it still has to be fed with cash. And investors eventually will run out of patience and pull out the rug from under us if we can't prove that we've got revenue. And so I think back to like Elon Musk in the early days of Tesla, or Jeff Bezos at Amazon. On any given day, Elon Musk could have, Tesla could have come crashing down if the lenders started saying, enough is enough. I'm not loaning you anymore. It's time for you, to either make money or shut down. And he was able to navigate that, as was Jeff when he was building Amazon. But the typical small entrepreneur isn't going to get that kind of treatment. They are not going to be able to sustain innovation and investment in a hope, in a prayer, if they cannot prove that money is there. So don't forget that while we may be interested in technologically changing the world, there's the commercial aspect of we got to make money. And before I worry about making money big, I need to prove to people I can make money small. And once I've got my product kind of to a stage to where it's ready to revenue, I need to turn down innovation, turn up marketing, and really focus on driving revenue creation and customer adoption so that I can then start generating cash, which will let me then go back to innovating, at a future time. So we have to be balanced. And a lot of times entrepreneurs forget the commercial aspect. And the commercial aspect is we got to make money. We're so busy innovating, we forget that we have to make money. And before long, it's like investors get tired of us because there's 1,000 other things for them to invest in. They pull the rug out from under us and we crash and burn. And so the best technology on the planet does not guarantee you commercial success. We have to drive commercial success as soon as we're able in order to prove the sustainability of our business.
No, 100%. And I feel like the ego has some kind of role in that, where like an entrepreneur is like very convinced because of certain reasons, but also their ego on why this innovation will only cause growth, although in reality it's only hinders their growth. Like, how would you?
That's why dreamers dream and doers do. So there's, I call it the accidental arrogance of success. It's like people get so into their own, self promotion that I'm God's gift and what I've done is going to change the world. And, I see those pitches every day from people who are out there. Adam, my idea plus your wallet equals, the best thing the planet has ever seen. And I'm like, first of all, if you're talking to me about money, you don't understand my value, because my value is what's up here, not what's in my wallet. Money is a commodity. There's trillions of it out there looking for investments right now. And so all you have to do is know where it is, go get it, treat it well, give it an outsized return, and you'll get funded. And so money is a commodity. Money's not the issue. People who are focused on money is my problem don't understand how money works. And so in addition to being, call it a tech genius, they need to have a business acumen, and or partner with someone who understands business. And they can be the strange person who's locked in the dark room for 20 hours a day, innovating and creating something great, but they still need some business guy out there to be the front end. And so when we get arrogant, and keep in mind, most of these people have not created anything yet, and so if they have an arrogance of success and they have it before they're actually revenuing and building something special, then boy, that's an entrepreneur who's going to have a hard time finding capital and finding money. There's a fine line between arrogance, and confidence, and we need to be confident. We shouldn't be arrogant. And if we're arrogant with no money and we're arrogant with an idea but no revenue, then investors just simply walk away. That's not an adventure that I'm going to back. So we have to be careful about letting the arrogance of our genius cloud our thinking, and ultimately investors see right through that. And if there's, it's okay to be arrogant, if you're the richest man on the planet and you have, you have arrived. When you have an idea and no revenue and you're arrogant with investors, that's not a good recipe for success.
And we are almost hitting the time. And could you tell us about your services? For example, we have new startups, but they have no idea how to do business. They don't have the business acumen. So maybe they can talk to you.
Yeah, so I do consulting work. People can read my books; they're cheap. I donate my royalties to charity, and all 3 of my books have been #1 bestsellers. So thank you to everybody out there who reads my books. I've been on hundreds of podcasts just like this. I do these freely so that they're, if you go to listennotes.com and type in my name in the search window, you'll find hundreds of podcasts that I've been on talking about these different concepts, and those are free. And from there, I teach seminars globally. Those are relatively low cost, and I'll do boot camps where we spend 2 to 4 days together, and I really get in depth about all things around growth and raising capital and selling businesses. And then I do work, one-on-one with dozens of entrepreneurs. I have a peer group we call the Chairman Group. I do that with my business partner, JT Fox. You can reach out to me on LinkedIn. You can go to my website, adamecoffee.com. You can also, I'd say LinkedIn is where you'll find me the most. I'm most active. It's really the only social media platform I'm on. Twitter, I post some things once in a while. I'm not on Instagram or Facebook. There's a fake Adam Coffee out there, believe it or not. I guess you've arrived when there's people who are intimidating you. And so on Facebook and Instagram, you'll find fake Adam Coffees trying to take money from you. I'm trying to help people, not bilk them for money. And so I'm a consultant, and I do consulting work with all kinds of different people, private equity firms, family offices, et cetera. So thanks for having me on. I appreciate you, appreciate your listeners out there. Good luck, take care of people, and revenue will happen.
Thank you, Adam.
The next question is, what is gradient descent? So gradient descent is an optimization algorithm that we are using in both machine learning and in deep learning in order to minimize the loss function of our model, which means that we are iteratively improving the model parameters in order to minimize the cost function and to end up with a set of model parameters that will optimize our model. And the model will be producing highly accurate predictions. So in order to understand the gradient descent, we need to understand what is the loss function, what is the cost function, which is another way of referring to the loss function. We need to also understand the flow of neural network, how the training process works, which we have seen as part of the previous questions. And then we need to understand the idea of iteratively improving the model and why we are doing that. So let's start from the very beginning. So we have just learned that during the training process of a neural network, we first do the forward pass, which means that we are iteratively computing our activations. So we are taking our input data, we then are passing it with the corresponding weight parameters and the bias factors through the hidden layers, and we are activating those neurons by using activation functions. And then we are going through those multiple hidden layers up until we end up with computing the output for that specific forward pass. So the predictions, y hat. So once we perform this for our very initial iteration of training the neural network, we need to have a set of model parameters that we can start training process in the first place. So we therefore need to initialize those parameters in our model. And we have specifically 2 types of model parameters in the neural network. We have the weights and we have the bias factors, as we have seen in the previous questions. So then the question is, well, how much error are we making if we are using this specific set of weights and the bias factors? Because those are the parameters that we can change in order to improve the accuracy of our model. So then the question is, well, if we use this very initial version of the model parameters, so the weights and the bias factors, and we compute the output, so the y hat, then we need to understand how much error is the model making based on this set of model parameters. That's the loss function. So loss function or the cost function, which means the average error that we are making when we are using these weights and the bias factors in order to perform the predictions. And as you know already from the machine learning, we have regression type of tasks and classification type of tasks. Based on the problem that you are solving, you can also decide what kind of loss functions you will be using in order to measure how well your model is doing. And the idea behind neural network training process is that you want to iteratively improve these model parameters, so the weights and the bias factors, such that you will end up with the set of best and most optimal weights and the bias factors that will result in the smallest amount of error that the model is making, which means that you came up with an algorithm and with neural network that is producing highly accurate predictions, which is our goal, our entire goal by using neural networks. So loss functions, if you are dealing with classification type of problems, can be the cross entropy, which is usually the go-to choice when it comes to the classification type of tasks. But you can also use the F1 score, so F beta score. You can use the precision, recall. Beside this, in case you have regression type of task, you can also use the mean squared error, the MSE. You can use the RMSE, you can use the MAA. And those are all the ways that you can measure the performance of your model every time when you are changing your model parameters. So we have also seen as part of the training of neural network that there is one fundamental algorithm that we need to use, which we called and referred as a backpropagation, that we use in order to understand how much is there a change in our loss function when we apply a small change in our parameters. So this is what we were referring as gradients, and this came from mathematics. And as part of the backprop, what we were doing is that we were computing the first order partial derivative of the loss function with respect to each of our model parameters in order to understand how much we can change each of those parameters in order to decrease our loss function. So then the question is, how exactly gradient descent is performing the optimization? So the gradient descent is using the entire training data when going through one pass and one iteration as part of the training process. So for each update of the parameters, so every time it wants to update the weight factors and the bias factors, it is using the entire training data, which means that in one go, in one forward pass, we are using all the training observations in order to compute our predictions and then compute our loss function and then perform backpropagation, compute our first order derivative of the loss function with respect to each of those model parameters, and then use that in order to update those parameters. So the way that the GD is performing the optimization and updating the model parameters is taking the output of the backprop, which is the first order partial derivative of the loss function with respect to the model parameters, and then multiplying it by the learning rate or the step size, and then subtracting this amount from the original and current model parameters in order to get the updated version of the model parameters. So as you can see here, this comes from the previously showcased simple example from neural network. And here, when we compute the predictions, we take the gradients from the backprop, and then we are using this dv, which is the first order gradient of the loss function with respect to the weight parameter, and then multiply this with the step size, the eta, and then we are subtracting this from v, which is the current weight parameter, in order to get the new updated weight parameter. And the same we also do for our second parameter, which is the bias factor. So one thing you can see here is that we are using this step size, the learning rate, which can be also considered a separate topic. We can go into details behind this. But for now, think of the learning rate as a step size, which decides how much of this size of the step should be when we are performing the updates. Because we know exactly how much the change there will be in the loss function when we make a certain change in our parameters. So we know the gradient size, and then it's up to us to understand how much of this entire change we need to apply. So do we want to make a big jump, or we want to make a smaller jumps when it comes to iteratively improving the model parameters. If we take this learning rate very large, it means that we will apply a bigger change, which means the algorithm will make a bigger step when it comes to moving towards the global optimum. And later on, we will also see that it might become problematic when we are making too big of a jumps, especially if those are not accurate jumps. So we need to therefore ensure that we optimize this learning parameter, which is a hyperparameter, and we can tune this in order to find the best learning rate that will be minimizing the loss function and will be optimizing our neural network. And when it comes to the gradient descent, the quality of this algorithm is very high. It is known as a good optimizer because it's using the entire training data when performing the gradient, so performing the backprop and then taking this in order to update the model parameters. And the gradients that we got based on the entire training data is the represents the true gradients. So we are not estimating it, we are not making an error, but instead we are using the entire training data when calculating those gradients, which means that we have a good optimizer that will be able to make accurate steps towards finding the global optimum. Therefore, GD is also known as a good optimizer and is able to find with higher likelihood the global optimum of the loss function. So the problem of the gradient descent is that when it is using the entire training data for every time updating the model parameters, it is just sometimes computationally not feasible or super expensive. Because training a lot of observations, taking the entire training data to perform just one update in your model parameters, and every time storing that large data into the memory, performing those iterations on this large data, it means that when you have a very large data, using this algorithm might take hours to optimize, in some cases even days or years, when it comes to using very large data or using very complex data. Therefore, GD is known to be a good optimizer, but in some cases it's just not feasible to use it because it's just not efficient. The next question is, what is loss function and what are various loss functions used in deep learning? So loss function is used in order to quantify the amount of overall error that the model is making. Whether it's a deep learning model, but also in general, the traditional machine learning models, in all these cases, we need a way to measure the amount of error that the model is making. And in order to do so, we are making use of this idea of loss functions. So loss function is a way to measure the amount of loss that the model is making, which means the amount of overall errors that the model is making when performing the prediction. So we can have a loss when we are dealing with classification model. We can have a loss when we are dealing with regression model. At the end of the day, we know that independent of the type of problem we are solving, we are always going to have these errors that we will have as part of the predictions. So we can never get predictions which are exactly equal to the true values that we want to get. Therefore, we need to know what are these errors that the model is making and what is the overall error that the model is making, such that we can then know how we can edit and adjust our model in order to improve it, such that the model will make less loss. Therefore, the idea behind the optimization techniques such as gradient descent, SGD, RMS prop is to minimize the loss function. But to be able to do that, we first need to have a proper loss function that is measuring the overall error that the model is making. When it comes to the different examples of loss functions, depending on the type of problem we are dealing with, we can use different sorts of loss functions. If we are dealing with regression problem, we can use the mean squared error, the root mean squared error, the MAA, which is another measure that is commonly used as part of evaluating the regression type of problems. So as a loss function, we can use this different matrix in order to compute what is the overall error in the predictions for that specific model type. And here we are using as an input the actual values of y's, which are usually numeric values, given that we have regression type of problem, and the estimated values, which come from our machine learning or deep learning model. So once we have per iteration the predicted values, then we can use these predicted values, these numeric values of y hat, and compare it to the actual y's that we have as part of our validation set, or training set, or testing set, in order to compute the amount of loss the model is making. So there is always this two set of input values, the y hat and the y. And then using mean squared error, which is the mean of the squared of all the sum of the errors that we are making as part of the model training, and then take the average of it. Therefore, it's also called the mean of the sum of squared of the errors. So when it comes to the classification type of problems, then for the classification type of problems, we can use the cross entropy, which is also known as a log loss, in order to evaluate the performance of the deep learning model. This is handy when dealing with a binary classification. When it comes to other type of loss functions that we can use for classification type of problems, we can use the precision, we can use the recall, we can also use the F1 score or the F beta score, which is more general version of F1 score, when we know specifically what is more important for us, the recall versus precision. Whereas in case of F1 score, we don't know or we don't care, and it's more that we want to have a good balance between the precision and the recall. Then the F1 score basically provides a 50% importance to each of those two. The next question is, what is cross entropy and why it is preferred as a cost function for multi-class classification type of problems? So cross entropy, which is also known as a log loss, it measures the performance of a classification model that has an output in the terms of probabilities, which are values between 0 and 1. So whenever you are dealing with classification type of problem, let's say you want to classify whether an image is of a cat or a dog, or the house can be classified as an old house versus a new house. In all those cases, when you have these labels and you want the model to provide a probability to each of those classes per observation, such that you will have as an output of your model that the house A has 50% probability of being classified as new, 50% probability of being classified as old, or the cat has 70% probability of being a cat image, or this image has a 30% probability of being a dog image. In all those cases, when you are dealing with this type of problems, you can apply the cross entropy as a loss function. And the cross entropy is measured as this negative of the sum of the y log p plus 1 minus y and then log 1 minus p, where y is the actual label. So in binary classification, this can be, for instance, 1 and 0, and then p is the predicted probability. So in this case, the p will be then the value between 0 and 1, and then the y is the corresponding label. So let's say a label 0 when you are dealing with a cat image, and label 1 when you are dealing with a dog image. And the mathematical explanation behind this formula is out of the scope of this question, so I will not be going into that details. But if you are interested in that, make sure to check out the logistic regression model. This is part of my Machine Learning Fundamentals Handbook, which you can check out. And this one includes also logistic regression, which explains step by step how we end up with this log likelihood function, and how then we go from the products to summations after applying the logarithmic function, so we get the log odds, and then we multiply it with the minus, because this is the negative of the likelihood function, given that we want to ideally minimize the loss function, and this is the opposite of the likelihood function. And in this case, what this showcases is that we will end up getting a value that tells how well the model is performing in terms of classification. So the cross entropy then will tell us whether the model is doing a good job in terms of classifying the observation to a certain class. The
The next question is what kind of loss function we can apply when we are dealing with multi-class classification. So in this case, when dealing with multi-class classification, we can use the multi-class cross entropy, which is often referred as a softmax function. So softmax loss function is a great way to measure the performance of a model that wants to classify observations to one of the multiple classes, which means that we are no longer dealing with binary classification, but we are dealing with multi-class classification. So one example of such case is when we want to classify an image to be from summer theme, to be from spring theme, or from winter theme. Given that we have three different possible classes, we are no longer dealing with binary classification, but we are dealing with multi-class classification, which means that we also need to have a proper way to measure the performance of the model that will do this classification. And softmax is doing exactly this. So instead of getting the pair observation two different values, which will say what is the probability of that observation belonging to class 1 or class 2, instead we will have a larger vector pair observation, depending on the number of classes you will be having. In this specific example, we will end up having three different values, so one vector with three different entries, pair observation, saying what is the probability that this picture is from winter scene, what is the probability of this observation coming from summer theme, and the third one, what is the probability that the observation comes from a spring theme. In this way, we will then have all the classes with the corresponding probabilities. So as in case of the cross entropy, also in case of the softmax, when we have a small value for the softmax, it means that the model is performing a good job in terms of classifying observations to different classes, and we have well-separated classes. And one thing to keep in mind when we are comparing cross entropy and multi-class cross entropy or the softmax is that we are usually using this whenever we have more than two classes. And you might recall from the transformer model introduction from the paper Attention is All You Need that as part of this architecture of transformers, a softmax layer is also applied as part of the multi-class classification. So when we are computing our activation scores, and also at the end when we want to transform our output to values that make sense and to measure the performance of the transformer. The next question is what is SGD and why it is used in training neural networks? So SGD is, like GD, an optimization algorithm that is used in deep learning in order to optimize the performance of a deep learning model and to find a set of model parameters that will minimize the loss function by iteratively improving the parameters of the model, including the weight parameters and the bias parameters. So the SGD, the way it performs the updates of model parameters is by using a randomly selected single or just few training observations. So unlike the GD, which was using the entire training data to update the model parameters in one iteration, in case of SGD, the SGD is using just single randomly selected training observation to perform the update. So what this basically means is that instead of using the entire training data for each update, SGD is making those updates in the model parameters per training observation. And there is also an importance of this random component, so the stochastic element in this algorithm, hence also the name stochastic gradient descent. Because SGD is randomly sampling from training observations a single or just couple of training data points, and then using that it performs the forward pass, so it computes the z-scores and then computes the activation scores after applying the activation function, then reaches the end of the forward pass and the network computes the output, so the y-hat, and then computes the loss, and then we perform the backprobe only on those few data points, and then we are getting the gradients, which are then no longer the
the exact gradients. So in SGD, given that we are using only a randomly selected few data points or a single data point, instead of having the actual gradients, we are estimating those true gradients, because the true gradients are based on the entire training data. And in SGD, for this optimization, we are using only few data points. What this means is that we are getting an imperfect estimate of those gradients as part of the backpropagation, which means that the gradients will contain this noise. And the result of this is that we are making the optimization process much more efficient, because we are making those parameter updates very quickly based on paths by using only a few data points. And training a neural network on just a few data points is much faster and easier than using an entire training data for a single update. But this comes at a cost of the quality of the SGD, because when we are using only a few data points to train the model and then compute gradients, which are the estimate of the true gradients, then these gradients will be very noisy. They will be imperfect and most likely far off from the actual gradients, which also means that we will make a less accurate updates to our model parameters. And this means that every time when the optimization algorithm is trying to find that global optimum and make those movements per iteration to move one step closer towards that optimum, most of the time it will end up making wrong decisions and will pick the wrong direction, given that the gradient is the source of that choice of what direction it needs to take. And every time it will make those oscillations, those movements, which will be very erratic, and it will end up most of the time discovering the local optimum instead of the global optimum. Because every time when it's using just a very small part of the training data, it's estimating the gradients, which are noisy, which means that the direction it will take will most likely be also a wrong one. And when you make those wrong directions and wrong moves every time, you will start to oscillate. And this is exactly what SGD is doing. It's making those wrong decision choice when it comes to direction of the optimization, and it will end up discovering a local optimum instead of the global one. And therefore, the SGD is also known to be a bad optimizer. It is efficient, it is great in terms of convergence time, in terms of the memory usage, because storing a model and that is based on a very small data and storing that small data into the memory is not computationally heavy and memory heavy, but this comes at the cost of this quality of the optimizer. And in the upcoming interview questions, we will learn how we can adjust this SGD algorithm in order to improve the quality of this optimization technique. The next question is, why does stochastic gradient descent, so the SGD, oscillate towards the local minimum? So there are a few reasons why this oscillation happens. But first, let's discuss what oscillation is. So oscillation is the movement that we have when we're trying to find the global optimum. So whenever we are trying to optimize the algorithm by using an optimization method like GD, SGD, RMS probe, ADAM, we are trying to minimize the loss function. And ideally, we want to change iteratively our model parameters so much that we will end up with the set of parameters resulting in the minimum, so global minimum of the loss function. Not just local minimum, but the global one. And the difference between the two is that the local minimum might appear as if it's the minimum of the loss function, but it holds only for a certain area when we are looking at this optimization process. Whereas the global optimum is really the mean, the real minimum of the loss function. And that's exactly that we are trying to chase. When we have too much oscillations, which means too much movements, when we are trying to find the direction towards that global optimum, then this might become problematic because we then are making too many movements every time. And if we are making those movements that are opposite or they are towards the wrong direction, then this will end up resulting in discovering local optimum instead of global optimum, something that we are trying to avoid. And the oscillations happen much more often in the SGD compared to GD, because in case of GD, we are using the entire training data in order to compute the gradient, so the partial derivative of the loss function with respect to the parameters of the model. Whereas in case of SGD, we learned that we are using just randomly sampled single or few training data points in order to update the gradients and to use these gradients to update the model parameters. This then, for SGD, results in having too many of these oscillations, because the random subsets that we are using, they are much smaller than training data. They do not contain all the information in training data. And this means that the gradients that we are calculating in each step, when we are using entirely different and very small data, can differ significantly. One time we can have one direction, the other time an entirely different direction for our movement in our optimization process. And this huge difference, this variability in the direction, because of the huge difference in the gradients, can result in too often of these oscillations, so too many of bouncing around towards the area to find the right direction towards the global optimum, in this case, the minimum of the loss function. So that's the first reason, the random subsets. The second reason why in SGD we have too many of those oscillations, those movements, is the step size. So step size, the learning rate can define how much we need to update the weights and or the bias parameters. And the magnitude of this updates is determined by this learning rate, which then also plays a role how different these movements will be and how large the jumps will be when we are looking at the oscillations. So the third reason why the SGD will suffer from too many of oscillations, which is a bad thing, because it will result in finding a local optimum instead of the global optimum too many times, is the imperfect estimates. So when we are computing the gradients of the loss function with respect to the weight parameters or the bias factors, then if this is done on a small sample of the training data, then the gradients will be noisy. Whereas if we were to use the entire training data that contains all the information about the relationships between the features and just in general in the data, then the gradients will be much less noisy. They will be much more accurate. Therefore, because we are using the gradients based on small data as estimate of the actual gradients, which is based on the entire training data, this introduces a noise, so imperfection when it comes to estimating this true gradient. And this imperfection can result in updates that do not always point directly towards the global optimum. And this will then cause these oscillations in the SGD. So at high level, I would say that there are three reasons why SGD will have too many of these oscillations. The first one is the random subsets. The second one is the step size. And the third one is definitely the imperfect estimates of the gradient. The next question is, how is GD different from SGD? So what is the difference between the gradient descent and the stochastic gradient descent? So by now, given that we have gone too much into details of SGD, I will just give you a high-level summary of the differences of the two. So for this question, I would answer by making use of 4 different factors that cause a difference between the GD and SGD. So the first factor is the data usage. The second one is the update frequency. The third one is the computational efficiency. And the fourth one is the convergence pattern. So let's go into each of these factors one by one. So gradient descent uses the entire training data when training the model and computing the gradients and using this gradient as part of backpropagation process to update the model parameters. However, SGD, unlike GD, is not using the entire training data when performing the training process and updating the model parameters in one go. Instead, what SGD does is that it uses just a randomly sampled single or just 2 training data points when performing the training and when using the gradients based on the 2 points in order to update the model parameters. So that's the data usage and the amount of data that SGD is using versus the GD. So the second difference is the update frequency. So given that GD updates the model parameters based on the entire training data every time, it makes much less of these updates compared to the SGD, because SGD then very frequently every time for this single data point or just 2 training data points, it updates the model parameters. Unlike the GD that has to use the entire training data for just one single set of update. So this causes then SGD to make those updates much more frequently when using just a very small data. So that's about the difference in terms of update frequency. Then another difference is the computational efficiency. So GD is less computationally efficient than HGD because GD has to use this entire training data, make the computation, so backpropagation, and then update the model parameters based on this entire training data, which can be computationally heavy, especially if you are dealing with very large data and very complex data. And unlike GD, SGD is much more efficient and very fast because it's using a very small amount of data to perform the updates, which means that it requires less amount of memory to store the data. It uses small data, and it will then take much less amount of time to find a global optimum, or at least it thinks that it finds the global optimum. So the convergence is much faster in case of SGD compared to GD, which makes it much more efficient than the GD. Then the final factor that I would mention as part of this question is the convergence pattern. So GD is known to be smoother and of higher quality as an optimization algorithm than SGD. SGD is known to be a bad optimizer. And the reason for this is because that the efficiency of SGD comes at a cost of the quality of it, of finding the global optimum. So SGD makes all these oscillations, given that it's using a very small part of the training data when estimating the true gradients. And unlike SGD, GD is using the entire training data, so it doesn't need to estimate the gradients. It's able to determine the exact gradients. And this causes a lot of oscillations in case of SGD. And in case of GD, we don't need to make all these oscillations. So the amount of movements that the algorithm is making is much smaller. And that's why it takes much less amount of time for SGD to find the global optimum. But unfortunately, most of the time, it confuses the global optimum with the local optimum. So SGD ends up making this many movements, and it ends up discovering the local optimum and confuses it with the global optimum, which is of course not desirable, because we would like to have the actual global optimum, so the set of parameters that will actually minimize and find the minimum value of the loss function. And SGD is the opposite because it's using the true gradients, and it is most of the time able to identify the true global optimum. So the next question is, how can we use optimization methods like GD, but in a more improved way? So how we can improve the GD, and what is the role of the momentum term? So whenever you hear momentum and then GD, try to automatically focus on the SGD with momentum, because SGD with momentum is basically the improved version of SGD. And as far as you know the difference between SGD and GD, it will be much easier for you to explain what is the SGD with momentum. So we just discussed that the GD suffers from oscillation, so too many of those movements. And a lot of time, because we are using a small amount of training data to estimate the true gradients, this will result in having entirely different gradients and too much of this different sorts of updates in the weights. And of course, that's something that we want to avoid, because we saw and we explained that too many of those movements will end up causing the optimization algorithm to mistakenly confuse the global optimum and the local optimum. So it will pick the local optimum, think that it's a global optimum, but it's not the case. So to solve this problem and to improve the SGD algorithm, while taking into account that SGD in many aspects is much better than the GD, we came up with this SGD with momentum algorithm, where SGD with momentum will take basically the benefits of the SGD, and then it will also try to address the biggest disadvantage of SGD, which is this too many of these oscillations. And the way SGD with momentum does is that it uses this momentum and it introduces this idea of momentum. So momentum is basically a way to find and put the optimization algorithm towards better direction and reduce the amount of oscillations. So the amount of these random movements. And the way that it does is that it tries to add a fraction of this previous updates that we made on the model parameters, which then we assume will be a good indication of the more accurate direction in this specific time step. So imagine that we are at time step T and we need to make the update. Then what momentum does is that it looks at all the previous updates and uses the more recent updates more heavily and says that the more recent updates most likely will be better representation of the direction that we need to take versus the very old updates. And these updates in the optimization process, these very recent ones, when we take them into account, then we can have a better way of and more accurate way of updating the model parameters. So let's look into mathematical representation just for a quick refreshment. So what the SGD with momentum tries to do is to accelerate this conversion process. And instead of having too many of the movements towards the different direction and having two different often gradients and updates, it tries to stabilize this process and have more constant updates. And in here, you can see that as part of the momentum, we are obtaining this momentum term, which is equal to Vt plus 1 for the update at the time step of t plus 1. What it does is that it takes this gamma, multiplies it by Vt plus the learning rate, eta, and then the gradient, where you can see that this inflated triangle and then underneath the theta and then j theta t simply means the gradient of the loss function with respect to the parameter theta. And what it's basically doing is that it says we are computing this momentum term for the time step of t plus 1, which is based on the previous updates through this term gamma multiplied by Vt plus the common term that we saw before for the SGD and for GD, which is basically using this eta learning rate multiplied by the first order partial derivative of the loss function with respect to the parameter theta. So we then are using this momentum term to simply subtract it from our current parameter theta t in order to obtain the new version, so the updated version, which is theta t plus 1, where theta is simply the model parameter. So in this way, what we are doing is that we are performing the updates in more consistent way. So we are introducing consistency into the direction by weighting the recent adjustments more heavily, and this builds up the momentum, hence the name momentum. So the momentum builds up this speed towards the direction of the global optimum in more consistent gradients, enhancing the movement towards this global optimum, so the global minimum of the loss function. And this then on its turn will improve, of course, the quality of the optimization algorithm, and we will end up discovering the global optimum rather than local optimum. So to summarize what this SGD with momentum does is that it basically takes the SGD algorithm. So it again uses a small training data when performing the model parameter updates. But unlike the SGD, what SGD with momentum does is that it tries to replicate the GD's quality when it comes to the finding the actual global optimum. And the way it does that is by introducing this momentum term, which helps also to introduce consistency in the updates and to reduce the oscillations the algorithm is making by having much more smoother path towards discovering the actual global optimum of the loss function. The next question is compare batch gradient descent to mini batch gradient descent and to stochastic gradient descent. So here we have three different versions of the gradient descent algorithm. The traditional batch gradient descent, often referred as GD, Simply, the second algorithm is the mini batch gradient descent, and the third algorithm is the SGD, or the stochastic gradient descent. So the three algorithms are very close to each other. They do differ in terms of their efficiency and the amount of data that they are using when performing each of this model training and the model parameters update. So let's go through them one by one. So the batch gradient descent, this is the original GD. This method involves the traditional approach of using the entire training data for each iteration when computing the gradient, so doing the backprop, and then taking these gradients as an input for the optimization algorithm to perform a single update for these model parameters. Then on to the next iteration when again using the entire training data to compute the gradients and to update the model parameters. So here for the batch gradient descent, we are not estimating the true gradients, but we are actually computing the gradients because we have the entire training data. Now, batch gradient descent, thanks to this quality of using the entire training data, has a very high quality. So it's very stable, it's able to identify the actual global optimum. However, this comes at a cost of efficiency because the batch gradient descent uses the entire training data. It needs to every time put this entire training data into the memory, and it is very slow when it comes to performing the optimization, especially when dealing with large and complex data sets. Now, next we have the other extreme of the batch gradient descent, which is SGD. So SGD, unlike the GD, and we saw this previously when discussing the previous interview questions, that SGD is using stochastically, so randomly sampled single or just few training observations in order to perform the training, so computing the gradients, performing the backprop, and then using optimization to update the model parameters in each iteration. Which means that we do not compute the actual gradients, but we actually are estimating the true gradients because we are using just a small part of the training data. So this, of course, comes at the cost of the quality of the algorithm. Although it's efficient to use only small sample from the training data when doing the backprop, the training, you don't need to store the entire training data into the memory, but just a very small portion of it, and we perform the model updates quickly, but then we find the so-called optimum much quicker compared to the GD, but this comes at a cost of the quality of the algorithm because then it starts to make too many of these oscillations due to these noisy gradients, which then ends up confusing the global optimum with the local optimum. And then finally, we have our third optimization algorithm, which is the mini batch gradient descent. And this mini batch gradient descent is basically the silver lining between the batch gradient descent and the original SGD, so stochastic gradient descent. And the way mini batch works is that it tries to strike this balance between the traditional GD and the SGD. It tries to take the advantages of the SGD when it comes to the efficiency and combine it with the advantages of GD when it comes to stability and consistency of the updates and finding the actual global optimum. And the way that it does that is by randomly sampling the training observations in two batches, where the batch is much bigger compared to SGD, and it then uses this smaller portions of training data in each iteration to do the backprop and then to update the model parameters. So think of this like the k-fold cross-validation, when we are sampling our training data into this k different folds, in this case batches, and then we are using this in order to train the model, and then in case of neural networks to use the mini batch gradient descent to update the model parameters such as weights and bias vectors. So the three have a lot of similarities, but they also have differences. And in this interview question, your interviewer is trying to test whether you understand the benefits of one and two, and what is the purpose of having mini batch gradient descent. The next question is, what is RMS prop and how does it work? So we just saw that RMS prop is one of the examples that can be defined as an adaptive optimization process. And RMS prop stands for the root mean squared propagation. And it is like GD, SGD, and SGD with momentum, an optimization algorithm that tries to minimize the loss function of your deep learning model to find the set of model parameters that will minimize the loss function. So what RMS prop does is that it tries to address some of the shortcomings of the traditional gradient descent algorithm. And it is especially useful when we are dealing with vanishing gradient problem or exploring gradient problem. So we saw before that a very big problem during the training of deep neural network is this concept of vanishing gradient or exploring gradient. So when the gradients start to converge towards zero, so they become very small, they almost vanish, or when the gradients are so big that they are exploding. So they are becoming very large and they result in a large amount of oscillations. Now, to avoid this, what RMS prop is doing is that it is using an adaptive learning rate. It's adjusting the learning rate, and it is using for this process this idea of running average of the second order gradients. So this is related to this concept of Hessian. And it is also using this decay parameter, which takes into account and regulates what is the magnitude, the average of the magnitudes of the recent gradients that we need to use when we are updating the model parameters. So basically, what is the amount of information that we need to take into account from the recent adjustments? So in this case, this means that parameters with large gradients will have their effective learning rate to be reduced. So whenever we have large gradients for a parameter, we will be then reducing the gradients. This means that we will then control the exploding gradient effect. And of course, the other way around holds true. In case of RMS prop, for the parameters that will have a small gradients, we will be then controlling this and we will be increasing their learning rate to ensure that the gradient will not vanish. And in this way, we will be then controlling and smoothing the process. So the RMS prop uses this decay rate, which you can see here too, this beta, which is then a number usually around 0.9. And it controls how quickly this running average forgets the oldest gradients. So as you can see here, we have this running average Vt, which is equal to beta times Vt minus 1 plus 1 minus beta times Gt squared. So this is basically our second order gradient. So then what we are doing is that we are taking this running average and then we are using this to adapt and to adjust our learning rate. So you can see here in our second expression, the theta t plus 1, so the updated version of the parameter is equal to the theta t, so the current parameter minus, so we are subtracting the learning rate divided to square root of this Vt, square root of this running average, and we are adding some epsilon, which is usually a small number, just to ensure that we are not dividing this eta to 0 in case our running average is equal to 0. So we are ensuring that this number still exists and we do not divide the number to 0. And then we are simply multiplying this to our gradient. So as you can see, depending on our parameter, we will then have a different learning rate and we will then be updating this learning. So by adapting this learning rate in case of RMS prop, we are then stabilizing this optimization process. We are then preventing all these random movements, these oscillations, and at the same time, we are ensuring smoother convergence. We are also ensuring that our network, especially for deep neural networks, it doesn't suffer from this vanishing gradient problem and from the exploding gradient problem, which can be a serious problem when we are trying to optimize our deep neural network. The next question is, what are L2 or L1 regularizations and how do they prevent overfitting in neural network?
So both L1 and L2 regularizations are shrinkage or regularization techniques that are used both in traditional machine learning and in deep learning in order to prevent the model overfitting. So trying to make the model more generalizable, like the dropout. So you might know from these traditional machine learning models what this L1 and L2 regularization do. L2 regularization is also referred as rich regression, and L1 regularization is also referred as lasso regression. So what L1 regularization does is that it adds as a normalization or as a regularization or as a penalization factor that is based on this penalization parameter lambda multiplied by this term, which is based on the absolute value of the weights. So this is different from the L2 regularization, which is the reach regularization. And this regularization adds to our loss function the regularization term, which is based on the lambda, so the penalization parameter, multiplied by the squared of the weights. So you can see how the two are different. One is based on what we are calling the L1 norm, and the other one is based on what we are calling L2 norm. Hence the names L1 and L2 regularization. So both of them are used with the same motivation, to prevent overfitting. What L1 does different from L2 is that L1 can set the weight of certain neurons exactly equal to 0. So in some way also performing feature selection. Whereas L2 regularization, it shrinks the weights towards 0, but it never sets them exactly equal to 0. So in this aspect, L2 doesn't perform feature selection and it only performs regularization. Whereas L1 can be used not only for shrinking the weights and regularizing the network, but also for performing feature selection when you have too many features. So you might be wondering, but how does this help to prevent overfitting? Well, when you shrink the weights towards 0 and you are trying to regularize this small or large weights, then these methods, such as L1 or L2 regularization, they will ensure that the model doesn't overfit to the training data. So you will then regularize the weights, and this will then on its turn regularize the network, because the weights will define how much of this behavior, erratic behavior, will be prevented. If you have too large weights and you reduce them and you regularize them, it will ensure that you don't have exploding gradients. It will also ensure that the network doesn't heavily rely on certain neurons. And this will then ensure that your model is not overfitting and not memorizing training data, which might also include noise and outlier points. The next question is, what is the curse of dimensionality in machine learning or in AI? So the curse of dimensionality is a known phenomena in machine learning, especially when we are dealing with these distance-based, neighborhood-based models like KNN or k-means, and we need to compute this distance using distance measures such as Euclidean distance, cosine distance, Manhattan distance. And whenever we have high dimensional data, so we have many features in our data, then the model starts to really suffer from the curse of dimensionality. So the complexity rises when the model needs to compute these distances between the set of pairs. But given that we have so many features, it becomes problematic and sometimes even infeasible to obtain those distances. And obtaining and calculating these distances in some cases doesn't even make sense, because they no longer reflect the actual pairwise relationship or the distance between those two pair of observations when we have so many features. And that's what we are calling the curse of dimensionality. So we have a curse on our ML or AI model when we have high dimension and when we want to compute this distance between pair of observations. And this can introduce data sparsity, this can introduce computational challenges, can introduce a risk of overfitting for our problem. The model becomes less generalizable. And it will also become problem in terms of picking a distance measure that can handle this high dimension of our data.